For hardware acceleration, we connect software to silicon. So we're working down typically the driver level to let applications get to the core silicon acceleration they need for things like 3D and machine learning, vision processing, stuff like that. And we have about 140 members. We've grown since last year from 120. So we're glad to have the participation of the industry to help us create all these standards. So for this session, we've grouped things into domains. We're going to cover the 3D standards, the APIs, and the associated file format, GLTF. We're going to talk about some of the heterogeneous compute, which actually we're not covering the rest of the day. So this is your one chance to kind of get an update on OpenGL, SYCL, and SPIR. And then we're going to VR and AR and inferencing and machine learning. And again, covering both the APIs and the associated file formats. So let's start with Vulkan, because it's SIGGRAPH. So 3D is where we should start. And I'm sure many of you here, well, who hasn't heard of Vulkan? Okay, no one. Oh, we're on a roll. So then, as you know, Vulkan is a new generation API. And like DirectX 12, and to a certain extent like Metal, it's low level and explicit. Gives you much more direct control over your GPU. Less surprises from the drivers, a lower latency, higher performance in the right hands. And the key differentiator between Vulkan, of course, and DirectX 12, which is on Windows 10, and Metal, which is on Apple, is that Vulkan is available pretty well everywhere. Not just Windows, but also Linux and desktop and the cloud. We have our first consoles on Windows 10, of course. And through portability layers that we'll be talking about later, we can actually now bring Vulkan apps onto macOS and iOS too. And we've launched Vulkan a couple years ago. We've already achieved pretty wide, pervasive availability. It's driver shipping from all of the GPU vendors. All the platforms out there have typically native Vulkan support. Everything from desktops into cloud services, VR platforms, embedded boards, drones and robots, consoles. The Nintendo Switch has fully conformant Vulkan drivers, and of course all of the games engines now have Vulkan backend. So we're doing pretty good in terms of getting Vulkan out there and available for developers to use. So this is a busy slide, and Tom, the working group chair, will have more time to go through this. But perhaps the key message here is the way we're developing Vulkan is we do a core spec, the first one, 1.0, February 2016. We test out new functionality with extensions, and then on a good regular heartbeat that the industry can cope with, we integrate those extensions into core, and then we start the process over again. 1.1 is still quite young. It launched at GDC, that's March this year, so just a few months ago. We already have a number of extensions that are shipping to 1.1, and there's a whole bunch of discussions in flight. And some of those, things like ray tracing, integrating video, better compute capability for Vulkan, are all critical things that will get extension shipping, and then in good time we'll bring it into core. And one of the key other messages is that Tom will really talk about this afternoon. It's not just the spec anymore. We're really putting a lot of effort into building out the ecosystem, the tools, the compilers, documentation, educational materials, and we're widening the platform support with things like the Vulkan Portability Initiative that we'll talk about. Lots of content is beginning to ship. I mean, the API is only a couple years old, but we do have content on desktop, including Vulkan-only content. There's lots of content on mobile, because of course Vulkan is the high-end API for Android. Android still has OpenGL ES, but if you want the best performance and your phone supports it, then Vulkan is the way to go for your truly interactive 3D applications. And a good example, kind of hot off the press, is Fortnite from Epic is now shipping on Android. And if your phone supports it, Fortnite will run on Vulkan for the best performance. So this was announced at the Samsung Unpack event for the Galaxy Note 9, and Fortnite on Note 9 now does use Vulkan for the best performance. That's pretty cool. Tom will go into more detail here too, but this is the SDK downloads for Linux and Windows, and we also now have a Mac SDK, and all the lines are going up. There we track the number of open source projects, and that line's going up too. So again, come to the Vulkan session later on for more details. The Vulkan Portability Initiative is something close to my heart. This is enabling many people that want to create runtime libraries that would map Vulkan apps onto underlying APIs. And that might be Metal, if you're going towards an Apple platform. It might be DirectX 12, if you're going to a Windows UWP platform. And the initiative that we have inside Khronos is we're firstly doing research to figure out how to port Vulkan onto those underlying APIs. And that research is going pretty good. For Metal 1, for example, there's about 5 things that we can't port efficiently on top of Metal. And that list gets even smaller with Metal 2, which has just been announced. Then we're creating a portability extension, and that lets libraries communicate to the applications. I'm a library, I'm not a conformant Vulkan, these are the things that are missing, but we can do that in a standardized way. And then we're developing SDKs, tools layers, so people can develop painlessly against those subsets. And we're encouraging multiple third-party implementations to take advantage of that infrastructure. One of the first is MoltenVK, which is now in open source. It's already being used for production applications. So Dota 2 on Mac has been upgraded. It's a free upgrade for hundreds of thousands of users out there, and that's coming from Valve. LunarG is shipping the Mac OS SDK, and we're making good use of SPIR. We'll talk SPIR-V in a moment briefly, but SPIR-V is at the center of lots of these cool things we're doing with compilers to take code from one platform to the other. And this app's getting pretty good performance. The Dota 2, the production version on Mac OS, it's actually getting up to 50% more performance than the native OpenGL drivers on the Mac platform. That's partly because the layer is actually pretty efficient, and it's partly because they did actually take some advantage of Vulkan over OpenGL. But nevertheless, it's delivering pretty good performance, and it's proven to be very stable. And we've actually had the first iOS iPhone apps ship through the App Store using MoltenVK. But MoltenVK is not the only implementation. Mozilla are driving GFX RS, which is another implementation of portability subset running over their Rust-based GFX HAL API. And that's actually given pretty good performance. They've put quite a lot of effort into optimizations. It's running across a range of Mac hardware. Valve have given them the Dota 2 to try, and that's running pretty well on the Mac platform. So this is kind of looking to the future. We're going to have more and more portability layers enabled to take Vulkan onto many different platforms with a good tools infrastructure around them. Of course, let's not forget OpenGL and OpenGL ES. OpenGL ES is 15 years today. And it's still the most pervasive 3D API out there. It's shipping currently on all mobile phones, so it's billions of units. And we have we've merged the working group meetings. Now we have OpenGL and OpenGL ES, the working groups are meeting together. And we're evolving the specs, we're evolving the conformance tests. We've just put the conformance tests into open source. So OpenGL and OpenGL ES are going to be around for another 15 years, 25 years in the case of OpenGL. These APIs are not going anywhere. They're being maintained and evolved as the industry demands. Of course, OpenGL ES was the thing that enabled WebGL. OpenGL ES 2 was really the first pervasively available 3D API across all the platforms that enabled the browser vendors to bring WebGL layered over OpenGL ES 2. Now we have WebGL 2, which is using all the good desktop functionality that comes in with OpenGL ES 3. And unfortunately, Apple didn't ship ES 3.1 So compute shaders is more of an issue, but we do have compute context and other extensions like the multi-view context coming as extensions to WebGL 2. So WebGL 2 is getting pretty pervasive. We're going up the ramp pretty well. WebGL 1 is like over 90% pervasively available on browsers today. We have Mozilla and Google shipping WebGL in production browsers now, and Microsoft and Apple are coming soon. And when they turn on, we'll get pretty much up to the same level as WebGL 1. So I think the next year or two is going to be where we see a lot of web 3D apps take advantage of the new functionality in WebGL 2, and we'll see some of examples of that in the WebGL BOF coming up later this morning. GLTF started out as a companion to WebGL, but it's evolved into something much bigger than that. The idea was we needed to have a highly efficient transmission format, a last mile transmission format for 3D. Audio has it, video has it, images have it. Images have JPEG, which you can use anywhere easily. 3D didn't have anything like that, and so we created GLTF, which is compact, easy, fast, describes full scenes, not just geometry, but animations, textures, lighting, and is open and extensible. And GLTF 1 used GLSL because it was for WebGL, but GLTF 2 was really when things took off. Microsoft joined, became a spec editor, helped us bring physically based rendering into the spec, not just tied to WebGL, but to DirectX, Metal, Vulkan, OpenGL. And it's really become the lingua franca now for how you transmit 3D assets into hundreds and thousands of different apps and engines, not just on the web, into native apps too. A lot of the GLTF development is done in the open. We have lots of discussions on the open GitHub. You don't have to be a Khronos member. So if you have ideas on the roadmap, or you find bugs or issues or comments, questions, come onto the GitHub. We do interact a lot there, so you would be most welcome. And I put it in, it's so cool, Ken's going to laugh at me. This is a GLTF model. So I don't know if people realize that Windows 10 has become like a 3D capable OS around GLTF. You can click on a GLTF file, you can drop GLTF files into your PowerPoint, and everything kind of works. And I'm actually going to break the illusion. This is a 3D model. So you can actually position it on the screen, and you can resize it, and it will work. It's actually pretty cool. And you can put the model onto successive slides in a PowerPoint presentation. It will use those positions on the slides as like keyframe in a keyframe animation sequence. So check it out. GLTF ecosystem is getting broader and broader. Every time we do this slide, we have to reduce the point size. Lots of engines on the right-hand side, including Office that we just saw, Facebook, Unreal, Unity, lots of the VR and AR engines, lots of the web engines, more and more tools, and all the repositories are beginning to provide GLTF versions of their models. Some of the recent highlights, particularly we want to put a spotlight to, we mentioned Microsoft bringing GLTF in as a fundamental part of Windows. Microsoft have also they had an internal SDK that they were using for doing their GLTF work. They've just put all of that into open source, so that's cool. TurboSquid have just upgraded their repository, and they're using GLTF. Facebook, you can drag and drop GLTF models onto your feed. Sketchfab has now over 150,000 royalty-free GLTF models. Adobe, their Dimension tools for creating marketing materials can now generate 3D materials, and that last mile transmission uses GLTF. Mozilla integrating GLTF into Hubs, which is their VR meeting space. Open Geospatial Consortium, so it's not just games and web, it's like professional, high-end. The Open Geospatial Consortium are now referring to GLTF and some of their standards for the 3D asset transmission. And then last but not least, for Google, we can now import GLTF into AR Core, and we've been working on the Draco compression, mesh compression technology is now shipping as an extension. And Patrick's going to talk more about the roadmap, but we have to be very careful around the GLTF roadmap because we can't let GLTF become too complex. Complexity is the enemy, though of course we all want functionality, we have to get that balance right. Things have to be consistent and reliably available. So we're kind of taking a similar approach to Vulkan where we put things into extensions first. Some extensions that are domain specific might just remain as extensions forever, so we don't load the base core spec. But extensions that everyone probably want, like Draco mesh compression, will make their way into a core once we've enabled the ecosystem to implement reliably and for everyone who needs it to ship that functionality. One of the key new texture, key new extensions to GLTF is kind of the companion to mesh compression, which is texture compression. And we're working with a bunch of folks, the binomial folks in the working group to define a universal texture format that can be super compressed, similar to JPEG, but it's much more amenable to efficient and high quality unpacking into the native GPU texture formats. We think we can support pretty well all of the texture formats, everything from BCE1 up to ASTC, and that transcoder is quite efficient and low cost. So this is going to enable folks to have one universal texture format, and you can send it to any hardware platform and you'll enjoy GPU accelerated texture when the app actually ships. And that's being worked on. So you'll probably see a provisional spec in the next few months. So let's move on to virtual reality. How are we doing on time? Not too bad. So virtual reality and augmented reality too. We have our portable VR AR spec. It's called OpenXR. We use the X because some people like A, some people like V, some people like M. So we said, screw it, let's have X. You can have any reality you want. And we have this current problem that fragmentation, it's all the first generation VR SDKs, because they were developed in parallel, they have proprietary APIs to things like tracking and input management, and means the applications and engines have to port to each independent engine separately. Also to the devices, if someone creates an innovative new hand tracker, they have to beg, borrow, steal engineering cycles from the VR runtime folks to get their devices integrated into those runtimes. And classic fragmentation problem, OpenXR is trying to address both of those by defining an application-facing interface that all the apps can use and only write once, run everywhere, and also a device integration layer for the runtimes that enable new devices to be installed. It tends to be more on the desktop rather than mobile, obviously, but for those platforms that want to, they can expose a device integration layer that enables someone with a new tracking device, for example, to self-integrate with their own drivers so they can ship on a lot more platforms. So it's a win-win-win. The apps get to run on more platforms, so they sell more. The devices get to integrate into more platforms, so they get to sell more. And the platforms get access to more apps and devices, so they get to sell more too. It's hopefully going to remove a lot of confusion and friction in the industry. We have kind of a who's who of the VR and AR industry helping us put this together. The latest joiner, which we just managed to add yesterday, is Magic Leap. They've just joined Khronos and now have asked for their logo to be added to this slide. This is not a guarantee that they will ship, but it's a positive indicator of positive interest in the initiative. And what we're finding is all these companies, with such amazing expertise, they're bringing their learning experience from their 1.0 APIs that everyone's kind of shipping today. So not only are we creating a cross-platform API, we're kind of integrating that learning experience from the first time around. And so we're kind of creating a 2.0 level API, which I think is going to be cool for the industry. We've been developing the spec since April 2017. That's when work actually started. We want to get this out as soon as we can. We gave some architectural information at the PowerPoint level at GDC just a few months ago. And we have hit another milestone here at SIGGRAPH. We're actually doing the first public demonstrations. And you'll see those at the BOF, on the OpenXR BOF, which is at 1 p.m. You say, well, wait, you don't have spec. How can you be showing demos? Well, it's a normal Khronos process that the Khronos members that are working to put the spec together do implementations before we do the final bake on the spec. Because you can read a 400-page spec for months and it all looks perfect, and you start to code to it, and in the first 30 seconds you say, well, that doesn't make any sense. And so going through that implementation and usage loop really helps us polish the final spec. So we're at the stage now where multiple OpenXR implementations exist. That'll let us get to a provisional spec pretty quickly. And once that's out, we can finalize the conformance tests, finalize the implementations, and then we can bake the final spec. It's getting pretty close. The demos that we can show today has 2 implementations of OpenXR. It's running on the new STAR-VR HMD and the Microsoft Windows Mixed Reality headsets. So both STAR-VR and Microsoft have prototype OpenXR implementations, and they're running the Epic Showdown VR demo using OpenXR. You don't have to change any code to go from one system to the other. So the age of portable AR and VR has arrived. And I mentioned that the 2.0 level design, I mean, a lot of care and attention going into making the spec future-proof. For example, the input framework, its layers of abstraction. So a portable app might find itself running on anything from a mobile phone to a desktop-based VR system. The input devices are going to be different. The input UI is going to be different. So OpenXR lets you map actions within the app to physical device interactions. So once you've done that mapping, then nothing else in the app has to change. And the other thing, of course, that can change from system to system, and OpenXR helps with, is helping the app configure its viewport configurations. OpenXR doesn't do rendering. You'd use Vulkan or DirectX or some other 3D API to actually push the pixels, but pretty much everything else you would want to do in an AR/VR app. Well, a VR app for 1.0, AR for the next generation, goes through OpenXR. So again, the app might find itself running on a phone with one viewport up to a stereo cave. You need 12 viewports. OpenXR lets you query and control all of that. And it's interesting, I mean, OpenXR is, again, like most Khronos APIs, is the foundational level. And of course, there's lots of companies doing awesome stuff on top. And in particular, for AR, I believe and many people believe that the web is going to be the metaverse. And so it's critical that we make sure that OpenXR is servicing not just the native stack, along with Vulkan, but also the web XR stack with OpenGL. So I'm glad to report that we're working very closely with the WebXR group that's bringing XR functionality into the web stack. But again, using WebGL and OpenXR is going to save those guys a bunch of work. So we're glad to be working with them. And it's interesting, OpenXR 1.0 primarily focused on VR. That's a deliberate minimum viable product. There's a real urgent need for VR. Let's get that out as soon as we can. But of course, AR is key too. And companies like Google and Apple are actually doing really amazing work with ARKit and AR Core on your mobile phone. But of course, they're proprietary, and you might need them on different systems. As OpenXR begins to integrate AR technology, it's going to be similar, I think, APIs to ARKit and AR Core. Find a ground plane, find vertical stuff, put a marker, and attach an anchor into the scene, that kinds of stuff. And so OpenXR can become not just a portable VR API, but the portable AR API. How are we doing on time? Okay, doing okay. Don't panic. So, neural networks. I know it's not like core SIGGRAPH, but it's important. I mean, inferencing and machine learning is around the show a lot. And so we have some stuff that's going on in that domain. This is the part that's not going to be covered elsewhere during the rest of the day. So this is a bit of a complicated slide, but it has one central message that machine learning comes in two halves. On the left, we have the training, which typically happens on high-end desktops or in the cloud. You typically have lots of GPUs or TPUs, 32-bit floating points, no problem. You have lots of awesome training frameworks, typically in open source, and they're evolving super fast. And over on the right-hand side, you actually want to deploy those trained networks onto edge devices. Your security camera wants to run a neural net to figure out whether it's a member of your family or an intruder or something like that, or robots, drones, autonomous driving, inferencing, low cost, low power, hardware accelerated is about to be everywhere. And we need something to link to. And an exchange format, just like GLTF for 3D, but for trained neural networks, is where NNEF is focused. It's an exchange format that lets you encapsulate a trained neural network, and it has features in there that let you optimize and compile that framework for best performance on your target hardware. And the target hardware can be anything from GPUs, DSPs, FPGAs, dedicated gates. Now, there's actually two initiatives out there, and both are awesome. There's NNEF, and then there's Onyx. Onyx is from Facebook, and with support of many other companies like Microsoft. Onyx is an open source project, and it's doing awesome work in tracking all of the authoring frameworks, and you can interchange between authoring frameworks with Onyx. I think the guys are doing a really good job. NNEF has a different focus into bridging into the hardware community. So there's some different design constraints. The hardware, a low-cost DSP might only have 8-bit integer, or if you're an FPGA, you might have 3-bit integer. And NNEF has variable precision, so you can go from anything from 64-bit floating point all the way down to 1-bit integer. And we have compound operations, which means you can compress a subgraph in your net to reflect your hardware architecture. You can, if you have like TensorOps, you can start compressing your tree into TensorOp operations that will map well onto your accelerator. So there's lots of commonality, and we're interested to see how we should cooperate. But it is interesting we have these different design perspectives. And we found the same thing. It's the velocity of open source can be awesome, particularly when you're tracking all of the training networks. But if you're trying to build a hardware pipeline and deploy devices, sometimes if you change everything too fast, it becomes an issue. We actually found that with OpenCL. We tried to use LLVM originally as our intermediate representation, but we kept getting broken by non-backward compatible changes in LLVM, so we had to invent SPIR-V. Now, we still love LLVM, but there's different requirements for different parts of the pipeline. So here at the show, we have released NNEF version 1.0. It's been out in provisional release since December. We've got some awesome industry feedback, but that's been baked in, and now we're final. Now we're building out the open source tools around the format. We already have exporters from TensorFlow and Caffe. We're doing importers, exporters from TensorFlow and Caffe 2. We have a syntax parser and validator. So if you are doing a hardware implementation and you have your own hardware compiler, and you want to parse and validate an input NNEF file, that you don't have to do that from scratch. That's all there in open source. And we're doing output generators into some of the common inferencing engines. There's the Google NN API, which is the Android neural net API, and OpenVX, which is in Khronos land, That's the inferencing engine. And let me talk a little bit about OpenVX. Again, this is something that we're not covering elsewhere, so I'll slow down just a little bit. The OpenVX vision acceleration, Vulkan has it easy because it knows it's running on a GPU. Open vision acceleration can happen on dozens of different types of architectures, anything, again, from GPUs to DSPs, FPGAs. And so how can you create an API that provides software portability across such a diverse range of hardware? The answer, of course, is you have to click up one level of abstraction, and a cool abstraction level is a graph. So OpenVX started life as a pure vision API. This was before machine learning really burst onto the scene in its latest iteration. And so the idea in the vision operations in OpenVX, it's like Lego. You have a menu of nodes, you connect them together in a graph, and then it's up to the hardware implementer to take that graph and to map it onto their hardware, however they wish. And because you have the complete graph defined before a single execution cycle starts, you have all the information you need for holistic global optimizations to happen before anything starts executing. So OpenVX has been evolving for several years. OpenVX 1.0 started, shipped in 1.0. We have a number of implementations. Now we're up to OpenVX 1.2. We have lots more flexibility, conditional node execution, so much more flexibility in the graph, more operators. And we're working on, and actually shipped a neural network acceleration extension. I'll go into that in just a second. We also have a safety critical version of OpenVX. So you take out all of the parts that you don't need at runtime, like the graph compiler, and you say that's not part of the safety critical spec, much less code to certify and get conformance tested. And looking forward into the roadmap for OpenVX, NNEF import is key, and programmable user kernels. So let me just quickly talk about those two. So OpenVX is already a pretty good match to neural networks because actually, a CNN is, after all, just a pretty large, complex graph. And so the neural net extension to OpenVX, which is shipping, simply defines tensor operations. And so you can quite easily define a neural network topology using the OpenVX graph building tools. And that's kind of shipping today. But of course, describing a multi-layer CNN can get pretty tedious, and actually, of course, that topology is going to come from your training networks. So hey, wouldn't it be cool if you actually had some kind of exchange format that we could just import into OpenVX to create the neural net part of the OpenVX graph? And of course, that's NNEF. So we are working on, now that the NNEF 1.0 spec is finalized, we're close to finalizing the NNEF import into OpenVX. So you'll be able to import a neural network and have it operate in the same graph with traditional vision operators too. So you often want to do some pre-processing on the camera and sensor input before you start doing your inferencing, for example. The other thing that people have been asking for a long time is, you have quite a nice menu of OpenVX nodes that you can put together in your graph, but of course I want something special. And wouldn't it be nice if we could let people write a custom node and still have it accelerated? If only we had a parallel programming framework. Oh wait, we do. It's called OpenCL. And so we now have the extension so we can have an OpenVX node sending commands directly into an OpenCL command queue, and the VX and the OpenCL can share memory with the kind of synchronization that you'd expect for a proper operation. This is being developed very, very close to shipping this. So if you have OpenCL and OpenVX on a platform, you'll be able to run both APIs within the same graph description, and you can code your own custom nodes. So talking about OpenCL, how are we doing on OpenCL, the roadmap? Last year, OpenCL shipped OpenCL 2.2. Now, it's kind of a pretty big milestone for the group because we brought C++ kernel language into core. It's pretty much all of the functionality that everyone's ever asked for pretty much is there. Lack of functionality is not the issue anymore. So where do we go from here? We actually have a three-threaded roadmap ahead of us. We have SYCL, which is a C++ framework built on top of OpenCL for people to do single source C++ programming. That's actually shipping today. But SYCL, along with other players in the industry, share the common vision. It would be really nice if ISO standard C++, some future version, was to have enough expressive power that we can do awesome parallel programming using standard C++. And SYCL, along with other folks, are contributing lots of ideas. For example, Khronos is hosting the C++ 17 parallel STL. We've been making proposals to C++ 20, and that's a worthy goal. It's going to be a long-term effort, but it's something that's, I think, really important to the industry, and the SYCL group are really engaged with that. We want to, last year we were talking about merging OpenCL and Vulkan. Did we need to do that or not? In the end, we decided we didn't want to do that because Vulkan is for GPUs, OpenCL is for GPUs and everything else. But we wanted to make the two standards work better together, and we wanted to provide more deployment flexibility for developers that have invested in OpenCL code. How can we get them to run on more places? Just like Vulkan portability, it's all about deployment flexibility. That's really becoming the main theme for 2018. So I'll explain how we're doing that. And last but not least, we're also going for deployment flexibility for the core OpenCL spec. Let me just spend a minute on each of those. So SYCL, if you haven't come across it before, this is the thing in the Khronos ecosystem that's actually most similar to CUDA. It lets you do a single source, it's C++. You're using standard C++. There's no extensions or directives. It's cunning use of template libraries and Lambda functions. Lets the compiler figure out where the acceleratable code is. And the acceleratable code will go into the SYCL compiler, which just outputs standard OpenCL that gets compiled down to your hardware. The rest of the code gets compiled on your CPU compiler. And we're finding that the state of the art in this compiler chain is now to the point where for complex libraries and apps, if you use kernel fusion in the latest compilers, you can get better performance than hand-coded OpenCL. And lots of libraries out there are written in C++, obviously, you can just compile them. You don't have to spend a lot of time rewriting them. So it's a pretty powerful tool. Bringing OpenCL to Vulkan. So we have an excellent example here of why we need deployment flexibility. Now, Adobe are going to be talking later this afternoon about this in more detail in the Vulkan BOF. But the highlight is turns out that Adobe have 200,000 lines of code of OpenCL for Adobe Photoshop. And they want to run it working with Google, having it accelerated by the GPU on Android devices. Now, Android doesn't support OpenCL as part of the native platform. Some phone vendors ship it, but it's not a standard part of the platform. So wouldn't it be cool if we could, but of course Android does have Vulkan. So wouldn't it be cool if we could just compile all of those OpenCL C++, OpenCL C kernels and have them run on the Vulkan runtime? And it turns out that's actually entirely feasible. We have an open source compiler called CLSPV, which is up there on GitHub. Google and CodePlay and Adobe have put a lot of work into this. And now the entire Photoshop 200,000 lines is running successfully through that compiler. It generates the Vulkan flavor of SPIR-V, and it runs perfectly on the Vulkan runtime. So this is awesome. It means that people can continue to invest in OpenCL and soon C++. There's more expressive power than the shading languages, but they get the choice. They can deploy on an OpenCL runtime, or they can deploy on a Vulkan runtime. We haven't yet translated the API calls. The API code is typically much more trivial compared to the kernels, but we could do, and if there's demand, we would certainly consider doing that, again, like we have done for the Vulkan portability initiative. In fact, what we want now is to have more compiler loads being fed through SPIR-V. So we've opened up, just like yesterday, we've opened up a repository that if people wish to have their kind of code being handled by SPIR-V, we encourage folks to put up their sample kernels. We'll try mapping it on through the compiler onto Vulkan. We'll either update the open source, or if it's a really interesting case that we find that the Vulkan runtime doesn't quite cope efficiently with yet, that will be input into the Vulkan working group to consider continuing to expand the Vulkan compute capability. And Vulkan's already doing a lot of that. We have the reduced precision storage. We'll soon have operators, the variable pointers, subgroups are here. So that's an ongoing process, and we think this will help and accelerate Vulkan become an even better compute API. And of course, I mentioned at the beginning that SPIR is the hidden hero in all of this. It's easy to do a Khronos presentation and forget to put the SPIR slide in because it's kind of behind the scenes. But in many ways, SPIR is, I think, it's one of the most important standards that Khronos does. It's the intermediate representation that has native support for parallel computation and 3D graphics. It's a spec. I mean, there's lots of open source compilers, but SPIR is a spec, so it's stable enough for the hardware community to use with confidence. There's an increasing number of open source tools that are enabling all the kinds of cool stuff you just seen. For example, the Vulkan portability, totally reliant on SPIR-V cross, which is a cross translator between SPIR-V and metal shading language HLSL and GLSL. So if you take a Vulkan program, the Molten VK is taking all your SPIR-V, throwing it out to SPIR-V cross, and it gets metal shading language back, which it puts down into the Apple compiler, for example. So lots of open source activity. If you're interested in compilers, I encourage you to take a look. And of course, it's always worth mentioning, we love LLVM. We're not trying to compete, we're trying to coexist in a really positive way with LLVM. Lots of people's tool chains go back and forth between SPIR-V and LLVM. Lots of awesome technology and toolkits in LLVM ecosystem. In fact, the OpenGL working group now has a subgroup which is dedicated to figuring out how can we work better with LLVM and upstream stuff into LLVM over time. I think the last slide here is OpenGL Next. That's the third thread on the OpenGL roadmap. So the lack of functionality is not our problem. It's getting it deployed flexibly onto lots of different hardware. And there's some things we can really do. Lots of the demand for OpenGL is coming from vision and inferencing. Lots of the hardware is lower precision DSPs or FPGAs. And yet we're in a weird situation today. To be conformant to OpenGL, you need to have 32-bit floating point. And that kind of is a legacy from the fact that OpenGL was originally developed for the cloud and the desktop. So we've a little belatedly realized this disconnect. And so we've stolen an idea from Vulkan, feature sets, where we define a number of features that can be made optional. And we can define all the machinery for an application to query and understand what optional parts are there or not there in a particular implementation. That could lead to horrible fragmentation. So feature sets are a way of grouping those features together into market-oriented feature sets. So for example, I think we'll probably end up with something like a DSP machine and vision inferencing feature set. So there's nothing in there that those guys don't want to ship in their hardware. It'll fit like a glove, and they will able to be fully conformant and use all of the power of the OpenGL parallel programming framework. Okay, I lied. This is my last slide. So the last thing we're actually announcing here at SIGGRAPH, because there are lots of educators around, is the Khronos Education Forum. So at every show, we get educators coming to us saying, you've just released another Vulkan 800-page complex specification, now you want me to teach it? Help. And then we actually also get some awesome educators come up and say, I've just done a Vulkan course. I'd like to share it and get some feedback and work on this together. And so we're going to set up a simple repository and hub to connect educators that want to work on course materials for Khronos APIs. It's free to everyone. You don't need to be a member or anything. We'll set up an open educational resource hub. The working groups will be able to provide some feedback and guidance to the materials, but they're not going to gatekeep, but they can hopefully get involved and help with the process. If you are an educator, we'd love to speak to you about that, or buy us a beer later, or send an email to education@khronos.org. Okay, that's it. Thank you very much. We have a couple minutes for questions, if there are any questions. I think there's a mic there. Stunned everyone into silence. So next up, GLTF, do you want to come on up? So again, if you want more details on any of that, come to the relevant BOF throughout the day, and you'll actually get to hear from people that know what they're talking about. All right, okay, thanks very much, everyone. We'll go on to the GLTF.
Close your Welcome to the GLTF BOF. It is 10 a.m. and we have a packed house here to talk about a very exciting topic on 3D formats. My name is Patrick Cozy. I'm from the Cesium team and I chair the 3D formats group with Khronos, where we focus on GLTF, the open standard 3D transmission format for scenes and models. And we have an incredible set of dedicated speakers today. They were here 7:30 this morning testing the projector and the mic. Great folks from a variety of industries. I'm only going to do a 2-minute intro before I hand it over to the folks who are doing the bulk of the work. So we've had great momentum in the GLTF ecosystem over the past year, from every part of the pipeline to rendering engines on the web, to on the desktop, using different graphics engines, also in VR. Also on the tool chain side, we're seeing a lot of work there being done in the open source. In the world of Blender, we have a pretty popular open source Blender exporter, and now efforts to unify that with an importer as well. We're also doing open source work on the Collada to GLTF open source converter to convert that to be up to GLTF 2.0. So really great progress across the board here. Some of the overall highlights that we see is, Microsoft's adoption of GLTF, I think, has been great for the community, and they've done so much open source work. And their GLTF library that they've been using in Windows 10, they just released as open source. We see model repositories such as TurboSquid and Sketchfab adopting GLTF, making tons of content available in GLTF. We see Facebook adopting GLTF, really easy drag and drop, bring your 3D content to the web in an efficient format, and these folks will be speaking more on this today. Adobe using GLTF and also contributing a lot of extensions in the world of materials. Mozilla doing VR work. Even in other fields, the Open Geospatial Consortium, they have community standards now that are referencing GLTF. Then Google, we've ratified the Draco mesh compression today, and we'll hear more from Jameson on using that for keyframes. Big efforts on the roadmap now are for unified texture compression, working with AMD, Basis, and we'll hear from Mark Holloway on that. And then we're just being careful in terms of adding extensions to GLTF so that we add functionality, but we don't want to make it too complicated, as the ease of use is very important for our runtime use case and have real lot of interoperability. And then the working group is really trying to guide the direction of GLTF, but we're doing so in collaboration with the community as always. So we love folks chiming in on our GitHub. If you just Google GLTF space GitHub, we're very active and the community has a large say in the direction. So without further ado, I want to bring up Patrick Ryan from Microsoft, who's going to talk about GLTF from the artist perspective. Patrick?
Good morning. My name is Patrick Ryan, and I'm a technical artist with Microsoft supporting our GLTF contributions. One of my main areas of focus is how we can expand the art pipeline for creators and help their adoption of the format. To that end, I wanted to walk you through a process for creating a couple of sample assets to help you understand what types of decisions need to be made when creating for this format. We will look at the flight helmet and the Yeti, two assets that present their own unique challenges while validating different needs for assets in GLTF. Starting with the flight helmet, we wanted an asset that would help to validate our Babylon.js renderer tech, but hoped that it could be something that could help all GLTF renderers. It needed to contain cloth, leather, metal, plastic, rubber, and wood in a single object to allow us to quickly see how changes in our rendering affect their accuracy. With those guidelines agreed upon, we set some technical goals as well. We wanted an asset that was heavy so we could test our loading speed across different devices. And we also wanted an asset that could withstand close inspection, utilizing high quality textures and a strong silhouette in the geometry. From there, a portion of the pipeline was defined by the needs of the individual assets. The flight helmet has elements with very complex shapes, like the oxygen hose, straps, and wires. The geometry creates a repeating silhouette, but is also deformed by a spline. ZBrush is particularly strong in creating this type of geometry, so it was chosen to model this asset in low poly. From there, the mesh was subdivided to sculpt the high-frequency detail that we captured in the normal map. After the low and high poly meshes were finished in ZBrush, the asset was transferred to Maya to set up the UVs. This is where the first decisions for GLTF come into the pipeline. The single mesh can only have one material with a defined blend mode, per the GLTF spec. This means that we need to distribute the UV islands across materials to maximize textile density for important parts of the model while limiting the number of materials and total meshes for optimization purposes. With the UVs defined for the mesh, both the low and high poly meshes are sent to Substance Painter for texturing. The normal map is baked from the difference between the two meshes, and that is used to create the rest of the maps used in procedural texturing, such as curvature, world space normal, position, and ambient occlusion. We can then use smart materials available in Painter as a basis for our textures, or create them entirely from scratch using procedural methods. We can weather each material to make it believable as an object that has a history, which reinforces the qualities of physically based rendering. Next step for this model, which didn't need animation, was to export to GLTF. We went straight from Substance Painter with their GLTF built-in exporter. The export process is as simple as choosing the correct export preset as the finished asset is already assembled in Painter. The other model that we recently published was the Yeti, which was created to help us test our animation export path from Maya, as well as show us what we could do with stylized texturing while still using PBR materials. The same general pipeline was used with an addition at the end. ZBrush was used for the character design. Maya was used to create the UVs for the model. And Substance Painter was used to hand paint the textures. And then we would go back to Maya for animation. The materials from Painter were exported as a base color texture, a normal texture, and an occlusion rough metal packed texture. These were used to assemble the model in Maya using Arnold materials before it was rigged and animated. The Babylon.js exporter was used to export the GLTF file with skinning information and animation clips. In general, most existing art pipelines can easily be modified to enable GLTF files as an output. It's largely the same as it has been, with a few points where decisions are made based on the GLTF requirements or needed features in an asset. Nothing about creating a GLTF asset is new territory for any artist who is currently making assets for other engines, and all requirements for the spec can be found online. These are the DCC tools that I regularly use to export the GLTF. Substance Painter is the only package with a first-party exporter, but Babylon.js offers exporters for Autodesk products. And if anyone here is working on an exporter for a DCC package, I'd love to speak with you about it. Thank you for letting me walk you through my process, and I hope this sheds some light on creating for GLTF. Do you want to go into, yeah, okay.
Good morning. My name's Bo Pershall. I am the Vice President of Business Development for TurboSquid. For those of you who don't know, we are the world's largest marketplace for online content for professionals for 3D. A little bit of our background. I won't spend too much time. We're founded in 2000. We've got about 75 employees based out of New Orleans, 60,000 plus artists around the world who've produced about 700,000 pieces of content, millions of customers worldwide who've purchased that content for their own productions. What's interesting is that in 2011 here in Vancouver, we launched the first modeling certification system called Checkmate. That basically we built a set of best practices with customers and clients to basically figure out what would flow into multiple different types of workflows. We boiled all of this down into a spec that's publicly available. We have staff internally that actually checks that content. And we work with artists if there are problems to improve their quality so that people have a good experience with content. So it was interesting when the Khronos group actually asked us to speak about why GLTF mattered to us. Well, with Checkmate, we wanted to make sure that people had a good experience. Same thing goes for GLTF as well. Khronos group has worked very hard to make the standard readily ingestible. They're actually using PBR material standards, which is very important. I'll talk about that in a minute. It's not a black box. It's easily certifiable. We can actually check our content and things like Babylon.js, make sure that the content works. Plus, it doesn't hurt when you have massive industry support. Companies like Microsoft, when they say 3D for everyone, yay, it's about time. We're glad to see that finally happening. Plus, there's a kind of a unique experience within our own industry. We have a lot of customers that come to us saying, hey, look, we're building our own experiences. We want to use GLTF as kind of our standard. So we're seeing things now where a lot of different companies want to use GLTF as the basis for whatever they're building for the web. So we had to kind of stand up and take notice. Of course, what's interesting is that how do you teach 60,000 artists to build to GLTF? Well, they're often slow to change their workflows. And I don't say that to be snide, just they like to work the way they work. They're used to working in Max and V-Ray. They want to continue working there. But we realized that customer experience for GLTF applications goes much further than professional standards. You're now talking about consumers. So they're going to have minimal 3D knowledge. They're basically not going to know a point normal from a UV. And we have to make sure that the content just works. So teaching an artist or an artist community how to deliver that content quickly, given how fast GLTF is actually being adopted, is difficult. So what we did is we spent the last couple of years building a process called Stem Cell. It allows the artist to build their content once in their native application of choice, professional artist building. Uses a series of calibrated PBR material workflows, which is why GLTF 2.0 is so valuable to us. On the back end, once they submit, basically we can take that content and convert it automatically into all the other formats, including GLTF, that allows us to hand off that content to any experience maker who needs that kind of content. Plus, the artist actually gets to review their content before it goes live. So you have Max V-Ray, these are renders, Maya V-Ray, or Max Mental Ray, Maya V-Ray, Maya Mental Ray, Cinema 4D Physical, Unity, Unreal, and then I actually have a little GLTF at the very end. So you can get very predictable results out of something like Stem Cell, specifically for GLTF usage in that community. And then we're really excited about the way GLTF is coming, because we'll be talking with the Khronos group about things like smart content and some more custom 3D stuff that's coming in the future. If you guys are interested in learning about Stem Cell, it's publicly available through turbosquid.com. If you want to follow us on social media, turbosquid @BoPershall. You can actually find us that way. Let me see if I can't switch. I don't think the viewer's there, so I'm not going to worry about it. Don't want to break this for anybody else. That's it. If you guys have questions, let me know. Thank you very much. You want to?
Actual papers. Let's see what we're doing here. Sorry. There we go. All right, so good morning. My name is Pervin Sel, and I'm here to give a very rapid overview of a backend system that we've been working on to take an uploaded GLTF model from a user and optimize it on demand for a specific request and client. This is all from the perspective of really highly technical engineering. It's not so much about products. Yes, that's me. Early this year, we made it possible to drag a GLB into the composer and post it, showing off to your friends. And unsurprisingly, the newsfeed is a fairly demanding application. It needs to be very low latency. Things need to move very rapidly. So we put a restrictive upload cap of 3 megabytes on uploads. That's a pretty small GLTF model. Furthermore, we were very strict about validation, like even a surplus comma in the wrong place would cause your model to be rejected. So while this was a popular product, many people like it, these two things are undeniably somewhat frustrating because it is not obvious to a casual creator how they would go about optimizing a model for size, or even a non-casual creator sometimes. And validation perhaps even more so, like how do you repair a GLTF file? Like you look for a tool that helps you or whatnot. In any case, we figured we could help. So we wanted to flip this paradigm on its head and sort of work the way images and videos already work, like in a transcoding fashion where we encourage the upload of high fidelity source material, and then we take it upon ourselves to say we will attempt to respect the intent behind this content the best we can, and sort of graciously interpret it and deliver it in a form that makes the most sense for whatever device the client is actually, the user is actually accessing on. Like an older Android phone might request an ETC1 compressed textures and a relatively low vertex count for speed, whereas a Rift-equipped PC user might have no problem rendering the model at full fidelity, but still would appreciate a zippy download. So to actually be able to do this subjective customization of models, the first thing we have to do is really tear the GLB to shreds, like decompose it down to atomic elements, so we can work on it as logical data. And while doing so, we can also repair harmless errors and be more accepting and less frustrating. So once we have it in memory and it's just an internal state, we're in this blessed state where we can perform powerful manipulation on the model. We could coalesce compatible meshes to reduce draw call counts. We can collapse part of the scene graph. We could take RGBA vertex colors and turn them into RGB vertex colors and save 1 byte per vertex if it turns out the material doesn't care about opacity, for example, or the alpha is all 1. We could compress the meshes using Draco, obsoleting the previous optimization. If we know the client has a decoder, that makes things move much. And thank you, by the way, for Draco. It's a wonderful product. Very briefly, I want to say thank you to this entire community, which is one of the most wonderful communities of developers I've ever worked with. So many people work so hard and are incredibly friendly and gracious. If any of you have any interest in joining, just jump into GitHub and you will be received with joyous exclamations. If the model needs really dramatic size reduction, for example, say we want to present an inventory, this is looking ahead a little bit of 16 by 16 models, we need to do something much more severe, and then we can run it through a mesh decimation system, for example. Yes, 1 minute, yes, okay. So the final transformation is to just reverse the shredding maneuver we started with, rebuild the GLB because we use GLB internally between backend and client as well, and we ship it off to the client that made the request. And for all this to scale, we save the generated asset associated with the client categorization, so the subsequent request from the same type of client doesn't have to be re-optimized. This is the only way that this could possibly scale. We can't do this for every request. Okay, looking ahead very, very briefly. Yes. Imagine a busy virtual world. Suddenly, the requirements are much, much greater. Right? Level of detail is no longer optional. MIP maps need to work perfectly. Streaming becomes quite relevant, although when to use it and when not to use it is an aesthetic and complicated question. This is something we're very excited about. We're playing with it, and there are no product implications here, but I'm having a lot of fun playing with it. Thank you very much.
Hi, everyone. My name is Gary, and this is Cedric. And at Microsoft, I work on GLTF and Babylon.js, and Cedric works on the mixed reality viewer. We're here today to give you an update of what's happening with Microsoft, with GLTF at Microsoft. So here are some of the products that already have 3D capabilities. We're using GLTF as the foundation for all of these products that use 3D. A runtime-friendly transmission format like GLTF enables us to make 3D objects as easy to use as images. So for example, interactions with a 3D object, like copy and paste from one application to another, or previewing 3D objects in Windows Explorer, or even double-clicking on one and seeing what it looks like in a mixed reality viewer. Also, I didn't have to ask the users 20 questions in order to properly render it. Everything just works. We're also continuing to use GLTF in new products with 3D. So this is Microsoft Layout. It's a business application for HoloLens that helps people design spaces in context with mixed reality. We are contributing to an open source project, Unity GLTF, which this application uses to save and load GLTF assets. We also announced SharePoint Spaces, an immersive mixed reality experience which enables you to view and interact with content. This experience is built with Babylon.js using standards such as WebVR and, of course, GLTF for 3D assets. And finally, Office for the Mac also supports 3D now, similar to PC versions. It is currently available with the Office Insiders program and will soon come to the public. If you want to find out more about that, please go to the link shown here. So that's it for me. Cedric is now going to show you some new features in some of our existing products using a couple of new extensions for GLTF. Take it away.
Thanks, Gary. So let's dive into mixed reality. So when using a Microsoft mixed reality headset, you basically brought into the mixed reality home. So this is like a desktop for your 3D world. So you can use your favorite apps for browsing the web, or even checking on your social media posts about GLTF. You can also customize the space with 3D objects like those GLTF sample models or the helmet that you saw earlier. This is the Yeti that Patrick Ryan talked about earlier. It's using the animation map extension, basically that we've been working with Facebook on. And so the extension allows you to define like semantics to play animation, so such as gaze. So when looking at the model, you can play a specific animation. And of course, you can take the experience to the next level with audio. So we just released an audio extension for GLTF on GitHub. And this, combined with the animation map extension, this is how we brought the T-Rex to life basically today. The same experience will be soon available in the mixed reality viewer as well. So you can double click on GLBs and basically get more scary dinosaurs. You can also basically look at this model in Babylon.js sandbox. And then, so we have a full open source implementation of the extension in Babylon.js. So if you want to contribute or look at it, just check it out. This is all the links about the things we talked just earlier, and special shout out to the Vancouver team right there that just open source effectively the GLTF SDK just in time for SIGGRAPH. So the GLTF SDK is a cross-platform C++ GLTF serializer, deserializer, well, that's full mouth, that we use across all our products, including the various Windows and Office applications. So as you can see, we do support GLTF in most of our 3D products, and we committed to basically continue this like for the rest of the ecosystem. Thank you.
All right, hi, my name is Ed Mackey. I work with the Cesium team and the SDK team. I'm here with Alex Wood from the SDK 3D graphics team. Do we have, Do we have a video up? There we go, thank you. Yeah, SDK or Systems Toolkit is a desktop analysis product. It has OpenGL visualization. And this year we added GLTF 2.0 support, and we want to share some lessons learned from that. So here's a model. We do more than just show pretty pictures with models. We actually do a little bit of analysis on them. And so, for example, this vehicle needs its solar panels pointed at the sun all the time as it moves. Now, with a typical GLTF model, an animator would have to come in and say, this piece moves, and then they would have to specify where and when it moves. We need models that can show which piece is allowed to move, but not where exactly it's pointing, and we created a vendor extension to help us out with that. We do more than just analysis, though. We did upgrade the visualization there a little bit. So this is a procedural reflection environment. I actually wrote this for Cesium last year, and we've ported it to SDK. But the new trick is that it's hooked up to the day-night cycle. So when the model goes into nighttime, the stars actually come out in the reflections on it, as well as in the sky. And because this is SDK, it's aware of the model's location on the Earth and the time of day, so it will actually orient the star map correctly. With that, I'm going to turn it over to Alex.
All right, thanks, Ed. So what we love about GLTF is, we've heard this in all the previous talks too, is the community is great, and it's really brought PBR to the mainstream to, layman developers like myself, where, like best practices are shared across the ecosystem. And so what we want to do is spend a little bit of time to share some, we recently added all of this GLTF support to our engine, and we wanted to share some lessons learned that really elevated the visual quality of our product. So here we're looking at, we'll start with high dynamic range. So here we're looking at, on the left, we have an LDR reflection map, 8 bits per channel, which means that your whites are clamped at 1.0. So once you start blending in darker base color factors or AO, those get shifted down to grays, and so you're kind of left with like a uniformly dimmer reflection environment. And on the right, what happens when you're using HDR, you're given a lot more, your colors go well above 1.0. And so what happens when you start blending in those darker materials is that you're actually accessing more detail via the levels of exposure in that HDR image. And so that really greatly enhanced our visual quality there. But when you're doing HDR, at some point you do need to back down into LDR in order to do the final presentation of the model. So to do that, simple gamma correction is just not enough. You need to actually do tone mapping, which is the process of mapping your high dynamic colors into that LDR space, or into the LDR space. On the left there, you see there's like a real hot spot. There's oversaturation, some hard edges, and with tone mapping, that all kind of gets averaged out. What you do is you define, there's a function, a color correction curve, which maps those colors for you. We tried several different curves, and even pulled it in, plotted it out, and tried to find one that we liked the most. But we also ended up finding the ACES fitted actually provided the results that we thought really showcased these models best in our engine. So we wanted to kind of bring some attention to this, these sorts of things, because there's a lot of rendering engines out there, adoption's massive, and it's important that we have consistency of our models across the ecosystem. And so we just kind of wanted to share some of those and hopefully continue some discussion on those. So we just scratched the surface, so please find us after the BOF or at the reception tonight. We'd be happy to talk more about these. And I'll turn it back to Ed for the next.
Okay, thanks, Alex. I'm going to jump right into the next presentation, which is on VS Code. I will have a VS Code window here, which is not maximized. So VS Code is a text editor. It's from Microsoft. It's free. It's open source. It's not to be confused with Visual Studio. It's similar in spirit, but it's a whole different framework. It's actually based on Electron, and it has JavaScript, and that means it has WebGL, and that means you can visualize your 3D models right in the preview window if you install the GLTF extension. But I showed you that last year. Let me show you what's new this year. One of the things that's new this year is we have a little outline. Normally it's, I've already got it popped open. Normally it's way down at the bottom, and you have to click where it says GLTF outline. And it will actually break down your model by size, and it'll show you that this mesh is taking half a meg, and this texture is taking up some space. It's albedo texture, and the normal texture is taking up some space. And it allows you to quickly navigate to different areas of the model. Another navigation feature, and some of this I didn't even write myself. Actually, Jamie is in the audience there. He contributed most of these features that I'm demoing and taking all the credit for today. But one of the features is there's a go-to definition, which is F12. It's all hooked up, so all these little numbers that reference different accessors or different materials, you can follow the go-to definition and jump to different places in the document where things are defined. And we also have a peak definition, which will pop it open in the middle of your document like that. Now, one thing I want to point out about peak, I just did peak definition on an accessor, and it's showing me all of the decoded mesh data as human readable ASCII numbers here. That data is all stored in binary in the gltf.bin file, and the VS Code extension actually looked at the byte stride and the offset and all that. It decoded all that and just dumped it out into a temporary memory document just to make it all visible. 1 minute left, thank you. And the other thing I want to foot stomp is that we actually have the official Khronos GLTF validator built right into this thing. So if I decide that I don't like these min-max numbers, maybe I like the number 10 to be better as my maximum value, or my maximum value here. But VS Code seems to be having some trouble with that. It squiggled it red. Let me just, I don't know how well you guys can actually read this. But it's complaining from the official validator. It knows the actual maximum value that's supposed to be there, and it will pop it up as a little, document problems window. Hey, you messed up this value. What I want to mention here is that the validator is not just looking at your JSON metadata. It's actually reaching into the images. It's reaching into the binary. It's looking at all the parts of the model and make sure it all follows the rules of GLTF, and will call out any problems it finds like that. I think that's all the time I have for today, but thank you.
Is this just somewhere? So there it is. Okay. So my name is Johannes Beer. I'm here with the rest of the team, and I show some extension to the Instance 3D Hub system we presented before in regards to industrial augmented reality application and how we use GLTF to tackle those different areas. And this is really looking at industrial augmented reality. So we have already seen some consumer augmented reality, which works pretty well, but this is really targeting. So if we look at the market, there are different prediction when this going to happen. So when people use this in this large-scale environments, and Gartner predicts it's going to take another 5 years. And what we try to do with the system infrastructure is that we accelerate this process, that we can follow the hardware pattern so that they move from specific hardware to consumer hardware, and that they have software platforms that are easy to use and can scale and can be connected to the really large data sets. Because right now they're still building prototypes using game engines and manual processes to convert the data. And that's something we try to change. And there we start where the industry is right now. They use 3D data already for 30 years. So they have CAD data, simulator data, and use this quite intense, and it works quite well. But what we realized over the last 5, 6, 7 years, the rate of change, the complexity, but especially the requirements that we have from virtual augmented reality, the performance increase and quality is something that is really too challenging for the industry, so they fall back to some simple states. Oh. So it was too much, sorry. Okay, so what we do, we observe the data in the original state on changes and translate the semantic cat data to some acceleration structure, and there GLTF plays a key role, and we patch and sort the data, and then the small pieces that are specially sorted can be transmitted really efficiently, so they're using the compact representation of GLTF, the direct mapping to GPU structures, and this allows us to deal really with massive data sets on really, really small devices. And this is also used not just for visualization, but for model-based tracking, so we use the server-side rendering system to render hypotheses on the original data. So the original cat data is untouched, used to render these edges of the cat data, and this is then matched with the edges that are in the original data stream. And then this can be overlaid with the cat data to get real application directly in your web browser, so you don't need any additional plugin or anything. So this is really helpful and is a big advantage compared to the state of the art. So if you look at what technology people use in consumer augmented reality application, so with the toolkits that are available right now, people all use LAMs, which is super technology, works really great, especially with the sensor fusion approaches, but the feature are not correlated to objects, so we cannot say, okay, what object is related to what part of the feature cloud. The other one is really using machine learning, but that's really costly, and we cannot deal with dynamic configuration, so if we have to derive situations dynamically, this doesn't work. So that's the reason why we use this model-based tracking, which allows us to directly match the cat data if we know the configuration of the cat data. So we use machine learning or other to initialize the system, but then we use the cat data directly to map this. And 1 minute, excellent. This is used by with different versions, so this is something that people use in reality right now, and Porsche is one of our customers, a couple of other customers, and they use the system to derive the digital twin directly from the vehicle identification number, so they work for it in, derive the data, then, and the next step is what we're working on right now is that they use exactly the same workflow to dynamically derive the service configuration. And at CeBIT, we had a full car from Porsche. Here we have a wheel back there, the colleagues with a wheel and the demo, which can be shown later on. So if somebody is interested in the live demo, you should come by or get more information on the website where Instance Really Hub, and then I have a couple of other demos and videos and showing how this works. So that's from my side so far.
Sweet. All right, I'm Jameson. I'm from the Draco team at Google. So we'll be talking about what we do for compression at GLTF. So if you haven't heard of it, Draco's our open source, royalty-free codec for 3D graphics, both meshes and point clouds. But for the sake of this discussion, we'll just cover meshes. Point clouds will hopefully come to GLTF later this year, let's hope. So just to give you kind of a reference on like how much smaller we can make models, this is kind of a simple car model. I think that's somewhat obvious that it's a car, but we can compress these things somewhere on the order of 10x on average, but depending on the model, you might see upwards of 20 to 30x compression. So that's just kind of a lossy compression that we add, makes this pretty small. You decode it in the client side and everything's great. We do a bit more than just straight up geometry compression. We can do a bit more complex scenes like this, where you might have stuff like connectivity data and colors and things like that. So something like this scene, which was captured on like a depth camera, is around 40 megs. With Draco compression, we can get it down to about 2.5 megs, and I think these might be old numbers. I think it's actually somewhere around 1.5 meg, which is great. So here we are. We're an official extension to GLTF. We have JavaScript, WebAssembly versions, C++ if you're going to try to build some native app. There's been some great ecosystem support from the pipeline tools to the viewers at Babylon, 3JS, and Cesium, so some really great support. So that's where we are today. Kind of want to talk about what's new. I love this robot, so I included them in our slides. But we want to add compression for animations. So we have out there today some code for handling keyframe animations as part of GLTF. Back at the office, we have our morph target support also available. We should be pushing that out sometime this week. And the results are really good. So far, we're seeing about, depending on how much mesh and how much animation that there is in a file, we can see somewhere on the order of about 6 to 10x compression on these files, which is pretty substantial and can be great. We released this just recently, so we're just looking for as much feedback as we can before we start going through the actual process of trying to get this spec ratified and trying to build out an official bit stream. Part of this actually includes a lot of the work that we've done on point clouds, so everything that we do to help push this along helps us also with getting point clouds out there. So one last thing, and this is somewhat of a maybe not that far future thing, but what we're looking at is maybe adding machine learning to Draco and seeing we have some experiments at the office where we've integrated kind of machine learning and TensorFlow into Draco, and we're seeing some decent results. I think there's a lot more areas for research in this. So what this is just finding the optimal compression level for a particular model so that you can dynamically generate it on a server and send it down. We're seeing okay. I think there's a lot more we can do with measuring the optimal quantization bits for a particular model and seeing this is the right one that will look perfect on your device. So if that's interesting to someone, please let me know and we might start looking at that more. So there we go. That's Draco.
My name is Mark Callow. While I get my presentation up, if you have a mobile device that can read QR codes and take you to a URL, get it ready. No, I don't need the. I need the slides on the computer. This is for my own notes. These are mine. Yeah, I need to go to the beginning of them. It's not at the beginning. No, it's not a touch screen. Okay. Sorry about that. Now, where's the clicker? Okay, so get your cameras ready. There's the URL for the presentation in Google Slides. The Google Slide version is not, it has some layout issues. We've tried to correct most of them, but the importer from PowerPoint has some issues. So I'm going to talk about compressed texture transmission format. The working group created this technical subgroup to look into this matter, and basically we've concluded we need to specify two things: a format for the image bits or the bit stream, and also a container, as textures normally consist of more than one image. A container is very helpful. I'm going to go through this slide in some detail because to show you what problems we're dealing with. With the image bits, we have a lot of issues. We could, of course, use the image formats defined by the GPU APIs, but the uncompressed formats are way too large for transmission, and the block compressed formats are suboptimal for transmission. For example, if you have an all-white texture, it's still going to send all of the blocks. And this is because the block compressed textures are designed for random access by the GPU for texturing. JPEG files can't be randomly accessed, so you're screwed there. And compression to GPU formats is unavailable on most clients, and if it was, it's very slow. So the idea of uncompressing the JPEG and recompressing it to the block compressed format is a non-starter. And finally, we have a Google of GPU-specific and platform-specific formats. So the whole thing is a bit of a nightmare. So what are we going to do about it? Well, we have a couple of solutions. First of all, solving the transmission size. We've got some super compression, by which I use super in the same way as it's used in superimpose. It's layered on top. It doesn't mean some kind of supercalifragilisticexpialidocious compression scheme. But we have a couple of super compression schemes. One is called rate distortion optimization. In RDO, both of these, I should say, are based on Crunch, which has been around for a few years. It was originally done for DXT textures, and it's recently been extended to support ETC as well. And in RDO mode, Crunch quantizes the raw BC1 to 5 or ETC bits using clusterization and vector quantization to lower their entropy, allowing LZ-style codecs to better exploit the redundancy in the texture data. The second one is Crunch's CRN mode. In CRN mode, sorry. In CRM mode, Crunch quantizes the endpoints and selector data of the BC or ETC1 data, again using clusterization and vector quantization. So it's basically applying its own super compression to the block compressed texture. So this gives us JPEG level compression for your block compressed texture data by applying these super compression techniques. Now for solving the Google of formats, we've come up with a universal transcodable format. This is based on ETC1. It's a subset we call ETC1S. It uses no flips and it disables individual modes. That is, each 4x4 block has a single 555 color and a 3-bit table index and 16 selectors. This is then Crunch is applied to this. And then at the other end, after decrunching, we can transcode it with a small piece of code into any of the formats shown on the slide, so you can load it into the GPU. The transcoders could be C++ or C, or it could be JavaScript, or even shader code. Now, I prepared this presentation for a much longer period of time, so I'm going to skip over a lot of slides. I won't go into the quality now, but and now this just shows the KTX. We're going to use KTX as the container, and this just shows it's basically an array of MIP levels, and the MIP levels, within each MIP level, you've got an array of array layers and faces or slices. What we've done for KTX2, we've added a couple of important things to the header of the KTX file. A super compression scheme, which lets you say which one of the LZ schemes you're using, or if you're using Crunch, and a level order, which allows you to change the bitmap level order in the file. If you send the smallest levels first, then it becomes good for streaming. We've added some metadata additions, but I don't have time to go into those now. And there's a data format descriptor to give complete information about the image, but again, I haven't time to go into that now. There are a few open issues in the spec. I welcome feedback to help me close those issues. The URL is here for both the place to file issues and the specification. The current status, the text, we expect to have a v1.0 provisional specification for the KTX text to transmission extension by the fourth quarter, which this will include the universal super compressed format I talked about. It will include the RDO mode. For now, it's only the lower precision formats, BC1 to 5, ETC1, PVRTC, ASTC, LDR subset. One of the things I didn't mention in the transcoding, we can support PVRTC. That was the most difficult one to do the transcoding for, but we have the code to do it, thanks to Rich Geldreich, who's the creator of Crunch. We're planning incremental spec revisions. We plan later to support another universal format for for precision encoding and high dynamic range. This will support variable block sizes and the high-end the BC and ASTC stuff. We're welcoming industry collaboration. We welcome everyone's feedback to help us get beyond the provisional stage. There's some comparisons here. I want to acknowledge these people, particularly Dave Wilkinson, who made all the images that I've just skipped over, and Rich Geldreich, who's provided all the technology. And there's all the URLs, and I guess we don't have time for questions at the moment, so I'll turn it over to someone else.
Do what everybody else is doing, looking a little bit stupid up here. Let's see, get this started. Okay, first slide. So, my name is Martin Ented. I work for a little company that you might know. Is it up there? No? Okay, it was the last slide. Yeah, it was the last slide. First slide. Then we go for the first slide. Okay, I work for a company called IKEA. Anyone here who doesn't know what IKEA is? Good. Take that later. This is the IKEA vision. The reason why I have it up here is because of the last two words, many people. We want to reach many people. And when we talk about many people, if you look at numbers, you look at the upper right, you have 2.3 billion people visiting our website every year, and we have like about 200,000 coworkers. And of course, we want to have planners, configurators, 3D things, internal and external stuff using 3D. And to be able to cater for that, for the thing we've done the last 12 years, we have been using computer graphics to create JPEGs and so on. And in the latest years, we have been doing things like the catalog AR app in 2012. We have done VR applications. We have been doing AR things with IKEA Place, if you've seen that one, both on Android and on iPhones. And we have been like building a library of very, very high-end 3D models during the years, and 37,000 3D models in super high resolution. We have down to 0.2 millimeter accuracy on textures and everything. So this is what we are then trying to push out to real time. And unfortunately today, we have to cater for many formats. And of course, that's a nightmare. And they are starting to become more and more of them. So this is what we are hoping for. So, and we hope that we can make GLTF that. And that's the reason why we joined Khronos group. That's the reason why we are in the working group. And this is also the reason why we're trying to be more and more active. So you have the desktop stuff, you have the phone stuff, and then the HMD stuff. And of course, probably different GLTF files with different compression, but still, this is what we are aiming for. And we are in the group now and trying to help out with
assets. We haven't been able to give out the much yet, but we hope to be able to do that. And we also are in there because we want to have more things in there that is not there now, like subsurface scattering and other effects, so we can show more of our products the whole way. Yeah, that was me. Thank you.
All right, so I am just blown away by the passion and the progress the GLTF community has made over the past year. I am also just amazed that we had 11 speakers stay on time, so thank you again for that. There's going to be a fantastic WebGL session in about 3 minutes in this room. So out of respect for them getting ready to set up the projector, I'll ask that all the GLTF speakers maybe congregate right where the t-shirts were, right out front. And a very friendly group, happy to take questions and speak with everyone. Thank you again for everyone coming and for the presenters. Good logistics, Patrick. Thank you. You're welcome. That worked out. You're welcome.
Members of the WebGL working group here that I haven't seen. Anybody who, oh, hi. It's HDMI. HDMI, yeah, okay. And there's a USB to Ethernet adapter. So who's there? Kirill, not sure if you want to come up and say hi. I just want to introduce the members of the WebGL working group that are here. I see some Angle folks in the back that should be up here. Who else? Anyone? Miles, do you want to represent Apple? Okay, so just to introduce folks that you can ask questions of directly about, like, why is WebGL slow in our browsers or something like that, please introduce yourselves.
Hi, I'm Kaini Nomiya. I work on WebGL and WebGPU in Chrome, and occasionally a little bit in Angle. So.
Hi, I'm Jamie. I work for Google on Angle, which is like an OpenGL portability library used in a lot of browsers.
And my name's Ken Russell. I work on WebGL at Google, and I'm the working group chair. So anything that's going wrong with your WebGL apps, please blame me. So could we bring up the computer on the screen, please? Okay, great, thank you. Let's see here. Okay, so I think we're ready to go. So do you guys want to maybe sit down for now and then come back up there? Thanks. All right, so we got a big show for you today, and it's going to be just a madhouse, so let's try to get through it. Let me point out that all of these slides are already up on the WebGL Wiki. So if you search for WebGL Wiki and you go to the Khronos website, go to presentations from recent conferences, these slides are already there. Now, I'm going to have to skip through my slides. I don't have time to present. So please don't worry, don't panic, don't try to take snapshots of everything that comes up on the screen. It's already on the web, so don't panic. All right, here we go. I'm going to give myself a hard time limit. All right, so welcome everybody. What have we been working on over the past year in the WebGL working group? Basically bug fixes, hundreds of bug fixes, and these are all in desire of making your apps more portable and more reliable. We hope that it's working. If it's not, we want you to please file more bugs so we can fix them and make sure that your apps actually run as expected. The Angle team, that is the portability layer under WebGL, has been doing a ton of work. Jamie, who was just up here, did some amazing performance optimizations over the past several months to get Angle to be like zero cost over going directly to the OpenGL driver and providing the WebGL semantics, the portability semantics. This has been fantastic work and is finding its way into other web browsers. And so we can see that WebGL 2 support is not quite where WebGL version 1 support is yet, but we hope to bridge that gap in the next several months. So, what are some major features that have been developed in WebGL 2? Kai, who was just up here, collaborated with Jeff Gilbert from Mozilla, did some tremendous work on making readbacks from the GPU asynchronous over the past several months. So finally, read pixels isn't slow. It's not going to block your app. Finally, you can do GPU computations, get the results back into your JavaScript code, and do some work there before re-uploading it, and in an efficient manner in all browsers. NVIDIA has done some tremendous work on multi-view. So this is a way that from your WebVR app, you basically get both views rendered for free, not at the cost of rendering your scene twice. We can do a quick little demo here. Let me see. So here is the WebGL Aquarium running in normal mode, and here it is running in VR mode. This is side by side. As it turns out, we found a problem with the graphics driver installation on this laptop, and it's not actually using the multi-view extension, so sorry about that, full disclosure. But basically, this means that your side-by-side renders are going to be free. So this increases the level of fidelity that you can make with your WebVR apps significantly. Here's another little demonstration of a, let me see here, oops. Oh. So I wanted to also show you some novel applications, novel domains in which WebGL is being used today. This is a demo built by I think the DeepMind team at Google, and they're showing the connectivity of neurons in the brain and are able to trace through a CAT-scanned data set with a neural net that fills in the connectivity of the neurons that they can see what's going on. Now, whether you subscribe to the philosophy that simply understanding how the brain is wired up means that you understand how the brain works is another philosophical question, and I'm over time. But anyway, lots of cool stuff out there. Now, another major contributor to the WebGL working group is Intel. They're doing some tremendous work, and so I'd like to invite up Yang Gu, who's the engineering manager at Intel. Please come. And he's going to tell you what they've been contributing to. All right, so let me delete this for you. Yeah, 5 minutes. So you're down there.
Oh, okay.
Ready? And so you can, ready?
Okay. So where's this one? Thanks again. My name is Yang Gu. I'm a software engineering manager from Intel Web team. Today I'd like to take this chance to introduce you our efforts on the web graphics. So before diving into the details of efforts from our team, I'd like to introduce a bit of our team. So we have been focused on web for more than 6 years, and we implemented WebGL 2 in Chrome from the very beginning together with Google. And currently our focus is on WebGL 2 compute, and we contributed a lot of patches into the Chromium and its related projects. So currently, we are now the Intel reps of Khronos WebGL working group and W3C Web GPU community group. Now let me introduce our efforts one by one. The first is about the WebGL 2 compute. This is to bring the OpenGL ES 3.1 features, where the most important feature is compute shader to the web. We have made it almost ready for both the OpenGL backend and the D3 backend for the compute shader. And currently, the TensorFlow.js can base on it and run smoothly. And as our plan, we will try to implement all the compute shader related features by the end of this year. Shader compilation has been a long headache for the WebGL developers. So we implemented some extensions. These extensions can make the shader compilation in the background and in parallel. We have some exciting data here. As the next step, we'll further parallelize the shader translation inside the Angle project so that your main thread will never be blocked again. We also try to do some optimization for 360 video, and we are optimizing the video uploads to the WebGL. The patch is still in progress, but we will try to finish it as soon as possible. We are also trying to bring the geometry shadow to the web, and currently we have finished the OpenGL backend for it, and we are working on the D3D backend. As to the web GPU, I think you know it, and it's definitely the future of web graphics. This is to bring the advanced native APIs such as Metal, D3D12, and Vulkan to the web. Our journey with this web GPU has begun. As to machine learning, this is a quite hot topic recently, right? Actually, there are two approaches here. One is based on our compute shader solution. The other is based on some OS vendor provided native APIs. Currently, we are working with these OS vendors and browser vendors to define these APIs. And we have a plan to create a W3C CG to move things forward. When we are doing web, we will often ask the question, how to compare the web performance with the native? Our answer to that is to port the Aquarium, the de facto WebGL benchmark, to the native. Currently, its OpenGL backend can work well with on the Windows, Mac OS, and Linux. And we also did some performance optimizations at the native side. Our plan is to port it to more backends, including both the WebGL and the native. We have been long acting as the quality gatekeeper on web graphics on Intel platforms. With our continuous support, Google helped to integrate Intel platforms into Chrome billboards, and our driver team also integrated the WebGL conformance test suite into the continuous integration system. We also have the monthly conformance and performance test, so we can further ensure the quality here. Finally, I want to call for your feedback. Your feedback, especially on the compute shadow, geometry shadow, ES 3.1 features, and machine learning, are especially precious and valuable for us. We want to prioritize our tasks and resources based on your feedback. Thank you.
Okay, so we're going to launch ahead. Mauricio from MergeLogix, please show us how you use WebGL to stack stores shelves.
Okay, so good morning. My name is Mauricio, and as Ken mentioned, there are novel domains out there, so this is hopefully one of them for most of you in the room. I'm going to teach you a little bit about retail space planning. So I work at a small company in Atlanta where we develop a fully online system called MergeLogix. Here you can see some of our customers. These and other retailers use MergeLogix to plan and execute projects that happen in their stores. So a typical retail project involves changing product assortments based on demand, product recalls, or seasonal promotions. They may also set up brand new shelving and assortments. Stores are constantly changing in order to stay competitive. So for example, this is what you might see near the front of a Home Depot store right now in August when they are running their Campus Ready promotion. Apparently, college students really like plastic storage bins. But very soon, the in-store labor teams will be replacing this with Halloween merchandise across almost 2,000 stores in the US. Here is a project dashboard in MergeLogix showing a bunch of projects in various states of planning and execution. To figure out where the work will be done in the store, you're going to need floor plans, which is the first component of retail space planning. To support this, we have a store map viewer and editor, which you see here. You can use this to modify the areas that are being updated by a project, and you can also set up new stores from scratch if you want. Since floor plans are traditionally two-dimensional, we use SVG for rendering and interaction in this case. Each of those rectangles, and there's quite a few of them there, represents a space where merchandise is placed, where you, the shopper, will go to buy things. So in the actual store, they might look like this. So these spaces with all the fixtures, the shelving, the products, all that stuff, they give us a third dimension to deal with, and that's height. These are designed and documented with special drawings called planograms. So notice the red circle here. In Home Depot stores, you can find these. That's a plastic sleeve which holds this. This is a printed planogram for the right side of that shelving unit of cleaning products. Typically, planograms are printed out on paper to be used by the in-store labor teams. One problem with this is that because the stores are constantly changing, these printouts are quickly out of date. So planograms like this are the second component of retail space planning. These are usually designed with heavy desktop software, but as I said at the beginning, we have a fully online system. So I'm going to show you what that looks like. Okay, so this is our online planogram viewer and editor built on WebGL and 3JS. This particular planogram shows an assortment of Lego sets that you might find in a toy department. On the left over here is a list of products. If there are any Lego fans in the room, you might recognize some of those that are used in the planogram. We also have the fixtures here, the shelves that are used in the planogram. If I select an item on the shelf, I can take a closer look at it. So this, I can see information about the placement of the product. This is actually called a position, so a list of products, and these are all positions for those products. So here I see the number of facings. This is how many of the product need to be placed in that location, across, up, and then back, sort of deep into the shelf. So that's 2 times 1 times 5. There are 10 instances or units of that product sitting there. I can also see details about the product itself, including a barcode and image for the product. Now, since we have product images for this planogram, I can click here and turn on product images, and so you can see those. If they have images for all 6 sides, we can show those here. So this one up here does have images for all 6 sides. Okay. Now I can move the fixtures, and the positions assigned to them will move together, so I can click on this and drag it around if I want. I can also move individual positions and work with them. So here I'm going to, let's say, take this one over here. I'm going to drag it over here. It moves the other ones aside. I'm going to shift this one over, maybe
delete this one, and then I'm going to increase the number of facings of this one now that I have more room for it. So those are the kinds of editing operations you can perform. Now, typically planograms are designed in 2D like that printed one you saw earlier, so you may be wondering why we even need 3D. So 3D is valuable for handling fixtures with unusual shapes and for spotting issues with the design. For example, on this particular planogram, if I flip over to the back, you'll see that the designer has specified too many facings for one of the products, and doing this in 3D makes it very easy to spot that. So all of this is also supported on mobile browsers. So here's the same WebGL-based editor running on an iPad, which required only minor additions to the code. By having this on a mobile device, in-store labor teams no longer need to use paper planograms. So they'll have the latest information, they'll be able to search it and update it to reflect the actual in-store status. So that's what we have today, but of course we'd like to do more. One thing we're looking into is using GLTF to support 3D models of products when the retailers have them. But as you can see, there's not a lot here from a graphics and WebGL perspective that's too exciting, especially compared to what you're about to see after me. So what makes this special? Well, this is less about what we can do with WebGL, but where we can do it. So for retail space planning, this is the status quo, right? Heavy desktop software, cumbersome installation, managing a bunch of local files, and so on. And they usually have limited 3D support. So with the capabilities I showed, we can now, just by clicking a link in a browser on both desktop and mobile, for retail space planning, that is a significant shift. And that simply would not be possible without WebGL. So I didn't really come here to show you a flashy demo, right? Although I do enjoy eye candy, I came here to say thanks. So thanks to Khronos for developing and promoting WebGL. Thanks to the browser vendors for embracing it. Thanks to the developers who are building WebGL toolkits like 3JS and sharing their knowledge. And thank you for listening to me today.
Fantastic stuff. Thank you, Mauricio. Yep. Thanks for opening our eyes to how it's used in other industries. So next up, Trevor Barron from Microsoft. He's going to show some cool eye candy with Babylon.js.
Sweet.
All right.
Cool.
There you go.
Thanks. So I'm going to talk a bit about Babylon.js. One sec. What happened to the slide? Did it just disappear?
What are you doing with
it just kind of disappeared.
Were you using?
How's it presented?
No, it was,
yeah, it's with PowerPoint.
It was right there. Where did it go? It was right there. It closed. Interesting. Okay.
Cool.
Yeah,
thanks.
You're on. Yeah.
Sweet. So I'm Trevor Barron. I'm a software developer on the Babylon.js team at Microsoft. I'm going to give a brief overview of Babylon.js. So Babylon.js is a 3D engine built on top of WebGL 1 and 2. We have full WebGL 2 support right now. It's built from the ground up with ease of use and performance in mind. Babylon's fully open source. All the code's available on GitHub, so you can go check it out, create a pull request if you want, or file some issues. It's written in TypeScript, and it's used across Microsoft. A lot of the Office products, the web versions, they incorporate Babylon in their product at some places, and it's used by a ton of external partners, as well as many third parties that just pick up and use Babylon. So this is an example of a game. This is called Age of Ascent, and they're using Babylon and the built-in features in Babylon, such as particles and instancing. That all comes with Babylon out of the box. You can see it's a rich space flight game, all working on the web and multiplayer. So you can see there's so much stuff that can go on, and they're using Babylon to support it. Moving over to the enterprise space, Babylon's also used by a lot of enterprise customers. So here's SharePoint Spaces. They are bringing SharePoint to the web, and it's interactive in WebVR as well. So Babylon supports that. So they're using GLTF models here. They can move around, view 360 videos, and bring all that goodness to the web. Jumping into some Babylon features. Babylon has a full-fledged playground right on the web, so you don't need to download anything to get started. You can just play around, edit some code, view some examples right from the Babylon website. Here's an example of particles. This is using WebGL2 transform feedback buffer to update the vertices of the particles much quicker than we could before. And of course, Babylon will fall back to WebGL 1 implementation if WebGL 2 is not supported. Next is soft shadows. So this is taking advantage of the shadow sampler in WebGL 2 to implement soft shadows with PCF. You can see the great visual quality you can get on the web, and this is using the flight helmet that Patrick created. Next is support for WebVR. You can create a basic Babylon scene, and then with one line of code, you can get VR support. We're hoping to make this really easy for anyone who's wanting to dabble around with WebVR. You can see with just that one line, it'll set up all the controllers for you, render the correct 3D model, and we're also planning to support WebXR once it starts making its way into more browsers. So with all this 3D interaction, we also just recently added gizmo control to move things in space, rotate, translate, and all these controls work seamlessly with the WebVR support that Babylon has. So if you have a VR controller, you can interact with these in there too. And as more application enterprise scenarios come on board, we also created this whole 3D GUI system that takes a lot of visual cues from the HoloLens toolkit to make sure that the visual aesthetics are consistent across native and web applications. Jumping into the Babylon viewer, this is a great way for developers who do not want to write a ton of Babylon code that just want to display a 3D model on their website. You can just reference a script, plop in a Babylon HTML tag, and import a GLB or GLTF model. Babylon handles all the heavy lifting. You can see here, you can just add it in, and if you want to customize it, like change the background, that's all possible too. And we want this scenario to be like adaptive to different types of screens. So if you're on a mobile device, maybe it'll show a WebXR view button, and here's an example of you can add VR support directly in the viewer as well. Like I mentioned, WebXR is also coming to Babylon. Here's just a small prototype running in Chrome Canary, showing it's kind of working. It's been fun seeing the kind of web move forward. And so going back to the viewer, these scenarios could become much easier for web developers to just plop in a 3D model and get something working on their website right away. So that's kind of Babylon in a nutshell. Definitely check it out. Check out the Babylon website. Play around on the playground. There's tons of examples. We're seeing a lot of interest from the community that's on Babylon. Ask questions on the forum. Everyone's pretty nice there. So thanks a lot.
All right, fantastic. So yes, please come up, gentlemen. I'll switch it over these. So while we do a small switch of the AV setup here, thank you. This is Ib Green and Yorgos Khronos from Uber, and they're going to show you some really cool large data set visualization using WebGL. Ready?
So yes, so yes, we are visualization engineers at Uber, and our job is to help literally thousands of data scientists and operations engineer to work with the very big data we collect, and so as part of our operations. And so the ability to do so on the web, and that WebGL affords us, is absolutely invaluable. And when the technology is really important to you, a really good way to invest in it is to, how do I? Oh. Okay. All right. So the really good way to work with it is to invest in the ecosystem and the community. And so we've been building a suite of frameworks that go under the VisGL umbrella, and that we were here last year at SIGGRAPH and talked about that. And so as the adoption of this has grown throughout Uber, we have also then started seeing that, even though these frameworks are incredibly useful to a lot of people, there is a number of people who can't, who are not programmers, and it doesn't matter how simple we make these frameworks. And so one of the things we've done this year to address that is we've experimented and launched an open source application that we call Kepler GL as part of this suite. And so this is basically a geospatial exploratory visualization tool. So, you do it with data that you're not familiar with to kind of find insights. And so we take basically our visualization engine, DeckGL. We also have a Mapbox.gl base map. And we add to that a user interface based on React with a layer configurator, data filters. And then on top of that, we have done a tremendous amount of work of really polishing this application. And we have been emphasizing the design. We worked very hard on the visual design. And obviously, it has a core of loading and data processing. And what you see here is basically how you use this app. It's a serverless. It has no back end. It's just hosted on GitHub Pages. You open it, you drag your data in, and you're basically, you start adding layers that interpret that. Here you see contours layer with a couple of 100,000 segments, and obviously WebGL gives you an incredible ease of visualizing that and manipulating it. And another aspect that this tool offers is also looking at the temporal component. And so you can have data sets with millions of elements, and you can animate them over time. And obviously, and most people here can imagine how easy it is to do these things in shader, but how useful this effect is. All right, and here we're looking at aggregation, which is something we're working really hard at now. So you can take your data and actually have it, so there's lots of points here that we don't see that get aggregated as grids or hexagons and so on. And we're implementing this kind of dynamic aggregation on the GPU. And so basically you can re-aggregate millions of elements very quickly, as smoothly pulling sliders. And just another highlight of what this very rich application can do. This is something we call brushing, and so you have a very big data set where it's hard to discern details. Here we have arcs that basically highlight the start and end point. Again, a simple effect to do in a shader, that really couldn't be done on the GPU. I think we should move pretty fast. We have built this as an application toolbox. So it's both an application, but you can also customize this if you want to add your own backend. So it's really an interesting concept to make applications available in this way. Of course, Kepler-GL is not the only thing we've added to VisGL this year. One of the things that I think is really interesting and valuable is something we call H3. So it's a geospatial indexing system that has many of the very desirable properties of the Google's S2, which is more cube face based. We have built a hexagonal indexing system, and that has many additional good properties, such as smaller quantization errors. You can work with radiuses. There's the same distance to every neighbor cell, and so on. So this is something we use for a lot for aggregation.
So we have DeckGL to visualize our data and render it, but what if you want to edit your data? For this, we create a new library called NebulaGL, and our goal is to have high performance, about 100K items being edited at 60 FPS, and because we wanted it to make it more accessible, we put it we put this editor on our homepage where you can load your GeoJSON data, edit it, and save it back. And if that's not enough, you can very easily, if you're already using DeckGL, you can integrate it by adding just a few more lines to your code.
So, of course, we're continuing to invest in the VisGL framework. I don't think I have time to show this. It's some pretty impressive animations that are built with a soup-up version of Kepler-GL that we showed at our Uber Elevate Summit. And of course, we're looking into all the areas we're working, including machine learning, autonomous cars, and so on. So stay tuned and check out what we can share. All right.
All right, awesome stuff, guys. Let's see. Let me close this. Okay, you're up. All right, so let me introduce Paul Chambers from SketchFab. SketchFab's been building this collaborative model visualization site for years, and they've been really pushing the frontier. So now some latest leading edge rendering techniques.
Thank you to Ken and the team here on the ground and everybody at Khronos Group and WebGL. We're very proud to continue to have a relationship with you guys, and we continue to be a good example of WebGL at scale, using using WebGL Player to share work from everybody from sort of hobbyists all the way through to professionals who need a simple way to share 3D with a link. Just very briefly here, something that we touched upon last year at SIGGRAPH, and that is our the ability to inspect models. Perhaps I'll move on. Just in the spirit of keeping this moving. Let's see if we go. But basically, just one thing I wanted to show here is the fact that in addition to the fact that we're rendering into the browser, we have exposed a number of things that used to be typically something that was only exposed to the team, which is the ability to analyze the topology of models, texture maps, and so on and so forth. And we're now using that as a feature for our community as well. You can see here some of the other aspects of this. Let's move on to the next slide. We've been continuing to grow exponentially. I'm proud to say that we now have over 3 million models online, and that's not 3 million models uploaded to SketchFab. We've had many more than that. It's 3 million models live right now online, contributed by just over 2 million community members. So just a quick overview of some of the recent updates to our WebGL viewer. The rendering quality continues to be extremely important to the team at SketchFab. Just in the past 12 months alone, we've added screen space reflection. You can see an example of that here, particularly on the floor around the table. Certainly encourage you to come by the booth to come and see some of these live demos. We've added clear support for clear coat materials, so this is a second layer material. So in addition to the fact that we can have texture maps and color data, in this case for the car paint itself, we can then add on a second clear coat, much like you would have in the automobile industry. We use a simple ray tracing system to set up now a real-time refraction even within the SketchFab viewer. And really the focus for the last year for us has been about new approaches to content distribution. So that's getting our content outside of simply the SketchFab environment itself, but out into other parts of the web. Again, I think there's some issues with playback here, so I'll just skip through here, but here's just a simple example of updates recently to our mobile app. So we're now supporting both ARKit and ARCore to take any one of the models that you've seen on SketchFab, simply a matter of a tap of a button and bringing that into an AR environment. We've also been working on extending our API access, so you can see here just a very simple example, but now we're exposing more of that information to allow a dialogue back and forth between the HTML on the page and the meshes themselves. So again, very simple example here, but that can be just a matter of swapping out meshes or swapping out materials and so forth. So there are lots of enterprise opportunities here. Moving on. In the same spirit of content distribution, we also launched our download API, and we're very proud to have partnered with Amazon and Facebook as two of our early adopters of that, a way to essentially bring SketchFab content into an application environment without leaving that application environment. At this point in time, that's our several 100,000 Creative Commons licensed models. That's also allowed us to do the same into 3D creation applications as well. We're already now supporting Unreal, Unity, and this week, I think it was yesterday, that we supported, we announced our support for Blender as well. So historically, we've always allowed export up to SketchFab from these applications, but we're now providing the opportunity, the reverse of that, to bring content directly into those applications. Probably the biggest news on the show floor that we're proud to share is something we're calling massive, and and it's not the one slide that doesn't work, but again, I encourage you to come by. The very quick short pitch on this is essentially historically with SketchFab, anything that we've viewed in our 3D player has been a mesh that's been loaded directly into memory. We are now supporting essentially mesh streaming with automated level of detail. So we can now handle large data sets. Some of the examples that we have on the show floor to share with you in excess of 70, 80, 90 million vertices, uploading that data to us. On the server side, we then chop that down into a series of optimized level of details and allow the camera to then move in and out, much like a game environment engine, but being able to do that within a browser. And then finally, as I'm getting the gong, the Sketchfab store is launched in the last 6 months, so again using WebGL to allow our community to monetize their models online, and again the ability to use exposing that inspection information has been terrific, because that means that anybody who's looking to purchase models online can now use our WebGL to actually inspect the model before purchase, so they're not sort of committing to buy something based on just simply 2D renders. They're actually getting to not only see and interact with the full 3D render, but also get down to all of the texture map detail. So thanks again, and come by and see us and learn more. Thank you.
Okay, thank you, Paul, and sorry about the AV issues, but the slides are online. Okay, so now let me introduce Tarek Sharif, who's going to take us inside the body with WebGL.
Yep. Hi, everyone. As Ken mentioned, I'm Tarek Sharif. I'm the lead graphics engineer at BioDigital. So what we do is basically anatomical visualizations for education, marketing, that kind of stuff. And over the past year, we've developed a particle system. So I thought I'd talk a bit about what the requirements are for a particle system for anatomy visualization, how we're using that. So a bit of background is why we were interested in this is that key things that we and our clients tend to want to visualize, like fluid motion, molecular interactions. We have a lot of pharma clients, so drug effects and how they work in the body. So before we had this particle simulation system, essentially we had a bunch of just tiny low-res hand-animated spheres that our artists would have to animate manually, which is very effort-intensive, was a huge pain to deal with, super inefficient. So this was an old example, an asthma inhaler. Yeah, you see these little particles coming in. There's a couple hundred of them that were all hand-animated. The heaviest part of this scene was actually the animation data, which I think was 13 megs for this thing. So good candidate for just simulating those particle effects, because we don't really care, and our clients don't tend to care about specific positioning of those things. It's just general kind of patterns of the movement. So most people know basic idea of a particle simulation. You're drawing GL points. A key requirement for us was that our artists have maximum flexibility in defining the kind of movements they want. So this comes down to really having modular little components that apply the forces and constraints and stuff, and that they can kind of rearrange them however they want. So this is one of our more recent examples, and you can kind of see that it's similar movement to the other one, a lot of control over how things are moving. This sort of activity of some compound in the kidney. So we're getting similar movement, and there's just there's no geo in here, just the definition of the forces in those points being updated. So architecture of the system, it's pretty standard, the way we have it set up, that you have sets of arrays that define each array is kind of a set of, defines one property for the whole set of active particles. So position and velocity are the key ones. For some systems, you'll have color, you'll have an age for the particle, those kinds of things. Each frame, the particles are updated by one of these tiny components. We have it split into 3 types. Creators will initialize a property when it's first created. Updaters run each frame to update forces, colors, that kind of thing. And then constraints ensure that these properties remain within certain bounds. So an example of that, for that scene we saw, is if you want, the positions have to stay within certain shapes. You make sure that they don't fly all over the screens. Not super important all the details, but this kind of shows, you can tell sort of from the names of these things. These are the component list that we have now. And you can see that it's not super huge. It's not a massively complex system, but with just these components, we can get a pretty flexible set of animations going. And as I mentioned, each component, very minimal effect, and that allows our artists to really kind of create the sort of movements that they want. So at the beginning, before this thing got too sophisticated, it was used for basic, you can see in the back here is the kind of ambient particle effects, which our artists like for cell scenes to make it look like it's floating in a fluid. And then some basic movements like or animations where it's just like kind of some cells spraying some stuff out. And then a nice thing about these kind of modular systems is that you just roll out features over time. So I'll just throw some new components at the artist, and they'll kind of go nuts and create new, just an interesting animation. So yeah, a couple of big ones that we rolled out was just like the texturing to allow them to create sprites, and then being able to animate those, like the component properties over time. So here we have just simple like Brownian motion. I'll move this forward a bit. And then you have this kind of cloud effect that's happening in the background, and then doing an add blend, you get a little bit of a flamey sort of thing on the cell in there. This one was kind of interesting one, like this whole layer here, it's a lipid bilayer, is all being done by our particle system. And that you have, just animating a collision sphere sort of downward, you get some control over like making it look like that molecule is sort of interacting with the lipid bilayer. And the last one that we just introduced recently, and this is just sort of a test scene that our artist came up with, is that having a sprite sheet animation on our particles, and now so we're simulating red blood cells moving through a vessel, and that's will be live in the next couple of weeks. So that's it. Right on time. Thank you.
All right, awesome stuff. So now that we've introspected, let's go back into the realm of games. Let me close this down. Okay, so may I introduce Will Eastcott from Play Canvas, and they're building a top quality game engine and have been for a number of years. So please tell us what's new.
Okay. Just go full screen on that. Okay, hi, I'm Will Eastcott. I'm the co-creator of this Play Canvas thing. It's an open source game engine, and it comes along with a real-time collaborative editing environment that, of course, runs in the browser, as you can see here. Now, Play Canvas is built entirely on HTML5 and CSS3 and JavaScript, and of course, WebGL. It's used to build a wide variety of applications, anything from interactive ads to branded experiences and even product configurators, like this example you can see here, which is the Indian motorcycles configurator. But Play Canvas is a game engine, and it's used widely to make HTML5 games. And we've seen it particularly come into its own on platforms like, say, WeChat and Facebook Instant Games. And we've listened to a lot of developers building these kind of games, and we've recognized lots of common demands, and 2018 for us has been about trying to address some of these key demands. So I'd say demand number one was better tooling for making 2D games. So Play Canvas has historically been a 3D game engine, but we wanted to give developers better 2D tools. So you can now use an integrated sprite editor and import sprite sheets, and then you can set up individual frames of animation, and then you can sequence those animations and then play them back directly in the sprite editor. And once you've done that, you can just deploy these animated sprites into your graphical scenes in the editor. And once you've done that, you can just publish a scene, and I'm not sure this mouse is working. I'll have to use the trackpad. There we go. So yeah, we can just control Ryu with the arrow keys. Okay, so demand number two was better tooling for building user interfaces, and historically, we've had developers come to us and say, hey, how do I build my user interface for my game? And we sheepishly said, hey, use HTML and CSS, because that's easy, right? No, it's not at all easy. And if you give that to like a front-end designer, well, like a game front-end designer, they get a bit confused. So we've gone and built a set of components that are made available through the editor that implement a whole series of user interface features, things like signed distance filled fonts, 9-sliced buttons, checkboxes, scroll views, layout groups, all of those sorts of things that you can use to build very complex user interfaces. And here is an export of that. So this is like a scroll view that has like even bounce behavior built directly into it. You've got buttons here, all kinds of stuff. So, and this was built by just a graphical designer on my team who has no coding experience at all. So that means that you don't have to rely on coders just to build these kind of experiences. And the last thing, and this is like the biggest, most major thing for us, and I'm very excited about, is full version control. So Play Canvas, as I mentioned, is a real-time collaborative platform, and when teams get large, in that kind of context, they start to trip over each other. So having a good version control system resolves that. So we now have the ability to set checkpoints in projects. And this just takes a snapshot, basically. And at any point, you can roll back, you can revert to a previous checkpoint. But things get interesting when you can create a new branch from a checkpoint. And at that point, you can work in isolation from your other team members. And then you can merge your changes back into the master branch of your game, just by saying what the source and destination branches are. But if there are merge conflicts, well, what do? Well, we present the user with a nice, easy to consume, visual difference of the things that have changed. So this is in beta right now. If you wanted access to this, just let me know and I can add you to the whitelist. The last thing I want to just mention today is that we've got full support for the GLTF2 file format. This is just a simple viewer app, but it loads a model that I just downloaded from the wonderful Sketchfab service, so thank you, Paul. Like I said, it's fully Spec 2 compliant. It supports Draco mesh compression. It's open source. You can grab the source code for that there. That's all I have for today, but I just want to end by saying I'm hiring lots of open positions on my team. If you want to work on a cool WebGL engine in sunny Los Angeles, then please do come and talk to me afterwards. Thank you.
All right, awesome stuff. So now we're going to start the AV shenanigans while we switch laptops. Let me introduce Gary Lee from Analytical Graphics. Analytical Graphics is building a virtual globe on the web that you may have heard of called Cesium. And they're going to show us some pretty cool large data set visualization in that environment.
So, are the shenanigans over? Can switch over.
Can you guys see the laptop? Okay, awesome.
Okay, cool.
I've got this one.
Yeah. Oh, I have 5 minutes. Oh, okay. So hi again, I'm Gary. I'm from Analytical Graphics Inc. From the Cesium team. And so so we're just showing off today a massive point cloud that we can show in Cesium using 3D tiles, which is what I'm wearing today. Real quick again, Cesium is an open source WebGL-based 3D map engine. And what is a 3D map? A 3D map is a globe. So it's also it's a library for building virtual globes. And what is 3D tiles? 3D tiles is an open format for streaming and rendering massive data sets. So you can kind of think of 3D tiles as like a mid-map pyramid or a mid-pyramid for more generic data, and it's also a little more flexible than that. But right now, 3D tiles can consume vector data, so like points of interest. It can consume 3D models. So for example, we have this demo that we keep showing that's like millions of buildings in New York City, and it can also do textured photogrammetry now. And 3D tiles also, of course, does point clouds, which is the main point for today. But hierarchical level of detail, it enables you to stream these sorts of large data sets over the internet, and it also allows you to render things on more limited hardware, like this woeful laptop. So I'm going to hop right over to the demo. So this demo is 6.4 billion point clouds, points. This is of a cabin complex in Pharsalia, Virginia. It was captured by a company called Trimble using 72 terrestrial LiDAR scans. What's really cool about this data set is it's not just outdoor LiDAR like you would get from a drone. They also brought their scanners inside so that you can go into the cabin and take a look at just all of the random stuff that's stored inside of here. So they also went into like the different rooms, and this is running a little slow, but something fun. so there's also this sort of underground room. It turns out what this is it's an ice pit for these old-timey cabins. For refrigeration, you would store ice in here during the summer so you could make ice cream, but now it's just holding a chandelier and a ladder. Some advantages to showing this inside of Cesium. Once again, 3D Tiles is an open format, but Cesium also adds additional tools, for example, clipping planes. Right before I get to the clipping planes, though. So we do have measurement tools that are built using the Cesium API, if I can find my mouse. So here's a demonstration of sort of like an area measurement tool. If you wanted to roughly click out the area of this roof here. And also the clipping planes let you do really cool things like, if I shut this off real quick. So again, this is an indoor-outdoor model, so it has a surface for the exterior of the cabin and the interior of the cabin. So with our measuring tools and clipping planes, you can actually do something like measure the wall thickness. If that works over there. So another thing that Cesium has is classification of the point cloud based on metadata. So this data set came with per point attributes that we can use to sort of color things by what's the cabin, what's the ground, what's foliage and things. We can also use this to show and hide different things and to adjust the color. This is all being done using shaders and wonderful GPU stuff. And Cesium also allows you to add, one second, sort of manual classification volumes. So if I go ahead and move this over here and scale it up a little bit. If I, here's the scale tool. And then I can go ahead and apply this volume. And this is volume, so it acts as a colored annotation, and we can also use it to isolate portions of the tile set or hide portions of the tile set. Yeah, and sort of to wrap up the demo portion, just to show off sort of how detailed this demo is, I'm gonna hop into this. I think this is the densest view inside of the tile set. I'm gonna go ahead and shut off our point attenuation. And I am going to allow Cesium to call down some extra detail. And it should start to fill in almost 1 point per pixel. So this kind of reminds me, I recently learned that offline renderers will sometimes tessellate geometry down to the level where like a triangle is smaller than a pixel, and woohoo, this is kind of like that. So yeah. So yeah, that's pretty much it for our talk. Thanks for listening. Once again, this data is courtesy of Trimble. They were kind enough to let us test our content pipelines on this. We've been working on a lot of content pipelines. And visit us online, and that's our contact information as well.
Great job, Gary. Thank you. Awesome visualizations. Okay, so next, the man who needs no introduction, Ricardo Cabello, who is the founder of the 3JS project. He's going to tell us everything of what's new and what's been used, how 3JS has been used over the past year.
Huh.
Do we have to change the mirroring settings?
How do you do that again?
We are running about 5 to 10 minutes late, so apologies for holding you from lunch, but hopefully this is exciting enough that you want to stay. Yeah. Gather windows. You want to?
I think it's working right. This is my screen.
Oh, okay, great.
Yeah, I think that you're sending it. All right, okay. Hello, everyone. Thanks for coming. I'm going to do this is quite a bit of content, so I'm going to try to go as fast as possible. So this is an update for this year. I want to start with a couple of quick samples to kind of show an idea of the kind of things that people are doing with the library. If it loads quick enough. a music video in WebGL, you can move the camera and pan the camera around. Everything is in sync with the music, and it also works with WebVR. You can look around also in a similar way. It is not interactive, but I think it's a good example of how quickly the whole thing loads and how quick it is to show a pretty enticing music video. Next one is a more random one. This is, I don't know, if this is supposed to be music. If possible, don't mess with the music, I'll control it myself. All right. So yeah, this is some sort of editor that you can customize your scene with different characters and add your own dancers. Like change the scale. I think this is the kind of thing that I was hoping people will do in WebGL eventually. I'm happy that it's finally happening. Anyway, this is like 2 quick examples to kind of see what people are doing with it. All right, so this is the Earth year with the libraries. There's been 95 releases, and we're almost reaching the 1,000 contributors. And what I've been learning this year, well, all the year, is that the whole open source approach is easily to not get super scalable. So you get to a point that there's too many pull requests, there's too many issues. So something I've been trying to work a little bit this over the last months is to try to make it whole workflow a little bit easier. So something I've adopted is like GitHub milestones, which basically allow you to assign some of the pull requests or some of the issues to specific milestones. So that way I can communicate to the contributors these issues, I like it, I'm gonna put it on this revision, and somehow they have a more feedback with whatever decisions we make them the people that are maintaining it, whether we're gonna merge it, or whether we like the feature but we put it on that RXX, which is something we like it but we don't know exactly where we're gonna put it. So that actually has helped a lot to deal with the amount of submissions at this point. So yeah, that's kind of more or less how it works. And so far it has helped a lot. It allowed me to actually have move to releasing one version every month. So this year has been 7 so far. So some of the features since last year is we now have more self-rendering objects. So for instance, reflector is an object that you can put on a scene kind of in a plug and play kind of way, and it's gonna render on its own. So whenever it's time for it to be rendered, it renders itself. So in this case, the mirror, knows that it has to render itself from the reflection, has to put a camera at the bottom, and it renders the scene from there, and then uses that as a texture, basically. Refractor is similarly, but it would have it to the reflection. It just renders to whatever is behind it, and then uses that as a texture, and you can distort it. So you can do this kind of refraction effects. Similarly, but reflector and refractor, one object that can reflect and refract the bottom at the same time. Lens flare used to be part of the render, the render itself. Now it's outside, and they also become objects that you just plug them on a scene, and they know what to do and which time to render it. Wow, only 30 seconds left. Or the sky is a similar way. You can put them in scene, and they just render themselves. Thick lines, the OpenGL only. WebGL doesn't support only supports 1 pixel lines. Now we have one using instancing. Cloud loader. We had the previous one, the optimized one. Now is we upgraded it to be the main one, and it loads things pretty quickly, and using pretty well the memory pretty well. I'm sorry, I'm going to run a little bit late. We have a loader for G-code for 3D printing, so you can preview 3D objects without having to print them. The loader for SPX is pretty robust. We can export things for Mixamo in low loads, as you will expect. The GLTF2 loader we also have a fork of the GLTF loader, so now we only have one GLTF loader that loads only the 2.0 version, and it's funny enough we're using the same example as the previous presenter for showing what GLTF. So I guess we are moving out of the helmet. I don't know. This is a nice scene. All right. It has animation. SVG loader. Now we can load the SVGs, and we just triangulate them. So this actually helps a lot for so designers can just drag and drop their designs. We have exporters like GLT exporter. So yeah, any 3D object on the scene, you can just use this exporter and it creates a GLTF for you, so then you can just download it. Also, we have a plot exporter. We don't have examples for it. Controls, we have controls for like maps, which is a typical, kind of like typical thing that people, interaction that people tend to use, and we have one for them to use. Transfer control, we have a new version of it, which is the one that, like, this one is way more helpful and more, I think people were finding a lot of bugs in the previous one, so this one is just ready also like to control the objects that, as you're used to basically on 3D packages. And then we are deprecating the JSON exporter from Blender because it was just never worked correctly, so we are focusing on the GLTF workflow instead. So we're like recommending all the people to use GLTF as much as possible. WebXR, this is something I've been working on a little bit, and so in order to have like a VR on your scene, you only have to do like VR enable true, you need to pass the update function to the renderer, and then you need using this like WebVR JavaScript library helper or utility, it allows you to have like a create a button that is just takes all the work for you for doing like sending the device to the renderer basically. But this is all you need to add to any project that you're doing for having a VR support. Also for controllers, you want like drag and drop things, like this is how the API looks like. You just ask for this VR object, you add the controller that you want to use, and then you have like those two events. Well, you have 3 events: select star, select n, and select. And with this example, we'll show like whenever you click on an object, well, kind of. Actually, this is not a good example because those objects are actually 3D objects, so it's changing themselves, but they're invisible. Anyway, I should improve the example, but this is more or less how it works. And then you will have to raycast from there to the scene to see you select something, and yeah, this is more or less how the API looks like. So this is using Daydream, the Lenovo Mirage. So this is like now on Lenovo, on Daydream you have a Chrome VR that whenever you go to a website that has that VR enable, you can enter it, and this is one of the examples that we have where whenever, like that line is the controller, so whenever you click and select, it just drops balls into the scene. There's another example that is dragging objects, and another example that is like drawing like kind of tool brushy thing. Those are like examples that are the usual. The good thing of this is that the same code runs in all those headsets. I don't know about like HTC Vive Focus, but I haven't been able to try it. But I think it's great for like the fact that WebXR, WebVR, the same code works in all of that headsets without having to modify it. Same thing. Something that we're working on is the WebXR, the AR version of it. This is some of the early tests where you can actually load that FVX model and put it in your scene using in this case, it's like a modified version of Chrome. Some tests. And Mozilla this year have been helping a lot and contributing. So they actually added like WebGL 2 support to the render, although we don't have an example for it yet. But like right now, we actually don't have like 2 renders. It's only the same render, but you can pass a canvas and a context to the renderer and then the render will know that it's a WebGL 2, so it will convert the shaders to GLSL 3, and it will do their own thing. But now we're adding more features to it. So like Fernando is adding transfer feedback. We're working on it, and also like he's been working quite a lot this week on adding a WebGL multi-view. So as like Ken was explaining before, like this is something that he just had running this morning. So this scene is running at 60 milliseconds without that extension, but whenever you enable the extension, well, I guess I'll have to wait for it. Sorry. Come on. All right, anyway, it runs twice as fast. And holographic displays and this and that, and then, yeah, that's about it.
All right. Thank you, Ricardo. I mean, I can't stress enough, 3JS is used on most websites that use WebGL, and so having these features like WebGL 2 support and WebGL multi-view support built into 3 like automatically upgrades every website to be WebVR and WebXR capable, and that's mind-blowing. If your mind isn't blown by that, I don't know what it should be blown by. Okay, so let me introduce Simon Colwade and Adrian Bloomer from Esri. This is our last presentation, and this one should be mind-blowing too. They're visualizing huge cities on the Earth with non-photorealistic rendering. It's really cool stuff. Okay, are you ready?
Hello.
Wait.
Do we have an image?
Yes. Okay, here we go.
Okay, I'm Simon, this is Adrian. We are from Esri R&D Center in Zurich, Switzerland. And we're part of the development team of the ArcGIS JavaScript API that allows our customers to build rich 2D and 3D JS applications for the web. Now, obviously, today we'll focus a bit on the 3D side of things. One thing I would like to mention is that because of our customers, they still run on kind of dated platforms sometimes. So we cannot fully embrace WebGL 2, which we would like to do, but we have to make sure that most of our stuff actually works on WebGL 1, including some extensions. So the first thing we would like to show you is some recent development concerning level of detail rendering. So in the past, we had like a 2,000 feature limit, so you could only display 2,000 objects per layer, which worked fine, which is brute force instance rendering. But we decided to lift that limit and basically allow to have tens of thousands of objects. So obviously, if you want to render like high polygon models like these trees, yeah, you need to render with multiple levels of details, and this is a bit of a challenge. We would like to use new stuff like transform feedback, which we can't. So basically, each frame you have to, for each object, you have to find out what the appropriate level of detail is, and there is no way to do that per frame when the camera moves. So what you do is kind of a batch system, which at each frame only updates a part of the object, and then over a couple of frames, you actually get like the proper selection. If anybody here has some experience with these kinds of systems, I would be loving to talk to you after this. And now Adrian is going to show you some other cool stuff.
Yeah, hey guys. I'm going to talk to you about edge rendering, which is a feature that we released earlier this year, which basically allows you to take a scene like this here, a city scene, lots of buildings in 3D, but it lacks, well, recognizability of individual 3D objects, partially due to contrast. It's highly dependent on the scene lighting. And yeah, it's difficult to make out individual buildings. So what edge rendering allows us is to take this scene and turn it into something like this. And basically now you can make out individual buildings. Oh, sorry, not used to Mac touchpads. But yeah, allows you to make out individual building units and gives the whole thing a more abstract, well, cartographic look, which we are aiming for. And the way we do this is, well, many approaches usually use post-processing on some screen space buffers, but instead what we do is at loading time in a web worker thread, we pre-process this geometry, extract important edges, categorize them based on impact on the final object, and then we render them using 4 vertex billboards. Again, WebGL, some limitation on like line rendering thickness, so using billboards allows us to vary thickness of the individual edges, adding special attributes, do some fancy effects, one of which I'll show you in a minute. And also importantly, allows us to do anti-aliasing during rendering, which is very important if you look at edges in the distance where it would just become a total mess when you reach sub-pixel coverage. Now, all these edges have quite some attributes stored with them, and the trivial thing would be to store all these attributes for each vertex of each billboard. To cut down on memory consumption and to speed things up, we instead use instanced rendering, so the instancing extension of WebGL, and basically every edge you see here is an individual instance. I see I have 30 seconds left, so let's continue. One thing is also that we use distance-based LOD, so this data is stored in nodes, and for each node, we store the edges sorted by their world space length. So during rendering time, we can then select just to render the first 50% of the buffer, something like this, based on the distance, allowing us to do thinning and adjust performance. Okay, and to wrap things up, just quickly, I mentioned other fancy styles. So this is something a colleague of mine at our Zurich office created, which is another edge style, which we call, well, sketch rendering. And what we do here is we use noise to perturb our edges on each billboard, giving the whole scene a more hand-drawn look. And yeah, I mean, if you look at it, looks like it could come from a newspaper print or a comic book or something like that. And yeah, let's leave it this. There's much more to talk about here. If you're interested, come talk to me. Thanks.
So I hope that you all are inspired to make even better WebGL creations yourselves. Please either catch us after this presentation or come to the Khronos networking session later this evening, and we'll be there and would love to talk with you all. Thank you for coming, and see you soon.
We lost the music. Sweet. Yay, thank you. Are we good? Okay, great. So thank you everyone for coming. I want to welcome you to our OpenXR talk on standardizing realities. So we're looking toward making a standard that will standardize a lot of the options in the immersive compute space, AR, VR, and MR. And we have a lot of very talented people working on this from different companies, and I'm going to talk to you today about the state of where we are. We've got some exciting demos to show you, and so let's get started. So here we are. We have a big proviso to start with, which is that the spec is a work in progress. It hasn't been released yet. We are getting a preview of it here. This is the second time we've given a preview of it, so this will be more detailed a little bit than the previous one we gave. And things will change before we finally release the specifications. So just to give you an idea of where we've come from, we started our first version of the spec in January 2017, had 52 pages. When Nick gave our first public talk on this in March, we had 268 pages, and we're now at 291 pages of spec. So I'm kind of hoping we'll asymptote at 300 pages. I'm hoping we're coming to the end of this process, so that's great. So the spec does have bugs. You may see things in here that you're like, hey, that wouldn't work. That's, you know, it's quite possible. There are some that we know about. There are some that we probably don't know about yet, because we're all working on our first implementations, and so we're going to develop them as we go along. As far as this talk goes, I'm making the assumption that you know something about AR and VR, something about how virtual reality works. Probably not going to cover some basic details of that, but I'm not assuming you know anything about the Khronos specification process, so some of you may not know. And that's okay. So this talk will also not cover all 291 pages of the spec. There are a lot of things and systems that we're not going to talk about. The things that we are talking about are the things that we feel are quite solidified now. So they're the things that we feel are pretty core in the spec, and they're probably not going to change, things like our mainframe loop and things that we think we have down pretty well. So, and of course we will have after that our exciting demos. So today we have the first public demos of OpenXR. We're going to be doing demos from Starbreeze and Microsoft. And we will show you the demos, and then you'll have ample time at the end to ask questions of me, of Nick, our chair, and of Remy and Alex, who are giving the demos. So it's great. So a brief history of the standard. One of the big questions when we started this was there's a lot of players in this field, and the question of can we get these people together to agree on something? And it's been pretty amazing ride, the people that we've gotten to agree. As Nick likes to say, we've gotten cats and dogs to the table. We have Unity and Epic at the table, you know, talking about what they want and getting things together. We have Oculus, and we have Valve at the table. We have Google and Microsoft at the table, although I have to say Alex is a little bit ornery, and he has strong opinions about things, so we have to see about that. So here's kind of where we came from. We started with Joe Ludwig of Valve going on a day trip, yes, a day trip to Korea to propose this standard at the Khronos face-to-face there. And we actually had our first working group face-to-face together in the ballroom next door in January of 2017. That is where we adopted that original specification, which came from, we had several proposals come together. We had a great one from Sensix that we took parts of, and we had one from Oculus that kind of united their proposals and united their APIs from the Rift side and the Gear side. And we kind of took the core of that and we combined some aspects of the other specifications, and that gave us kind of the base of where we started from. So from there, we had face-to-faces in the spring and in Amsterdam, and we decided that we needed more because we had a lot of work to do. So we actually had extra face-to-faces at Valve's offices in Seattle. We defined our MVP, our minimum viable product, in Chicago. From there, we had more interim face-to-faces. That one in Seattle in the interim face-to-face is one where we locked all of our rendering programmers in a room for 10 hours. Fortunately, Valve has deodorant in their bathrooms, so we're good. So Taipei, we've continued. We've been working on, we had our first public launch, our first public information, which Nick presented at GDC this year. We're all working on our implementations, two of which you'll see today. And today we have the more updates and the demonstrations. So from here, we'll talk again more about this at the end and talk about what happens next. So next up, our goals and philosophies for OpenXR. So this is kind of the problem space that we started in. We have, on the right, you can see, on the left, I guess, for you, you have all of these VR applications. And there are so many different ways for a VR app to access all of our runtimes. You can either write your own rendering engine, you can use a proprietary engine, you could use Unity or Unreal. And from there, all of those, you could also use, since Brandon is here, it should be on this diagram, you can use web browsers, so you can use Chrome to access web applications. So you can access all of these platforms in those multiple ways, and you can, from there, there are a number of devices you can do. Some runtimes, like Daydream, which is what I worked on. Daydream has only, well, we started with only one device, so we have that, and that many platforms have multiple devices that they can use. Some devices are usable on different platforms. So we wanted to let's go to the next slide. So we wanted to solve this kind of space by having two layers at which OpenXR would interface. The first layer at the top is the API layer, so that all applications who are wanting to speak to a runtime that is doing immersive compute, whether it's AR, VR, or MR, could speak a common language. And the bottom side of that, if you go and, as Joe likes to point out, if you go and buy a printer, you can just plug it into your computer and it knows what language to speak. Our dream would be you can go and buy a VR device and the same thing happens. It knows what language to speak. You just plug it in and it understands. It understands how to talk to a runtime. So that would be fantastic. So that's kind of our two-layered approach to having solving this VR, the fragmentation in the VR space. So let's talk about our OpenXR philosophies. So first of all, one of our biggest goals was we wanted to enable VR and AR applications, and actually MR applications, and in fact other immersive compute spaces like caves, and there are so many tabletops even, there are so many different ways to do immersive compute now, and I think that we can all probably agree that we don't even know half of what is going to happen in the next 10 years. It's a really exciting space, and there's a lot of new development. So we want to make sure that we're able to support a wide array of the space. So we want to be pretty future-proof, which is pretty scary, but we do know some ways to be future-proof. We've learned a lot of lessons about from Vulkan about how to be future-proof, how to have extensions. Even OpenGL has extensions, so we've got good ways of doing that. But also we found some new ways to make our platform and make our platforms and make our APIs extensible. One of them is specifically semantic paths, which I'll talk about a little later. We don't want to try to predict the future of XR technology, so I think none of us know what's going to happen. I feel like immersive compute right now is a Swiss Army knife, and there's so many tools that we haven't even figured out yet, and they're going to be fantastic. So we'll see what's happened, and we'd like to be extensible enough to support them. So we also want to work on unifying performance critical concepts, because things like right now, especially, we all do our frame loops very differently. And we all block very differently. So we all block very differently in our frame loops, especially like for Daydream, we block on the acquisition of a buffer to draw in. For Oculus, they block, I believe, in submission, so they block when they're submitting. And Valve blocks on the acquisition of input because they think that's a very important time, and they want to minimize latency. So that's great, but it kind of makes Nick's life terrible, because when he's trying to write an engine that is going to do a frame loop for XR application, he's got to write 3 different frame loops, and then he has to somehow communicate to his users, his developers, how to optimize that, and that's kind of not a great scenario. So in order to make the space better for everyone, we've been trying to talk about how to do that in a common way. So here's a diagram that kind of shows what this will look like. You have an application at the top, and then there's an OpenXR layer. So all applications will be speaking OpenXR. Now that application may actually be running on Unity or Unreal. So it's possible the application will only be speaking to Unity or Unreal, and then Unreal would be speaking only OpenXR. So then in that case, Unreal wouldn't have to speak 4 or 5 different APIs. This is actually especially valuable when you have something like Chrome as your surface layer, where I'm pretty sure Brandon doesn't want to input, have the memory to put these 5 different APIs in there. So below that, you would have 2 different runtimes, or many different. So say on an Android phone, you might have a Gear VR runtime and a Daydream runtime running. One of them may use the device plugin extension, and one of them might not. So it's possible. There are some reasons not to use the device plugin extension on some platforms, and we'll talk a bit about why we might make that decision. But some of them will be able to use the device plugin extension, and then you could just plug in your device as though it were a printer, basically. So OpenXR, again, taking a great lesson from Vulkan, is a layered API. So the layering allows us to insert into the call stack. If you as a developer, or you can insert a layer that will give you more information, but you can then take out that layer at runtime at your production build so that you are not having the overhead of doing, say, validation in there. And I give some examples later of layers that we might want to insert. So you can insert a layer, for example, that gives you more information on why your application is, whether you're doing compositing in a smart way. So let's talk about the architecture of OpenXR. So a little bit about the primitives that we use. So one of the basic concepts is handles, which we take from Vulkan again. So oftentimes we need a runtime that needs to be able to allocate some memory on behalf of the application and return it. And we use handles for that. So handles, they're objects, and they are opaque identifiers, so the application cannot query specifically things about the, they cannot specifically query things about the handle, and they are because they're specifically runtime specific. So as it did when I'm writing Daydream, I might implement my handles in one way, and Alex could implement his handles completely differently, so that's up to us. Their lifetime is completely managed by a create and destroy, which is in the application's hands, so it's up to the application to create these handles when they're needed and destroy them when they're out of scope. They're hierarchical, which means that if you have, say, for example, our outer layer is called an instance, and inside that we have a session, which we'll talk about a bit. So to create a session, you need to pass an instance. So the instance is going to be the sort of the parent case of the session. So now let's talk about semantic paths. So semantic paths are our way of encapsulating. We don't want to pass strings around to identify things like a space or a device or anything else. We want to be able to talk about them in a way that's sensible. Strings are obviously too slow, so we kind of reduce them to an atom, and we make semantic paths that are hierarchical, and I'll give some examples of them in the next slide. So they're all stored in a string table, so we map your strings to this atom. The string is human readable, the atom is obviously not, but you can anytime get a mapping back and forth to do your work. Some semantic paths are reserved. For example, I might reserve a controller button, and then you can't actually create that, but you can create your own, supposing you want to create a space in your application, a definition of a coordinate system, and you can just define your own, and you can create a handle for that and pass it to the runtime. And then the runtime will understand it from then on. So that's good. There are some, we've now made the case, it used to be, if any of you saw our presentation at GDC, it used to be that we had uppercase in our semantic paths as well. They're now all lowercase only, 0 to 9, a few delimiters that are allowed. They are null terminated, and they're not file paths. So here are some examples of semantic paths, which makes it a little easier to understand. So for example, to refer to a controller on your left hand, user hand left. So you can see it's hierarchical, user hand right. And then we had user hand primary, I think user head. For spaces, for example, space head, space hand, left grip would be the coordinate system of that left grip. Then for devices, if you are a device manufacturer, you can create your own semantic path for your device to being your device, vendor name, your unique identifier, your type, your component. So you could have your trigger click, for example, being your particular device component and functionality. So let's talk a bit about spaces for a second. So XR space is kind of the general representation of a coordinate system, and we use them all through the API for different things. We use them for head poses, we use them for controllers. It's the same concept. The runtime can hold any representation of a space it wants internally, so I can represent that in any way that I want, which is really useful for us for a number of reasons. So they're also independent. So for us, for example, in AR core, we we might choose to make spaces into anchor points, whereas other people could have spaces be something much more dependent and hierarchical. So they could be independent. Some spaces might relate to other spaces. Some spaces might not be able to be relatable to other places. For example, if I look over at that speaker over there, the speaker might be in one anchor point, and I might not yet be able to relate it to the other speaker over there if I don't have tracking information on the space in between. So that allows us to do some pretty fun things. In certain cases, like motion controllers, spaces can be attached to track objects, right? So your space could be actually attached to your sensor, which could be updated, and therefore it would drift also. So let's talk about our loader now. So how many people in here are familiar with Vulkan, just so I know what's going? Okay, great, a fair number of people. So Vulkan has a loader. In OpenXR, the loader is going to be optional to start with. There are some reasons for that. Specifically, the biggest one is on mobile devices. We have pretty strong security requirements, and loading a third-party DLL or binary is not really a thing in a secure space where you need access to user-secure protected memory. And so we'll get there, but we're probably not going to be there for our first release. So that's why it's not required. But in general, the OpenXR loader is the thing in the middle, and it communicates with applications. It has access to runtimes. It has access to device plugins and any layers that are created. So if those of you who are familiar with Vulkan should be pretty familiar with how this works. So we have our OpenXR trampoline terminator pattern in the same way that Vulkan does. So the loader will start with a trampoline that can intercept the function call, and that function call can be directed to a layer if that layer is present. And then it can be directed to a terminator at the end if necessary, and then finally sent to the runtime. And again, if the layers are present, they would be specifically specified by the application. We want to run with this layer. So if the validation layer is present, your call could be sent to the validation layer before it's sent to the runtime. So you can do something with that there. So here's a bunch of examples that one of our representatives from LunarG wrote for us, which is just all the different ways you could make calls across layers into the runtime. So it could stop in a layer, it could stop in both layers, it could avoid the layers, it could actually terminate in a layer. I thought that's interesting that we can actually stop in a layer, have a function that only exists in the layer and doesn't exist in the runtime at all. So we talked a bit about that. So let's talk a bit about core versus extensions. So some of you who are very familiar with Khronos may understand this. Basically, we have a core standard. So there's our core, which is the minimum that every runtime needs to implement. Then there are extensions. Some of them that are commonly used by all runtimes are in the same IP zone as the core standard are called KHR extensions. So for example, we have a bunch of KHR Vulkan extensions that will allow you to run with Vulkan, although not every OpenXR runtime is required to use Vulkan. So some runtime may not be able to use Vulkan, and it would not use that KHR extension. EXT extensions are outside of the core IP zone, so they could be very vendor specific, but their EXT extensions are often used by a number of vendors, so they're not one vendor specific. And then we have vendor specific extensions, which can be either public and they could be completely private. So if, for example, if you as your company are working on some secret sauce that is really cool and you're not ready to release it yet, but you need an extension to work on it with, you could reserve an extension number and do whatever you want with it, share that with your partners, share runtimes that use it with your partners, and you don't have to make it public in any way. So let's talk about layers and what they might be. So validation we talked about a little. That's the obvious layer to have to sort of validate that you're using the runtime correctly. Another layer could be platform application quality. So you could put a layer in there that tells you, for example, you're using pre-multiplied alpha, and this platform, or you're not using pre-multiplied alpha, and the hardware on this platform only supports pre-multiplied alpha. And yes, you can do that, but we're going to be doing all of your calculations in software and not in hardware, and so your application will probably not run as you're expecting. So we can insert a layer to tell you that. And then you take out that layer when you're running in production, so you're not doing all those extra checks. Debug panels are another really useful case. We can put in there to capture, say, the number of frame drops that you have. That layer can be capturing that information and then displaying it to your screen in another way, or into a secondary display, and doing whatever it needs to tell you the information you're looking for. So from there, let's talk about application life cycles, because they're actually pretty complicated. I have here two two platforms that are used by members of our working group, Android and Windows 10, and had some discussions with Alex before about whether I had the Windows 10 lifecycle correct, which is kind of interesting to me, but here's the Android lifecycle for sure, which I know is correct. So you can see it's got states and transitions the same way, states and transitions pretty much for Windows. So these life cycles are really useful, but sometimes they don't actually even give us enough information. For example, in Android, I cannot tell you based on this life cycle when your surface is going to be available to be drawn to and when your surface is going to not be available to draw to. And I see my coworker Ariana smiling at me because she had many bugs related to that. It's difficult to tell these things, and we have to, so when we're thinking about the OpenXR lifecycle, we need to think about whether it's going to work on all the platforms that we need it to work on. So this is what we've tried to do, and so we have this outer layer, which is the instance, and the instance is basically the application's representation of the OpenXR runtime. So the application gets an instance. It's similar to a Vulkan instance, and the instance can have extensions and layers, and all of those things can be enabled for the instance. So the instance is created by a discussion between the loader, if there is a loader, and the application. They negotiate, and then we create an instance. The instance gives you the ability to create a session. The session just defines an interactive session between the application and the runtime. So here's the hardware that I'm going to run on. Here is what I want to do. Here's what it's going to look like. And now in our specification, as well as an instance, a session can actually have its own extensions. So you can specify extensions for a session specifically. Swap chain management is all done here, so this is actually the first time where we actually really need to know what underlying graphics platform you were using, whether you're using Vulkan or OpenGL, because we need to create your swap chain and return something to you in the language that you want us to speak. So again, after you create the session, you can begin the session, which basically is the time when you say to the runtime, hey, I actually want to render frames now. And that's how we do that. So we have events that come back too. Some of the events are pretty simple. Visibility changed is one of them. So your application may not be visible anymore. You've changed the focus. We can also, sometimes the runtime might get a message from another application that says, hey, I want to draw now. So your application might get a request from the runtime to stop end your session because something else wants to draw. We have availability changed, which means, say, a device has been lost or has been taken off. Oh yeah, the engagement changed is your device has been removed from the user's head, so they're no longer using it. Input and haptics. So a lot of our input stuff came from Valve's contributions, and Valve does input really well, and I think it's reflected in a lot of their knowledge and expertise is reflected in OpenXR. So I'm pretty proud of the stuff that we have here for input. So we go through this layer of abstraction called an action. So you can, as an application, say, I want to have a move action. And you don't have to say that I want to press the X button or the triangle button, or I want to use this controller or press A or whatever. You just say, I want to move. And you specify that specifically, and you create an action. And the runtime will bind your action to something in a controller that's connected to it. And there's some really great things that allows. For example, if you, as a device manufacturer, create a super new shoe binding that you tap your foot twice to move, and it's a great new device, then you can actually tell the runtime that you want to bind that to move. And so the device can talk to the runtime, and the runtime takes all of that information in and just makes a decision of how to do that binding. So this allows us, basically future-proofing. This is a great quote here from Joe Ludwig from Valve, who said, dev teams are ephemeral and platforms are forever. Although I love Nick's comment on this, which he thinks it's totally unfair because he works on a dev team. So basically, we want to make this platform be as extensible as possible because it's really, just like with Android, we have to support everything indefinitely. So we want to make sure we are extensible that way. So we allow runtimes to mix and match multiple input sources. Again, like I said, you could have your move action be bound to a controller or to your spiffy new foot tapping device or many different things, and the runtime can synthesize all of that. We have optionals, we can have new things coming in. It also, this last point is one of my favorite things about it, which is that as a device manufacturer, if I do create a cool new device with the ability to, say I create a device that does gestures, and I do an exciting circle gesture, and I want that to mean something, I can have that communicated to a device as being move if I wanted it, or say it's a move gesture like this. Then the runtime can actually, I have an existing pool of content of applications that want to say move, and I can hook those up to my move action, and suddenly I've got a pool of content that I can use to test my device with. So I think that's fantastic. So here's specifics on what an action is created with. An action has a name, that's a short name that's kind of teleport, like that idea. It has a localized name that's sort of human reasonable, good for debugging or for informing the user. It has an action set, and we'll talk about that in a little bit in the next slide. It has a suggested binding, so you can actually suggest, hey, as an application, I really want my move command to be this button on the controller. But the runtime is not actually obliged to do that. It can change its mind based on what hardware is available, but you can say, I would really like to use this button. And there are some action type flags that you can specify to tell what kind of data it is. So if, for example, it's a D-pad, you can say it's a vector 2. So you can do that. So there's another type of input action, which is the pose state, which allows for adding new tracked rate. So we can actually specify poses as actions and use that data to communicate between the app and the devices. So let's talk about action sets. So this is, again, Nick's example of his kitten petter VR. You might have a mode where you're actually petting the kitten and a mode where you're in UI and searching through the menu. So you can collect all of your actions up for your kitten petter mode, and you can also have your UI mode, and then you can swap between them. So I'm saying right now I'm in the petting mode, and these are the actions and how they map. And now I'm going to switch to the other mode and UI mode and have different actions for each. And I want to say, I'm going to skip Nick's example for a second and say I think my killer app for VR is actually having Vim in VR, and I want to switch between insert mode and have all my insert mode bindings. And clearly having a text editor in VR is the future. So. So here we go. The opposite part of input and haptics, which is pretty cool, is that as a user, sometimes as an application, you want to tell the user, okay, press something to teleport. What do I tell them to press? How do I know what controllers are connected right now, and how do I know what the runtime has bound? So I can ask the runtime, hey, I want to tell the user to teleport. Tell me what to tell them, and the runtime will tell you, okay, here's the path that you can tell. Here's the model you can draw to say, here, draw this and show the user to activate to trigger this way for teleport. So there we go. It's moving on to haptics. Right now we just have one haptic type, which is XR haptic vibration. There is every potential to extend this in the future. We've tried to make it as open as possible. So right now we just have this start time, duration, frequency, and amplitude of the haptic event. So I definitely expect more types of haptics to get added. I expect one of the first things that will get added is corded haptics that are coordinated between devices. I think that would be fantastic. But for core, this is like the core of what we need for moving on for haptics. Okay, frame timing. So again, as mentioned, we locked a bunch of people in a room. A few of them are in this room right now. I see Adam over there, and Alex is here. And we made them come up with 3 functions after 3 months of work. And so you guys are... So it looks pretty similar to many frame loops that you've seen. One is it has XR begin frame, where you start a frame. XR end frame was when you're done rendering and you're ready to hand off, and you have to give a mapping between what you actually rendered and where you want it drawn. And XR wait frame, which we call to kind of synchronize timing and throttle the app if you're running too fast or if you're running too slow. So frame timing, so a bit more into XR wait frame, which is deceptively complicated for a small function. So we have, you specify a swap interval here. So swap interval 1 means we're going to render at the next frame, at the next native refresh cycle. Swap interval 2, which means we're going to render every other vsync cycle or every other native cycle. Swap interval 0 in OpenXR is invalid, which if you're an Android programmer is not the same thing it means in Android. In Android it means just throw it to the screen as soon as you can, don't even bother to sync anything. But in OpenXR it's not valid. So throttling of the application is done by the runtime. It tries, and we'll show you some pictures of how that works, to try and align GPU work with compositor's hook time. So here we go, our first frame chart example. So the best way to look at this is to start with the blue, which kind of does actually look taupe now from this angle. All right, Nick was telling me it looked taupe to him. I'm like, the one that starts in frame 101 is the sane, sensible frame, where the application does its work on the simulation thread. It finishes in plenty of time and passes off its work to the render thread. The render thread takes over. It calls the green diamond XR begin frame when it's ready. It does its frame rendering. It calls XR end frame at the end. And then it passes off work, and it's done until the next frame when XR wait frame is called again. So that's great. So if you go back to frame 100 there, this frame was late. It arrived so close to that compositor frame hook boundary that the runtime knew I can't possibly get this frame displayed in time. So in this case, you can see the XR wait frame, the yellow arrow and diamond there, is pushed off a lot longer because it's actually trying to synchronize and saying, hey app, I'm throttling you because you're not going to get this frame out in time. Let's do this next time. So this is why it took 3 months, and I totally blame Unreal Engine for this because their engine is quite complicated, but it does some great stuff. So they have what's called a render hardware interface thread, this RHI thread. So they have their render thread, which does a lot of work, but then it passes off to these render workers and the RHI thread to actually generate the render commands. And it has a render thread fence, which is between the render thread and the RHI thread that tries to sync up and figure out when to coordinate passing off data. So between all of that, this makes it a lot more complicated, but I think we've got things set up now with begin frame and end frame and wait frame so that we can make this work and make the simple case work so it's not too complicated for people who are just writing simple applications. So, all right. So let's talk about swap chains. Our swap chains look very similar to Vulkan swap chains. So we have XR create swap chain, which actually creates the swap chain. After you've created your swap chain, you can call XR get swap chain images, which could be passed to you in any order. That's important. So that you'll get a list of images that you can render to. When you enter your frame loop, at the start of your frame loop, you need to acquire a swap chain image to draw to. So that is a potentially blocking application, but if you've sized your swap chain correctly, hopefully it will never block because you have enough swap chains to just grab one and it'll be fine. That is another thing that you could put into a layer, by the way, informing you, hey, your swap chain is too small. Maybe you should increase the size of it. So XR wait swap chain image is going to, XR, yeah, that's going to, you get your swap chain, so wait is actually going to be the one that waits until it's available if it's not, which hopefully it will not. You actually do your drawing. When you're finished drawing, you release the swap chain images. Then after that, you would call your XR end frame, which we talked about previously, and when you're done all your rendering, you destroy the swap chain to release the memory that you allocated. So compositor layers. We have layers that you pass to the compositor. So when you're rendering, you're going to render into layers, and you can render layers. By the way, we have some arguments over whether that is the right name, so it might change. We have many things called layers in the API now. But we have layers they're aggregated by the compositor into the XR end frame, and they're mapped to swap chain buffers. So you can use multiple or up to the limit of the runtime. So runtimes may have a limit as to how many compositor layers they can support. They have basic XR composition layer data, which includes the swap chain, the current index in that swap chain, the type of layer it is, the display time, the eye, any space that's associated with that layer. There are 2 types of layers in core, and we have some extensions that support really more exciting types of layers, perhaps. So let's talk about these 2, and then I'll mention a few of the extension layers. So multi-projection is the first one. It's the most common type of layer where you have a projection for your left eye and your right eye, and each has a standard projection matrix. The quad layer is a quad projected into the world, so it's just basically a billboard in world space. So those are kind of our two common core layers that every OpenXR runtime is expected to support. The more exciting layers are cylindrical layers, which are really useful for text rendering, spherical layers, which could be very useful for video, we have some other cube map layers, which are used for our backgrounds that don't change. And those are all layers that could be supported on different platforms, but not every platform can support them, so they're not part of core. So from there, let's talk about, there are lots of ways you could configure an XR device, and there are lots of types of immersive compute. So these are 3 types that we have support for right now. And when you create your session, you're going to specify what viewport configuration you're going to use. There is camera pass-through AR on the left side there, which is basically you have a phone and you hold it up to the world and you're doing magic from it and you're tracking and you have anchor points in the world and you're figuring out. So that's basically what AR Core is doing, for example. Then you have stereoscopic VR, which is a traditional, you put the HMD on, you have two viewports per eye. You might have a different kind of stereoscopic VR, which has four viewports and is doing foveated rendering, for example. Then you have cave projection and cave projections, which use many viewports, but it's still the same thing. You're still projecting the same data. You just have different viewports. So applications can query the active XR system ID for its supported viewport configurations. So when you create an XR system, you get an system ID, and the system will tell you, hey, I can do AR pass-through and stereoscopic VR, but I'm not a cave. So it will give you a list of what it can do, and you can query that. You can also, because the hierarchic paths are, the semantic paths are hierarchical, you can query viewport configuration / VR, what VR viewport configurations do you support as an application. So you can change aspects of the active configuration over the life cycle. So if you change the interaction, you want to go into VR, you want to come out, whatever, you want to change things. You can make changes to some things, but not to everything. So we'll have more details on that later, but we're trying to make it as flexible as possible. Runtimes can request that the app change configuration entirely as well, but the app is not required to comply. So an example of when that might happen is if, say, you're running too slowly and you need to go to you need to use a smaller viewports, or you need to change something. The runtime can make a request for that, but you're not required to comply. You just might not get the performance you expect if you don't listen to the runtime. So viewport projections, I will skip over this a little bit because I want to leave plenty of time for demos and things, but basically we have viewport projections, and the viewport projection has, each projection has a number of viewport projection infos attached to it. These might be eyes specifically, so it could have a left eye projection info and a right eye projection info, or you could have as many as you want. So now let's talk a bit about the device plugin. So this is kind of a chart of showing kind of basically how the device plugin works. On the left side, you have the OpenXR runtime, which is, it's going to be your Gear VR runtime or your Oculus runtime or your Valve runtime or Vive runtime. So you've got that running. In the middle, you have a driver layer, which is your driver that's actually talking to the device. And on the right-hand side is the device. So at the top, you can see the device making a connect request to the driver layer. And that would not be in any language that OpenXR speaks. That's going to be between you as a device manufacturer and your device driver, how you specify that. But once you receive that call from your device, you would call XR Device Plugin Connect KHR. Again, this device plugin is a KHR extension because we expect a lot of people to use it. We're hoping almost everyone will use it, but it's not required because not everyone can do it. So device plugin KHR, and you pass in the instance, you pass in the device plugin info, and you pass in, you get back a device plugin. So that's specifically, and once you have your device plugin, you can call XR device plugin create device KHR, which will actually create the device in the runtime. And after that, you can start making calls on it. An example of one call you could make on it is to set the tracking status of that device, saying that it's currently tracking or it's not tracking. And then from there, we would get, if you get no response back from your device, you can change the device status. So that is basically how our device plugin works. So let's talk a bit about, we've talked a bit about the spec where it is, so let's talk about where we're going. So here we are back in our updates and first demonstration today. So from there, in September, we have another face-to-face meeting where we'll be talking more about implementation conformance and refinement. We have some plans for conformance, but they're not complete yet, and we know it's quite important, so we'll be talking about that more in September. We're going to be talking about our implementations. We're all working right now on our OpenXR runtime implementations. You'll see a demonstration of 2 of them in just a minute. So that is good, and from there we're going to go and make a provisional release. So we have plans to provisionally release the spec as soon as we can, and we will release it all and ask for feedback. So the spec will go out to anyone who's interested. It won't be released properly yet, and we'll ask for feedback. And we know we have issues that we know about. We want help to find all of the issues that we haven't found yet. So hopefully we'll get lots of feedback and we'll be able to correct anything that we have wrong. We will, from there, have our conformance testing set up, and we will have implementations actually built and running against our conformance tests. All right. And from there, we go to the Khronos ratification. So we have to actually get ratified by Khronos to release. And then we will actually release our specification, hopefully alongside of a couple of runtimes that are actually shipping and running it. So that is kind of where we are for, where we're going for the future. So from there, let's go on to talk about our demos. And I'm going to introduce Nick, who's actually the OpenXR Working Group Chair. And he's going to give you a discussion of what our demos are going to look like. He is a technical director for Unreal. And he is our working group chair. And I apologize in advance for his sense of humor.
Hey everybody, thanks for coming out. We wanted to demonstrate live today because a presentation really isn't fun unless you have the constant threat of looming catastrophe. So we decided to make it exceptionally challenging today by not only having to switch AV in the middle of a live presentation, which if you've ever worked with AV is somewhat terrifying, but we also wanted to show a demonstration of the same piece of content running through Unreal Engine right now. It's the Unreal Showdown demo, which is available to anybody that wants to download it. It's a piece of content that we made, I think, 4 years now. Time is all blending together and flying by. But at the application level, for UE4, we wrote an OpenXR compliant plugin. And our hope was that people could take this plugin, write compliant runtimes, and then that same piece of content, the same build can be run on 2 different things, on 2 different pieces of hardware showing exactly the same. So we had a pretty interesting case here. We've got on one hand over there, the Windows mixed reality headset, specifically a Samsung Odyssey headset, which is running through using inside-out tracking. And then on the right, we'll have the SPIR-VR headset, which they debuted yesterday or the day before yesterday, which is interesting because it's using a different viewport configuration. Instead of just the left eye, right eye, it's actually using a quad viewport configuration because it's got 210-degree field of view. So Unreal handles both of these with the same plugin. Everything is the same, and we're kind of living the dream. Now, like Kay said earlier, my interest in OpenXR was really to make my life easier. So instead of having to write 20 plugins for Unreal Engine, I can just write 1 plugin and have it work all together. So today is the first demonstration of that. And to do that, we have from StarVR, Dr. Remy Arnault, who has a localized picture. That's him standing in front of the Gastown clock. He's the chief architect officer at Starbreeze and has been leading the efforts for the StarVR SDK. And then next to him, we'll have Alex Turner from Microsoft, who's the principal programming manager and has been kind of leading their efforts to get the Microsoft Windows Mixed Reality runtime kind of up and supported through OpenXR. So with that, we will unplug an HDMI cable. Things might catch fire. And then hopefully we will see on one screen the Microsoft version of the runtime and the other screen the StarVR version of the runtime, both running Showdown through Unreal at the same time. So let's hope nothing explodes. We have 2 screens. That's good for a sign. No sound though? All right, so we have Alex. Oh. Yep, there you go. Remy, you want to put yours on as well, and hopefully we'll see it. All right. So SPIR-VR, Microsoft's dogs and cats living together. OpenXR lives. And I still can't believe that all worked live. Watching them gesticulate is half the fun. Is it blowing your minds? Oh, look at that. It's doing the full Neo. There you have it, no fires. Everything worked. A huge thanks to all the people behind the scenes at Microsoft and SPIR-VR that made it happen, and shout out to Jules Block, who we recently hired at Epic that helped with the implementation for the plugin. So with that, I think we're ready for questions. Awesome. All right. So does anybody have any questions? Sure. Do we have microphones for the audience, or is it just... yell loud and we'll repeat the question.
Yeah, we can repeat.
Figure out how many runtimes are there and do all that stuff manually, right? There's no just like event-based system that would just provide me all the headsets that are in the system and I can just pick one of them.
So just let me repeat the question for the audience on the microphone, which is we have one instance per runtime. So how do we find out? You've got a microphone now. Do you want to?
Yeah. So the question is, if there is one instance per runtime, then I will see two available runtimes, for example, Oculus and SteamVR, and I need to manually pick one, right?
Yeah, that was one of the earlier things we talked through as a group and tried to figure out, hey, how can apps enumerate this? And the main catch was kind of for the very first app you run, we could like enumerate all of them and let the user pick. But there's many cases where perhaps the user's already in the headset, or maybe they're launching the app from within a headset, and there's really kind of a right answer. The user likely doesn't want to switch headsets while they're in there. And we were kind of debating ways we could support both. So one of the simplifications for OpenXR 1.0 is that there's kind of a user intent to which is the current runtime on the system at any point. So kind of if you launch like SteamVR and you end up having like the SteamVR widget, that's kind of a user intent that that's my like default or current runtime. And then apps that go to the loader and they discover which runtime would find that particular runtime. And then the user could change that at any point by launching one of the other environments. And then as we start to learn from that, we would perhaps expand that to let apps enumerate and choose runtimes.
And I would say the demo today is kind of the simplest version of that, where we just have a JSON file and an environment variable that says, pick this runtime, use this loader. But a lot of that we expect to be kind of encapsulated in the loader. It's something that people can make. If you have an idea or for a management system or something, anybody can make it and hook into there.
Okay, and the second one is kind of more complicated. So you have just XR begin and XR end. Is it encapsulating all the GPU work in the frame or just the post-dependent one?
It's encapsulating all the issuance of draw call commands to the GPU, but it doesn't necessarily capture the entirety of the GPU work being executed itself. Does that make sense?
Because my point is that it's not like a console, right? There will be other processes throwing GPU work that can derail application GPU work from time to time a little bit, right? Like just shift the workload. So from my point of view, it makes sense to separate all the framework into post-dependent that should be executed as last as possible and post-independent that can be executed as fast as possible, right? And it looks like there is only CPU synchronization mechanism here. There is no like GPU synchronization, like GPU events. Like for example, compositor is signaling event on a GPU and it's done, and my application can start as soon as possible post-independent workload, right? There is no such stuff.
Yeah. Specifically, we have cases, for example, on Earth where you're downloading textures from the internet and you need to composite those texture tiles into a texture to render, and it may be for a frame 10 frames down the road and not for your current frame. You can do those. So I think, did you ask this question at GDC, by the way?
Yeah, but
I thought it was a fantastic question, and I think, yeah, there's definitely GPU work you might want to do as an application that's outside of your post-dependent work. It's just work that you need to do that you're getting ready for some future frame, and it's not something that you need to do in between the begin and end.
I think it's also something that we don't explicitly fully address because there's so much variability at the driver layer for GPU preemption and platform layer for GPU preemption that I think it would be tough for us to fully specify it and leave room for innovation on there.
Okay.
Yeah, a lot of the runtimes will do kind of their own adjustment, live adjustment and hysteresis around like CPU and GPU and when to wake up, and so some of the wake calls will try to handle that, and then like, we might discover over time there's different knobs or different kind of runtime specific weights that people might experiment with. And I think we're trying to carve off something we think is going to address like most of the cases at the core to get that unification. And part of the benefit of extensions is that people can still experiment with exactly that.
Okay, thanks.
On the point he was talking about, pose-independent GPU work, when you create your swap chain, if you're working with Vulkan, are you going to be able to get down to the level of, I'm creating it, I want to use this queue with this priority for the GPU submissions for the XR work?
I was going to say, there's kind of a difference between the rendering that you're doing as an app and the rendering that the compositor is doing. So you might be using Vulkan for your work and your level, and you might have a runtime that's using OpenGL. So, I mean, it doesn't have to be the same thing. You could have a runtime that's using an entirely different system than the one that you're using too.
Okay, so the API doesn't enter into the swap chain creation?
It does somewhat. That's why we have them all as KHR extensions. So that's probably the part that's the least well-defined at the moment. Platform work is kind of being solidified a little later on. Right now, there's basically, we can specify a bunch of the parameters for Vulkan swap chain creation, but we can't fully specify them yet. So.
The other thing I wanted to ask is if you have an application that wants to switch between, say, a VR mode and just a 3D rendering on the desktop mode, are you planning on making that possible without sort of leaving the OpenXR environment, such that you have like essentially a desktop plugin that's a very simple plugin for OpenXR?
That sort of concept is kind of encapsulated within the XR session stuff that Kay had talked about. So you activate and deactivate an XR session, which means I'm going to be sending frames to a headset or not sending frames to the headset, which would be going back to the display.
Well, okay, so would you treat like the there's no plan to say have the desktop treated as this is just a monoscopic view, I can fetch it as a device?
Yeah, and that's currently even a thing that's kind of different between runtimes, and we'd probably have an extension to communicate. Some runtimes will show kind of a mirror view on the desktop automatically, and they'll do that in some efficient way and pull it out of the compositor, and others expect the app to do it. And so currently a lot of apps will just render their own desktop view, and they have their own efficient ways to do that. So we're currently generally leaving that up to the app. If it wants a monitor view, it can do that itself, or it can rely on the runtime.
I wanted to add that we believe the runtime should have a lot of power there, because when you have an app that's designed for one environment and then you want to run it, let's say in an LBE system with a different type of hardware, or you want monitors for the public to see, or like we did today, you want to be able to do some settings in the runtime and don't change the app and recompile the app, so this has an impact. Oh, by the way, I wanted to apologize, but there is no way to show 210 degrees on the screen, so what you've seen, it's totally not what I saw in my headset, so I invite you to come see for real the demo in our booth in 210. But no, for example, that's why you want to be able to give power to the runtime for those settings.
So we have another group coming in here at 2, so we need to vacate, but there is a reception after, and I'd invite anyone to come to the reception, and please come and ask more questions.
Yeah.
And we'll also...
Yeah, and as Robbie said, come by booth 620 and 210 and come see our demos live on the expo floor.
Yeah, we're actually neighbors on the show floor.
Yeah.
Thanks, Gary. Sorry, I didn't presentation. I'm just concerned about Not awesome. Anybody know how to do this better? I guess we'll go with this. So welcome everybody. This is the beginning of the Vulkan sessions. I kind of wanted to call it hardly strictly Vulkan, but then I realized that it actually is almost entirely Vulkan. Hats off to Piers, who bravely is going to talk about OpenGL in a couple of minutes. So the agenda for the rest of the afternoon looks like this. We're trying to talk about these APIs from various perspectives. So we're going to start with a working group perspective from me and other working group chairs, TSG chairs. And then we have a couple of guys talking about language issues. Hai Nguyen, who gets the prize for the best title, mark my D words, is going to talk, I believe it's about special debug tooling, is that right? Yes. And then we'll close with two of our very favorite high-end game developers talking about using Vulkan in modern game engines. Notice that, well, you can't quite tell on the slides, but there aren't really any structured breaks here. We have tried to allow 5 minutes between sessions for Q&A, and there will be one laptop switch right after I present. If you feel an urgent need for a bio break, Q&A is your chance, dude. Go. And I suggest run, don't walk, because you won't want to miss stuff. If you don't get to ask your questions during the presentation, please come or stick around till 5:30 or come back at 5:30. For the reception, I think the way it works is we knock this curtain down, turn on the strobe lights and the dance music, or maybe not. At least there's beer. At least there's some beer. But that is also, not all of the speakers can stay, but most of them can. And so that's a great opportunity to talk to them or talk to any of your peers who are in this community together. So starting with the working group perspective, I should have said my name's Tom Olson. I work for ARM. I chair the Vulkan working group. Another agenda slide, sorry. So I'm going to talk about Vulkan, and I'm going to hog most of the time. Some of it on where are we today, but most of the focus on what are we trying to accomplish and how are we trying to accomplish it for the future. Neil Trevitt will give a special report on the portability initiative, which has some exciting news. And then Piers will give us the OpenGL ES view of the world. So where's Vulkan today? I'm going to start with rather quickly going through some kind of basic stuff. So many of these things you may know, so that hence covering them quickly. On the driver front, we're kind of at maturity now in the sense that every vendor who's making a GPU, leaving Apple aside, a special case, but all of the major GPU vendors have Vulkan drivers for all of their current hardware. And it's proliferating and building out to the point where we've got open source drivers as well as proprietary drivers for Intel. AMD has 2 open source drivers. It's all pretty awesome. Not to say there aren't challenges, and the big ones are that just because you can get a driver doesn't mean you did. Like my mom does not update her computer very often, being 91 years old. So she does not have a current set of drivers. And there are the usual problems. Laptops are hard to update. Mobile devices are really hard to update, despite Samsung's heroic efforts, by the way. Shout out to them. So there's hardware driver situation. On the platform front, it's great that Vulkan is officially exposed and supported on Android. Not every device, it's got to be a capable device, but every device that has a Vulkan-capable GPU, pretty much these days, ships with a Vulkan driver. And then Linux is also a friendly environment. On the Windows front, support is very good, at least availability is very good on Windows 10. It's somewhat less good on Windows 7 due to restrictions that I believe Microsoft imposes. Windows 8, as far as I know, is extinct in the wild, so I don't know if, I think some of us have drivers, but I'm not sure they're actually shipping. But again, there is the question of available doesn't mean present, and so that's the next challenge. There is also the gaping hole in the platform story, which is iOS, macOS, and UWP, otherwise known as Windows 10s, which are closed platforms. You can't install a third-party driver on them. We actually have a solution for that, which Neil will talk about later. Game engines, compared to last year, again, the ecosystem's building out. Situation is pretty good. Every major engine has a path. The challenge here is that it's not, in many cases, it's not the default. So if the user doesn't explicitly enable Vulkan, it runs on some other API. Often there's a good reason for that, and that, again, reflects that there are challenges in the ecosystem. So I'm going to be talking about these challenges later on. Compared to last year, the content story is awesome. There are quite a lot of games shipping on desktop, a number of which shipped, or at least initially, as Vulkan only, which is very exciting. And you know, this is kind of my GDC slide, so this is not GDC. It's not all about games. If any of you went to Real Time Live last night and saw the awesome demo from Pocket Studio, that's a collaborative filmmaking software platform. They now have a Vulkan backend, which they announced from the floor at Real Time Live. So that's very cool. Mobile, again, the story's good because the Android support is so good. There's some late-breaking news as of a couple of days ago. We just found out Fortnite is now shipping on Android, or it's available on Android, and it's shipping on selected devices. It runs on top of Vulkan. The details of this I'm not completely familiar with. I think it was Samsung exclusive for a while, and I don't know if that's still the case. But it's coming to Android in any case, and it's coming to Vulkan. So that is very cool. So those were the pretty pictures. Now we get the engineer stuff. The way that I track developer interest, there's a couple of measures. The folks at LunarG are kind enough to, and savvy enough as engineers, to keep track of the download rate for Vulkan SDKs on the platforms that they support. The signal's very noisy. It correlates somewhat with high-profile game announcements and blog posts, but the trend, nevertheless, is relentlessly up. And since GDC, I mean, I showed a plot much like this last year, but since GDC, we now have data for macOS SDK downloads as well. And that story's looking good. My personal favorite way to track developer interest is the GitHub test. I go to github.com, I type Vulkan into the top-level search box, and at SIGGRAPH 2016, it said there are 431 projects that make use of, or that mention Vulkan in their text somewhere. And I've been tracking that number for a while, and I track it at other times of year as well. And the result is that I can now plot the data. And it's actually shockingly linear. It just freaks me out. It's actually more linear than it looks because my data points are not equally spaced in time. But I can do the math. And GitHub is adding almost exactly 2.5 Vulkan-related projects every day for the past 2 years. So that's kind of the very, very quick view of where Vulkan is today. Again, I invite your questions when it comes time for questions about, and I'm also very curious to know how you see it. But this is how we see it. Basically a good story, but there are definitely challenges, and those challenges need to be addressed. So I want to talk about how the working group is thinking about that. Before I talk about specifics of what we're doing, I want to talk philosophy, as Kay did earlier in her presentation. And basically the way the working group is approaching this is we drive everything we do off of that top line question, what do Vulkan developers need to be successful, to deliver their content successfully on Vulkan? As spec geeks, we tend to think in terms of, oh, our job is to add features to the Vulkan spec, and you know, what should we add next? What should be in 1.2, et cetera. But that's wrong-headed, and we've come to realize it, and we're thinking much more broadly now. What are the things that make it hard for people to develop on Vulkan, and how can we make it better? So API and language functionality is one thing, and it's an important thing. But so is ease of use and tooling. That's equally critical, particularly with a gnarly API like Vulkan, where if you don't have tools, if all you have is the API in your compiler, good luck. So tooling's very important. Implementation quality is very important because debugging Vulkan is hard already, and if you can't trust your driver, it's even harder. And even sort of mundane things that you might think are out of Khronos' control, like availability, are concerns to us. Basically, any problem that is your problem is also our problem when it comes to delivering on Vulkan. And we're trying very hard to keep these things in an ordered list and sort it by priority and get your input on what those priorities need to be. So that's the philosophy with which we're approaching stuff. So I'm going to run through those categories, and the first one was functionality. The big news since SIGGRAPH a year ago is Vulkan 1.1, but that came out at GDC, so you all know about it, right? So I'm not going to say very much because I don't actually have time, speaking of time. So a number of very cool features, which I've hit the highlights here, but there's more like 30-odd major features in Vulkan 1.1. The main thing I wanted to point out actually is not what are the features that are in it, but that everything you see there are actually two small exceptions, came out as a KHR extension first. So one thing we're doing with KHR extensions, I know some people are reluctant to use extensions. A KHR extension in Vulkan is taken absolutely just as seriously as a core spec. We have the same criteria for shipping. It must have conformance test. There must be 3 implementations passing the test before we even publish the specification. It must have validation support at release. You can rely on a KHR Vulkan extension to be as high quality as we know how to make it. There is also, of course, maturity over time, and until developers start running into it, there will be bugs we won't find. But it's not for lack of effort. It's as mature at release as a core spec is at release. Okay, got sidetracked by my passion there. Right, so lots of cool features, but you already know about them, so I won't talk about them. Since GDC and since the last time we talked in public, we have a couple of new things. There's some small ones which are housekeeping, which I did not put on the slide. But KHR draw indirect count, this generalizes draw indirect so that you can have a variable number of indirect draws and have the GPU say how many there should be. So it's a kind of a step in an as-DOE direction, and it allows you to do what Vulkan does best, which is to get the CPU as far out of the loop as we can put it. 8-bit storage, this extends, so Vulkan 1.1 added the ability to have 16-bit data types in buffer objects. Now you can have 8-bit data types in buffer objects. That's particularly interesting for compute, as you're going to hear Erik talk later about running OpenCL kernels on top of a Vulkan implementation. OpenCL treats bytes as first-class data, so that's an important feature. And finally, descriptor indexing. This is our answer to bindless. So it's the ability for you to index into a very large table of descriptors. Since descriptors are opaque, we can't store them in variables, but we can select them at runtime. So this gives you essentially the same capability as bindless texturing and bindless resources on OpenGL. It's not KHR yet, and the reason is validating descriptor and bindless textures is really hard because now suddenly the compiler can't tell you whether, because it's the halting problem all over again. Compiler can't tell you whether you are screwing up. So when you might select, and we can't determine what you're going to select until we actually run the shader. So that's one reason. The other is just time. We wanted to get it out, get some developer feedback because we weren't quite sure we got it right. It will be KHR in the fullness of time. And people are using it today. We have lots of things that we are thinking about in the functionality area. And I'm not going to go through these in detail. I want to hearken back to what I said earlier. We drive our priorities off of what we hear from the ecosystem. These are things that we think have certain degrees of importance. and these are near the top of our agenda. But the agenda is dynamically prioritized based on what we hear from the ecosystem. So if there are things here that are particularly interesting to you, or you have use cases that are blocked because you don't have these, that's very important for us to know, and we're very grateful, even if we may not always look like it, to have your input. Okay, so that was all about new functionality in Vulkan. I want to talk about the next thing would be tools and ease of use. That's a big problem, and the tool ecosystem around Vulkan is very large, and the Khronos group doesn't control even half of it. It's much more of a community thing. A lot of emergent projects, which are incredibly cool, like RenderToken. That was not our project. It came out, and it is the most awesome Vulkan debugger ever. There are some that we do consider that are primarily our responsibility, and validation is one of them. The validation work was originally designed and developed by LunarG, a Khronos member who is also deeply involved in developing the Vulkan ecosystem. This is their data showing coverage over time of validation. Everybody knows how validation works? Anybody not? Everybody knows why you need validation. Okay, so the red line at the top of the chart is the total number of valid usage statements in the Vulkan spec. In principle, validation should check that your program is obeying every one of those, because if you break even one of them, you get undefined behavior. You see that the number's been growing over time. It doesn't just sort of go along flat and then jump when Vulkan 1.1 comes out. It gets built up incrementally as we add KHR extensions, and also as we realize, crap, we forgot there's something that has to be true for this to work, and we add additional stuff after the fact. So that number's been climbing over time. The green line down at the bottom climbing up is the number of valid usage statements covered by the validation suite. You can see that it's behind, but you can also see that it's catching up. Slowly, but it is catching up, leaving the blue line, which is the number of uncovered validation statements, is declining, again, slowly. That picture is going to get better because the conversation started before GDC, but particularly picking up now, we've agreed that we're going to take the load of developing validation for new features off of LunarG. That is the routine stuff that's relatively straightforward, how to validate it, argument type checking and stuff, we'll do that. And they're going to because they have special expertise in validation, they're going to tackle the really gnarly stuff that we don't know how to validate. And that should cause the slope of the green curve to tilt up and let us catch up faster. A couple of things that LunarG is working on in the advanced validation area, which are really exciting. Something they call GPU-assisted validation. The idea here, you've all used tools like Valgrind? How do you tell if you have made a reference through a pointer that points to garbage? The only way you can really do it is to instrument your code. So tools like Valgrind or Purify go in, and every time you make a memory reference through a pointer, they insert some code that checks whether it's a sane reference. LunarG is going to do the same thing for SPIR-V. So when you create a shader that, for example, uses descriptor indexing to fetch an index that might not be valid at runtime, they'll insert extra SPIR-V code that validates that it actually points to something, it's initialized, and it points to something that is appropriate for the reference you're making. That's actually the hard case, and they're going to do that one first. Then they're going to do the easier cases, which is checking bounds, array bounds checking, buffer bounds checking, et cetera. And that should help catch a lot of the gnarlier bug cases that you get in Vulkan. They're also doing work to extend the synchronization validation. There is some already. There's already checks. I hope Carl's not going to kill me, but I believe there are already checks, for example, if two different threads try to access a non-thread safe Vulkan object, I believe that you can enable testing that. We'll see. Say yes, Carl, you can do that. Carl says, yes, that works. But they're going to extend this further to harder synchronization cases. Another challenge, bugs in the drivers. Vulkan drivers, we did our very best, but when Vulkan drivers first hit the market back in early 2016, they were not mature, and the quality was variable. So we have been investing heavily in this. This is the largest single engineering project that Khronos runs. We have 3 full-time employee, well, they're contractors, but they're under contract to Khronos to work on this, plus tons of work that is done at the member companies. Project leadership is done at the member companies, et cetera. So this is the trend of test cases in the Vulkan conformance test since SIGGRAPH 2 years ago, picking up about 100,000 test cases a year. We're also trying to have better cases, more driven by developer experience and less by close reading of the spec, because sometimes the spec talks about corner cases that nobody's code ever actually hits. Something new, Vulkan, sorry, not Vulkan, but Khronos traditionally has a rule that if you can't pass, if you're an OpenGL vendor and you can't pass the current conformance test, but you can pass an older one, you can submit using the older one. And that's done because the hardware pipeline's long, and it would be really nasty if you spend 3 years developing a part and then discover in the last week that it doesn't pass the latest conformance test. We have that rule. With Vulkan, we're aggressively trying to shorten that window, that grace period, as much as possible. So it is no longer possible to make a Vulkan submission on the 2017 era, say pre-SIGGRAPH 2017 conformance test. It's deprecated. You have to pass the newer one. And we're just going to keep that sliding window moving forward linearly in order to get the older, to force implementations to pass the highest quality bar that we can reasonably ask. However, I should say, well, not on the slide before, but you probably knew that all the validation layers are in open source on GitHub. So is the conformance test. And if you are seeing things, you're trying to develop code and you're seeing bugs in implementations and you're thinking, why the hell doesn't conformance catch that? You can tell us. Go to GitHub and raise an issue that says, hey, there's bunches of implementations that exhibit this behavior, which as far as I can tell is out of the spec. And we will take that in. If you want to write a conformance test for it, that's even better. But we'll settle for the bug report and we'll be grateful to get it. Another challenge, availability. I alluded to Apple platforms before, and is it Unified Windows Platform, Universal Windows Platform? Windows 10s. Both platforms where we can't ship Vulkan drivers. That is, the GPU vendors cannot ship a Vulkan driver even if they want to, because the platform doesn't allow it. So the portability initiative exists to address that need. And I'm going to let Neil talk about it. There's URLs and things here, but because he's going to talk about it, I won't. Those are sort of, so I've talked about a bunch of the challenges that we face in terms of implementation quality, tool quality, spec features. The things that, we feel like we have a handle on those. The things that worry me are the things that we don't know about. And here we depend on you, the developer community, to tell us what is stopping you from delivering successfully on Vulkan. And also, relatively, we'll take as much information as we can get. It really helps us to know not only is this a problem, but how bad. Of the various problems that you face, which are the ones that are real showstoppers? We will put full court press on that and address them as fast as we can. So there's lots of ways you can tell us this. For general issues, we have a new group called the Ecosystem Forum. It's mostly devoted to tools issues, but any issue that you see that you want to tell us about, raise it on GitHub at Vulkan Ecosystem. If you read the spec and something doesn't make sense or you don't understand it, raise an issue at Vulkan Docs. That is the spec, and you can build the whole thing right there. If the SDK isn't working for you or you're having issues with components of it, The LunarG website, vulkan.lunarg.com, is where the SDK is managed out of. And, anywhere, as I said, we'll take your input in any format. I have been known within Khronos to say, please no Twitter, but I'll settle for Twitter. I'll even take that. So it's a recent version, and I can't explain where it came from. Okay, so that's kind of that story from me. We're going to let Neil and Piers talk, and if there's any time left, we'll take questions then and then move into the next.
Cool. Thank you, Tom. Welcome, everyone. So I'm going to talk about the Vulkan Portability Initiative. The whole premise and differentiation of Vulkan, of course, that it's portable. It's not proprietary. We can take it to multiple systems. So developers only have to develop once and they can ship everywhere. And we're getting pretty close. As Tom has said in his slides, we're shipping on Windows, we're shipping on Linux, and that's Linux on the desktop, Linux in the cloud, Linux in embedded, Android. Tom left out Switch. Switch has conformant, Nintendo Switch has conformant Vulkan drivers, and of course Android. And people go, yes, Neil, that's all very nice, but what about Apple? And so, as we know, we're not allowed to ship native drivers on Apple platforms. So the Vulkan Portability Initiative started there, but it's actually now a little bit more general. So how do we solve this problem, getting Vulkan apps onto locked platforms? So the Vulkan Portability Initiative, what we're trying to do is to put the infrastructure in place. So third parties, multiple third parties, the more the merrier, who want to put a porting layer for Vulkan over some other native API, has the infrastructure and testing support they need to ship as reliable a solution as possible. So we're doing a number of things inside the Vulkan working group. The first thing is that we're spending quite a lot of time, quite a lot of brain power, figuring out how do we port Vulkan over APIs like Metal and DX12. And the good news is that we've figured out how to port almost everything. So Metal 1, for example, there are only 5 pieces of functionality there on the slide that we can't port and layer efficiently over the underlying API. And that list actually gets even smaller with Metal 2 that's shipped. And as the underlying APIs continue to evolve, that list is going to probably get smaller and smaller. Then we want to have a agreed cross-vendor, cross-platform way for these portability layers to expose to the applications. Well, I'm doing this portability layering for you, but here are the list of functions that I can't support. So the application can query, and there's a standardized way to do that. So we're creating, it hasn't shipped yet, but we're creating a portability extension that will be the standard way for applications to make that kind of query. Then we're working along with the LunarG folks who, along with shipping the Mac OS SDK, so as well as running your apps on Mac, you can develop your apps on Mac. LunarG are porting some layers to enable the use of these layers in a good development process. So a dev sim layer and a validation layer. So even if you're running on a full Vulkan, you can pretend you're running on a subsetted portability layer Vulkan and debug your application. The conformance tests, of course, are key. If you're a subset of Vulkan, you can't be fully conformant, but for these layers, you want to encourage them that everything that is exposed should work properly. So we're kind of being driven from the list of missing features, and we'll turn off the relevant tests that are not applicable because that functionality is missing. But we're encouraging these layers to have everything else, everything that is there and present in the layer, be fully conformant and pass all the tests. And of course, that will feed back into the extension and new ways of filling in some of the missing gaps. So the third-party implementations is where the rubber hits the road. And the first one out the gate is Molten VK, a company called Brenwell Workshop was working on portability layers for many years, and they had Molten VK that was used to be a paid product. You know, they're a small company. You buy their product, and you could use their porting layer. But working with Valve, they've actually now brought that into open source. And they leverage lots of the SPIR goodness, the open source tools ecosystem, SPIR-V Cross in particular. So you have your Vulkan program with Vulkan SPIR-V. These layers will typically take the SPIR-V programs, pass it into SPIR-V Cross, where it gets transcompiled into metal shading language if you're running on metal, and then you bring it back in and put it into those metal shaders into the Apple compiler chain. But the runtime linking from the Vulkan calls into the metal calls is done by the runtime layer, Molten VK, and this is now in open source and shipping. And actually the first production apps have shipped already using Molten VK on the desktop, Mac desktop. The upgrade to Dota 2 from Valve, it's a free upgrade to their hundreds of thousands of users, is shipping today. And we've had our first, as of a few weeks ago, we've had our first couple iOS apps ship through the Apple App Store using the Molten VK porting layer. The performance is pretty good. I mean, a porting layer, of course, is always, is it going to be performance? The Dota 2 running on Mac OS is actually faster than the previous OpenGL version running on the Apple OpenGL drivers, up to about 50% faster, but faster across the board. So it's a nice performance upgrade for the Dota 2 users on the Mac platform. And Valve are happy to report there's been no significant support issues or surprises through using the portability layer. But now, even more exciting news, now we have our second implementation out of the gate. It's in open source, and it's GFX-RS from Mozilla. They're actually being even more adventurous. They do have a metal backend, and Valve, they've been working with Valve. Valve has let them run Dota 2 over this portability layer, and they're actually getting pretty good performance. They're actually slightly faster than Molten VK right now. They focused on optimization first. Now they're working to fix the conformance coverage before they formally ship. But they're also working on a DX12 backend. So UWP platforms like Xbox, for example, that might be interesting if we can bring a porting layer over DirectX 12. And these guys are working hard on that, and some links in here. Everything is being done in the open, so follow along. And I'm going to sneak in one slide. Tom did agree I could do it. It's the only place in this agenda that it kind of fitted. Nothing to do with portability. We're actually here at SIGGRAPH because there are lots of educators here at SIGGRAPH. We thought it was a good place to launch the Khronos Education Forum because it is an important part of the overall ecosystem. We get developers coming up and say, you've just released a complex 800-page specification and you want me to teach it? Now, help. And so we want to provide some help. So we're going to be setting up a simple, but hopefully effective, open forum that the educators and the industry can come together to collaborate and communicate on creating course materials. The Khronos working groups will do their best to provide review and guidance to make sure that materials are high quality. There's no fees involved. It's open to everyone. You don't need to be a member. Just send us an email. We'd be glad to get you on board. And we want lots of happy students learning lots about Khronos technologies. Thank you. Piers.
So don't let these Vulkan guys fool you. OpenGL and OpenGL is still alive. And I'm here to tell you, in the next 5 minutes, that's all they gave me, to tell you that, yes, it's still alive. So my name is Piers Daniell. I work for NVIDIA. I am the OpenGL chair, and I'm also now the OpenGL ES chair. We haven't merged the groups or anything. We just merged the meeting times because most of the people that attend, the members that attend, do both anyway. So it makes sense to run the meetings at the same time. And by doing that, we improve efficiency and we can work on our product. So over the last year, our product has been fixing spec bugs, updating the specs, and also updating the quality for implementation, so updating conformance. So over the last year, we've updated both OpenGL 4.6 and OpenGL ES 3.2. They were released in June. Tons of bug fixes for issues are reported through GitHub, which is an easier way to collaborate with the community. And also, we've actually merged the source code for the GLSL, GLSL, excuse me, and ESSL specs. They've now merged into one source document. It makes it more maintainable. It's all part of the Git toolset now, and it makes it a better quality product, less divergence. So big news this year, it's 15 years since OpenGL ES 1.0 shipped. And when ES 1.1 came out, it was shipping on the iPhone and Android devices, and that quickly exploded into millions, hundreds of millions, now billions of devices. So OpenGL ES in 15 years is the most prolific 3D API ever, and I'm going to show you on the next slide, it is actually still growing. So we released an update to the OpenGL ES 3.2 conformance test suite. Tons of bugs. It's actually a multi-person year investment from Khronos. We've added coverage, we've fixed bugs, and now we've released it 100% open source in GitHub. Anybody can see the source and play it and fix bugs and report problems. And the adoption of ES 3.2 is growing. A snapshot of the data from the Google Android site from November last year shows no adoption because that was in a previous version of the OS. And now just in less than a year later, 3.2 is already 30% of the ecosystem. So you have tons of users out there, hundreds of millions, ready to pay big bucks for pretty pixels. In terms of the ecosystem, there's been contributions of extensions from Mesa, Qualcomm, Intel, AMD, and a few multi-vendor extensions. So it's definitely a vibrant and lively ecosystem, still viable. OpenGL 4.6. Last year, we announced OpenGL 4.6, and since then, we've released conformance for it. The conformance was released in January, and then it was updated again in April. It's available on open source on GitHub, and Intel and NVIDIA are both adopters of OpenGL 4.6, and AMD, if they would allow me to say this, are almost adopters, just a few more weeks, and they'll be adopters too. And another new adopter, Amazon Web Services, is an adopter of OpenGL 4.3. So again, the OpenGL ecosystem is still growing. And there's more extensions, Mesa extensions, NVIDIA extensions, AMD extensions, Intel extension, and some multi-vendor ones. So still growing. And, oh, I'm going to do a quick wardrobe change. So I was wearing my... Okay. All right, so now I have my NVIDIA hat on. So just another example of the OpenGL ecosystem still being vibrant and valid. NVIDIA is going to release a bunch of new extensions for our new Turing, which was released on Monday, which was announced on Monday, which we'll be releasing soon. And there's going to be a bunch of new extensions. We have a variable rate shading extension, a texture space shading, so you can do object space rendering without rendering all those unseen pixels. And then a bunch of new shader extensions and a whole load more. So that's all coming real soon from NVIDIA. And after all of this 3D session, in the networking reception at 5:30, I'll be showing some Vulkan Raytracing demos on Turing. I have a Turing with me. And also we'll be showing some Insight demos. And another quick shout out, LunarG will be doing a survey later, and they have a prize. So if you could find the LunarG folks during the reception as well, that will happen. Karen or Carl? Okay, thanks. Yeah, there's a LunarG table, and you can fill out the survey and potentially win one of these. So that will be happening later. And that's all I have. Thank you.
So because we got a late start, we're going to try to not do questions right now, but we'll be around, and you can grab us now, you can grab us when we try to sneak out for a bio break or whatever suits you.
Is it good to go, or how should we go? Okay, hello everyone. I hope you are all enjoying SIGGRAPH thus far. I'm Lei, and I work on stability tuning within Google, and it's a pleasure for me to be standing here to give you some update on Vulkan shader compilers. So I will first talk about shader toolchain in general and introduce projects involved. Then I'll give you updates on GLSLang on the SPIR-V tools. And the rest of the talk will be focusing on DXC SPIR-V code gene. I will introduce its goal, and Ehsan following me will be discussing its status, feature coverage, and practical tips of using DXC. So we all know that SPIR-V is the center of the Vulkan shader universe, and it is the standard intermediate language of the Khronos group, and it is the only format that Vulkan drivers accept. But of course, we are not handwriting SPIR-V. We have our favorite high-level shading language, and we want the compiler to do the work to translate them into SPIR-V. So if you're coming from OpenGL world, you must know GLSL. GLSL is the language of choice in OpenGL, and OpenGL driver consume GLSL source code directly. But as said before, Vulkan drivers only accept SPIR-V. So the GLSLang compiler is here to translate GLSL into SPIR-V. I have a /shader_c here. Shader_c is Google's wrapper around GLSLang to provide a GCC clone-like command line experience and also better library APIs. One of the benefits of adopting the SPIR-V intermediate language is that it enables innovation on the high-level shading language, so you can use whatever shading language you want right now. For example, HLSL, and even design your own. So we know that HLSL is the dominating shading language in the industry right now, so it brings huge benefits to both the developer and the Vulkan ecosystem to support HLSL for Vulkan shader authoring. So that's why we had two compilers for it. And GLSLang pioneered it. DXC followed suit to make it great. This HLSL to SPIR-V compilation experience will be the focus of this talk. I will talk about these two compilers in detail more later. So with the SPIR-V generated, you still need a bunch of low-level tools to investigate and debug it sometimes. So that's the SPIR-V tools project. It provides a SPIR-V binary parser, assembler, disassembler, and also validator. What's more, it also provides a toolbox of GPU agnostic general optimizations. Both the GLSLang and DXC uses SPIR-V opt to optimize the raw SPIR-V generated. SPIR-V reflect is the project you'll find handy if shader reflecting is part of your workflow. And if you want to go back to high-level source from SPIR-V, so that you can target other APIs like OpenGL or Metal, you can use SPIR-V cores. That will let you to have SPIR-V as the single source of truth for your shaders. But we will not cover SPIR-V cores in detail in this talk. HLSL to SPIR-V compilation is our focus. So before diving in, let's step back and talk a little bit about history. GLSLang pioneered HLSL to SPIR-V compilation 6 months before Microsoft open sourced their next generation HLSL compiler. We thought it's a great opportunity for us to be contributing to share the front-end parsing, HLSL validation, and also involve in sync with the language, because HLSL is known to be a language without a public spec. So we started to contribute a SPIR-V code generation since April of last year, and we learned a lot from GLSLang experience. We still cooperate with GLSLang to provide a consistent developer experience. Fast forward to today, DXC has already outgrown GLSLang. It covers more features and handles more sophisticated code patterns. So we recommend DXC as the forward path. So here is a more detailed comparison of these two compilers. GLSLang accepts both GLSL and HLSL, but only generates SPIR-V. DXC accepts only HLSL, but generates both SPIR-V and DXIL. So DXC allows you to use one compiler to target both Vulkan and DirectX in the future. So both compilers support all three major platforms, but GLSLang is much smaller and embeddable, while DXC has all the LLVM clone heaviness. On the other side, DXC covers more shader model features, and it has full HLSL validation. Oops. So before entirely focusing on DXC, here are some updates on GLSLang and the SPIR-V tools. In the past 6 months, GLSLang has supported lots of new extensions, to name a few: distributed indexing, 8-bit and 16-bit storage for GLSL, and also HLSL functionality for HLSL. Now we can also link multiple GLSL compilation units for the same stage. GLSLang also improves its integration with other tools. It adopted the standard SPIR-V disassembly from SPIR-V dis, and also updated the incorporated optimization from SPIR-V opt. It emitted more debug information, also a bunch of other incremental improvements and fixes. So on the SPIR-V tools side, we were talking about legalization, SPIR-V legalization for HLSL previously, and we are happy to say that it works. A brief recap on legalization. We know that HLSL is a permissive and flexible language. Certain code patterns like grouping resources into structs or structs, and then passing these structs around into various functions, if translated, will cause illegal SPIR-V for Vulkan. Drivers will not accept that. So we need transformations to optimize to remove excessive function calls, structs, and temporary copies to produce more streamlined, simple SPIR-V. So legalization is just such a set of must-have transformations. It shares the same infrastructure as SPIR-V opt, and it is always run in DXC if necessary. So don't be surprised if you say your code still get transformed even you have optimization disabled. Maybe it's legalization doing its work. So on the optimization side, the SPIR-V opt is greatly improved and much stable right now. It has added loop optimizations, although it is not enabled by default in the standard recipe. It also newly supported many instruction combining cases. It has better dead code elimination and whole array copy propagation. The runtime performance is also greatly improved. I mean by 10 times, if not by 100 times. So for validation, it's getting better, it's almost there. And we now, among others, we now have built-in variable and resource layout validation. Error message is also improved. So onto DXC. So first thing first, our goal. We'd like to make HLSL for Vulkan shader authoring great, always, not again. So that naturally consists of two parts. The first is translate native HLSL features into SPIR-V for Vulkan. The second part will be expose Vulkan features via HLSL. We have been mostly focusing on the first part recently, and we are happy to see that we have basically done that task. The second task, we are also making great progress on that. Next, Ehsan will talk about details. Thank you.
Hi guys, thank you. My name is Ehsan. Thank you, Lei. I want to briefly talk to you about DXC. I hope you're excited about compiling your HLSL shaders to SPIR-V using DXC. First and foremost, we believe DXC for SPIR-V code generation is quite stable now. It's been for a while. Moreover, we have covered almost all native HLSL features that we're aware of, as well as all Vulkan KHR and EXT extensions that we're aware of. Also, since GDC, we have added better optimization support, as well as better debugging support, and we've also made it possible to compile and run DXC on Linux and Mac OS. In terms of the HLSL shader model, we currently fully support shader model 6.1 and below, and we're currently working on supporting shader model 6.2, and we've already finished implementation for 16-bit types. Moving forward to HLSL language features, we have had C-like feature support for a long time now, and we have added C++-like features supported over the last several months, things like namespaces, classes, the dis pointer, inheritance, etc., that are supported in HLSL. We now support their compilation to SPIR-V, as well as other common code patterns like grouping resources into structures, as well as aliasing structured buffers, things like that. As Lei mentioned, the other side of the story is bringing Vulkan-specific features to HLSL, and in order to do that, we have relied on the C++ attribute style to bring that information into the HLSL source code. And our philosophy is to be as least intrusive as possible, and we only introduce types, built-in types or methods when truly necessary. So using that approach, we've been able to support all the Vulkan 1.0 and 1.1 features, such as push constant, subpass input, etc. And we've also been able to support all the major KHR and EXT extensions, as well as some other useful ones so far, and we continue to add support for these extensions. So now I'll just quickly go over a few tips and tricks about using DXC, so that can hopefully help you with porting your workloads to compile your HLSL shaders to SPIR-V. First and foremost, we heard from the community that they want to have pre-built binaries, so we've made those available. From the latest master branch, you can download the binaries and use them. Secondly, we take documentation very seriously and we keep it up to date. So that's also available on the second link, and I highly recommend that you read it if you want to compile your HLSL shaders to SPIR-V. And in addition to that, you might look at the SPIR-V code and wonder why we've done some things in certain ways, and we have written some blog posts in the third link that can answer some of your questions. As I mentioned, we have also added Linux and macOS support. DXC is originally based on LLVM, so it could be compiled and run on Linux and macOS to begin, but certain Windows-specific techniques were added, such as COM and SAL, etc., which made it impossible to compile and run on Linux and macOS. So over the past several months, we have worked hard to implement adapters for other platforms, and it's now possible to compile and run DXC on both Linux and macOS as well. And we also have a continuous integration bot that makes sure all the commits to the Microsoft's master branch can also compile on these platforms. Just a quick note about resources. If you are compiling your HLSL shaders to SPIR-V, one of the things that you're going to be spending time on is going to be resource management. And the first side of that would be resource descriptor assignment. As I mentioned, we have used the C++ attribute style to allow you to bring some Vulkan-specific information to your HLSL shader. And we try to give you different mechanisms to deal with this issue, with this situation. One way to handle it is if you are able to change your HLSL source code, you can add these attributes to your resources to add the binding number and set number to a resource, as well as the VK counter binding for resources that have associated counters. However, if you're not able to change your HLSL source code, we can still leverage the register annotation in HLSL to map the space number to the set number and the register number to the binding number. However, there is no concept of the register type, so you might end up with situations where you have overlapping usage of the same binding number and the set number, and that's when you can use the command line options to shift the binding number for certain sets if you wish to. Alternatively, you can specify on command line a one-to-one mapping for every single resource that you have in your shader. The other side of the resource management would be the resource memory layout. By default, we use the Vulkan vector relaxed STD140 and STD430 memory layout for uniform buffers and storage buffers. I won't go to the details here, but all the documentation along with examples are available in our user manual that I mentioned earlier. Also, if you want to get a memory layout similar to what you would get out of FXC, you could use the use DX layout command line option. And if you would like to get a layout similar to the OpenGL layout, you could use the third command line option. Although I should mention that the second one, the DX layout, is not officially supported by Vulkan, but it happens that most drivers happen to work with it. We also heard from the community that they want to have support for pack offset, for example, which is a native HLSL feature for C buffers, and we have implemented that. So don't be shy. If you think there's a feature that you think is needed for this compiler, please file an issue on GitHub, and we tend to respond to them very, very quickly. And we've also implemented the VK offset attribute to help you with your struct offsets as another method to help you for memory layout. Just quickly, a note about optimization. As Lei mentioned, we will run the SPIR-V ops standard optimization recipe for you under the hood, which is equivalent to running the -O optimization level. However, if you want to run a specific set of optimizations of your own, you can specify it using the -O config command line option and specifying them in a given order that you want. And any optimization pass name that is acceptable to SPIR-V opt, you can mention it to DXC and it will take care of it. And also, as I mentioned, we have made debugging a little bit better. If you use a -ZI command line option, we will emit some debug information for you. Firstly, we'll put the full path of the main source file in the emitted SPIR-V. We will also include the pre-processed HLSL entry point in the SPIR-V. The reason we emit the pre-processed version is because we want to make sure that if you have include files or if your engine has added other boilerplate code, we want to make sure that you get all of that in your SPIR-V so that it makes it easier for you to debug. You will get what you would basically be running on the GPU. And we've also added some line information for certain instructions. Lastly, if you want to get some information out of it for SPIR-V reflect, you can use the -FSPV reflect command line option. I'm not going to go into details there either, but again, please refer to the documentation. Over the next few months, we'll be adding more Vulkan extension support. We'll also try to make debugging, add debugging information as much as we can to make debugging easier for everyone. And lastly, I just want to thank a lot of people who helped make DXC as good as it can be and make it possible to compile HLSL to SPIR-V using DXC. Specifically, I want to call out Greg Roth, who is an external contributor from the GitHub community and has helped us a lot with porting DXC to Linux and Mac OS, as well as other individuals from Google and other companies, and in general the community who have given us constant feedback and have helped us make it better. And I wish I had a Google hat to put on right now. Please drop by the Google booth. We'll be happy to talk to you. We're hiring, and we'd be happy to have you on our team. Thank you. Okay. Next up is Erik, I believe.
Okay. Good afternoon. I'm Erik Berdahl. I work in Adobe's Digital Video and Audio group. We're the group that does the professional video creation products that you probably have heard of and some of you hopefully love, products like Premiere Pro and After Effects and Audition and Adobe Media Encoder. And I want to continue our SPIR-V Love Fest section this afternoon by coming up to testify to you about what the power of SPIR-V is and how it's allowed me to do something that, frankly, years ago, a lot of people told me was completely impossible, and that is to take a fairly large body of OpenCL kernels and get them running on Vulkan with actually minimal effort. And I'm going to wave my hands at minimal effort while we tell the story. First, I want to take you back to last year in this session. Ralph Potter was up on the stage from CodePlay, and he unveiled to you all here the existence of a project called CLSPV. CLSPV is a compiler that takes OpenCL source code and turns it into SPIR-V for Vulkan. SPIR-V, of course, comes in two different dialects. We talk about SPIR-V for OpenCL and SPIR-V for Vulkan, and never the twain shall meet. Except they have a fairly large overlap, and you can do some really useful things if you're creative and sneaky and really smart and know how to use that overlap, and can, in fact, twist the arms of some compiler people to do cool things. Part of what I want to do today is talk to you not necessarily about how cool the compiler is, because it is, but talk to you about why this was exciting to Adobe, why we're part of this project from the beginning, and what we're doing with it today. Along the way, hopefully inspire you all to go out and do a few impossible things yourselves. Now, my story starts a few years ago, where conversations inside of my group look at saying, okay, so Adobe Premiere Pro CC, professional product. I take all of the code that's in Premiere Pro and I dump it into two buckets. One really large bucket is all of the user interface, all of the workflow management code, all the stuff that customers interact directly with that make that product an awesome product, that make movies and television, and it makes it the fantastic product that professional editors use. Another really huge bucket is what we call the Mercury Playback Engine. Mercury Playback Engine is one of the largest GPU compute applications you've ever seen. It implements a very highly optimized real-time video and audio rendering solution. So Mercury is the thing that allows our products to be able to decode multiple HD or 4K video streams, decode multiple audio streams, render them all together, apply effects, filters, create a video, and run it out to your screen. All of this happening in real time with the magic of GPUs. Now, this is all done with GPU compute, right? So, question, can I put the Mercury engine everywhere? This was the thought experiment we played at Adobe a few years ago. Have a few issues. One is Mercury under the scenes, all of the GPU kernels are written kind of in our own meta language that is easily translatable into CUDA-C, OpenCL, and Madill-SL. And that means we've got Mac OS and Windows covered no problem, because we can use all those technologies in whatever the user has on the system. How do I get to mobile? If I want to be everywhere, I got to be on mobile. How do I do that? Well, on iOS it's pretty easy. iOS has got Metal. So we already can do Madill-SL, so not too much work to go to Metal. That's a big lie, but I'm going to stay with that lie for the moment. But we can get to my iOS pretty easily. Getting to Android, CUDA doesn't work on Android. OpenCL doesn't really work on Android. You can get OpenCL implementations, but by and large, you can't say that OpenCL is part of Android. And Metal really doesn't work on Android. So in order to get to Android, we've got to go through Vulkan, right? And Vulkan's an interesting opportunity because Vulkan actually doesn't speak a language. It speaks SPIR-V. It speaks that intermediate lingua franca, right? So how can I get my kernels into SPIR-V? Well, this gets now to talking about how do you manage complexity when we're building software, right? In my application is very plastic. This is the easy thing to do. You can write code in an application really easily. Unfortunately, it's also really expensive. When I say that Mercury is one of the largest GPU compute applications, there are the equivalent of several 100,000 lines of OpenCL code that implement all of our effects and all of our processors. Rewriting all of that into something like GLSL or some other language that already goes to Vulkan SPIR-V is prohibitively expensive. So that's kind of out of the question for us. Next thing would be to say, well, can we get drivers to consume OpenCL SPIR-V? We know we can get to OpenCL flavor SPIR-V. Problem there is that drivers are really sensitive to quality and performance. And when you're talking about mobile devices, you also have to get those drivers out to customers, which is a really long haul. All of those things, frankly, we're really sensitive to. I don't necessarily want to mess around with the quality of drivers. I don't want to screw around with the performance, and I need them to be everywhere. So that's not a good decision for me. So we turn to the third leg, and we say, can we find a compiler or build a compiler that will take what I have and turn it into what I need? And it turns out that this has a tremendous advantage. And this is what we proposed to Google and CodePlay and say, come help us build this. Now, I've been using CLSPV for, I'm going to wave my hands generously and say about 2 years. And I'm here to tell you that CLSPV is actually a really, really interesting prototype. It's a very useful tool. Some of you may actually be using it. If you're not, take a look at it. It's really kind of cool. Compilers give you a great agility, right? So what we were able to do with the compiler is say, I'm going to take my code, I need it to be emitted now in this way that looks like something that would come out of GLSL or HLSL, something that's a graphics shader. Turns out the compiler can do some really amazing things. It can actually create 16-bit and 8-bit I/O. I know you've just heard that those extensions just came out. We've been doing it for 2 years. You can actually trick the runtime into making all of your 8 and 16-bit I/O look like it's 32-bit I/O if you have a compiler that's in cahoots with you. And so this is part of what we've been doing. Also turns out that your compiler can help you work around a bunch of bugs, right? So we'll start running code, SPIR-V code looks fine. We run it on a driver. Turns out the driver doesn't quite execute it the way we want. Well, that's clearly a driver bug. We'll talk about that more in a second. But the most important thing is if I have a compiler, I can tell the compiler to emit the code differently. And now we can play around with saying, okay, if I change this sequence so that it's semantically equivalent, suddenly the driver starts executing correctly. Okay. Now, when was the last time you heard somebody stand up and tell a story about finding a driver bug where code is being executed correctly and you were able to diagnose it, fix it, and then get it running in your application in under an hour without the driver guys getting involved? These are stories that we've been able to tell 5, 6, 7, 8, 10 times over the last several years, right? And this is part of what having a compiler will buy you. And it turns out that SPIR-V is really solid for allowing you to play in that white space. And the Vulkan implementations of SPIR-V are exceptionally complete for allowing us to play in that space. Okay, now, one of the results of this is that we are able to actually compile several 100,000 lines of OpenCL code, and for all intents and purposes, we didn't have to change it. It's a little bit of a lie. I had to change about 1/100th of 1% of the code. Okay, so for those of you doing the math, that means I changed less than 100 lines out of a several 100,000 line program in order to run my OpenCL kernels all inside of a Vulkan implementation. That's pretty impressive in and of itself. Part of the magic here, and this is if you're looking at doing your own language, the pattern we use is pretty simple. The compiler guys come to us and say, gee, this code that you've written doesn't work in Vulkan SPIR-V because Vulkan SPIR-V doesn't support some feature that you're using. So instead, you need to change your source code. You need to recode yourself. You need to make it look a little more like GLSL, and here's how you transform your code to do that. And through a long conversation and a lot of whiteboard time, we eventually come back to say, let's just have the compiler pretend that I actually already wrote my code that way. If the compiler can recognize that this is a bad pattern and that it needs to be rewritten in a formulaic fashion, just pretend I've done that, and then emit the code as if I'd written it that way, and then emit the SPIR-V properly. And this is what lets me run a huge OpenCL program with very few source changes. Okay. Another interesting thing about this is that we actually were able to find gaps in CTS. CLSPV's experience over the last couple of years has significantly improved the coverage that's in CTS. So we would find things where, as I alluded before, we'll execute some sequence, and one or more drivers will implement that incorrectly. And by the way, I'm just going to take a tangent and say I don't in any way mean to cast aspersions on the driver writers. We've had fantastic driver support going forward. What we find when we get into this is, yeah, no kidding, the drivers missed this particular sequence. It's not something that idiomatically is emitted by GLSL compilers or HLSL compilers. It's part of the SPIR spec, so somebody should have implemented it, but there's no conformance test for it. So the driver writers had no way to know that this particular sequence wasn't passing conformance. Okay, great, let's add a conformance test. So let's add a conformance test, and this is one that the GLSL compilers won't hit. That's fine. It's a conformance test. Go in, add that. Now we have drivers that are failing. The driver writers look at that and say, great, we'll go working on that and fix it. Meanwhile, I can go back to my compiler and say, how do we work around this? Let's change a few SPIR-V instructions. This is where like SPIR-V assembly and disassembly comes in really handy, because we can make these changes at a fine-grained level. Once we see, hey, the code sequence starts succeeding, starts doing what I want it to do, now we figure out how to build that back into the compiler. Again, a very exceptionally powerful tool. Okay, now, the last piece of this is what this really means is that CLSPV is actually a really useful tool. Now, I have to be honest, it's still a prototype, right? CLSPV does not implement the entire OpenCLC language. Turns out that's not a problem for me. It implements a lot of the language. It implements enough of the language that my program works. And they document up on their GitHub site. You can find a document that says, here are the OpenCLC features that we implement, and here are a few interesting and big ones that we explicitly don't. So it's also a prototype because, well, frankly, if you've used it, you may see that some of the error messages leave a bit to be desired, particularly when you start going into those realms where the compiler doesn't quite implement all of the language. You won't get a nice little compiler error that says, oh, this is an unsupported language feature. Instead, what you will see is something that is an internal compiler assertion out to your terminal line, followed by a seg fault by the compiler, and however that manifests in your build system. We've kind of accepted that as a substandard developer workflow, but once we get past it, it doesn't cause us problems, we move past it. Most interesting thing is that the code that does get emitted is actually very high quality, very performant, and always correct. We've had very, very few, in fact, I think I can count on maybe 2 fingers the times when we've got incorrect code having been emitted. And I've never been able to say that about any alpha compiler that I've used in 30 years of writing code. So this is actually an insanely useful product, so much so that even though it's a prototype, I'm building a commercial Android product on it today. Some of you may have actually heard of this product. A couple of months ago at the VidCon conference, Adobe unveiled a new product called Project Rush. Rush is a new video editing product. It's aimed at people who want to create video fast. They want to create video possibly aimed at social media. Rush makes it really easy to put things out to social media. But the most important thing, particularly for this group, is Rush has the same rendering engine that that exists in our professional products. And this goes back to where we started 3 years ago. I need to be able to take that same rendering pipeline that is part of our professional products and run the exact same code everywhere, including mobile devices, including on Vulkan. CLSPV has let us do this. SPIR-V is the enabling technology that's made this possible on Android. So that's my story. I hope that through this, part of what you've got is a little bit of inspiration, either to go out and try CLSPV itself, or maybe go out and build your own novel language. Build it on top of SPIR-V, and then come tell your story about how you have done something that somebody told you was impossible. Do we have time for questions? Yes. Okay, so questions? All right. Thank you.
Okay, the assertion that I previously made about no breaks turns out not to be necessary. So we're going to take an exactly 10-minute break So it's 3:23 now. We'll resume at 3:33.
Hi everyone, we're going to be starting again in about 2 minutes. Hi everyone. My name is Hai. I work at Google on the same team as Lei and Ehsan on the DXC team. And I'm here to put an end to this SPIR-V Love Fest because I've had enough. No, I'm kidding. My talk is entitled Mark My D Words. The title was it's very clever. Unfortunately, I can't take credit for it. Alon suggested it on a call, and so we just went with it. It was it's humorous and amusing. So this is the brief agenda of what I'm going to go over, and I have a little story structure that I'm going to try to weave this talk through and talk really slowly because I don't have a lot of content. I need to fill time. So I'm going to talk a little slower than I normally do because I normally just breeze through the presentations. But as graphics programmers, this scenario might be familiar to you. You're sitting at your desk, typing away furiously. You hit compile, everything looks good. You hit run, looks good. Splash screen starts up, looks good. You WASD, mouse input starts to work. All of a sudden, like, it crashes. But in this particular scenario, it crashes and there's an assert on VKQ submit. It returns error code device lost. And you raise your fist into the air. You're like, what happened? Like, what just happened? Why can't you tell me anything? The original language is a little more colorful, but since Khronos is a family-friendly organization, we had to clean it up a little bit. So we've all been here, and one of the unique things about Vulkan is that, well, not unique to Vulkan, but one of the things about Vulkan is that people have contributed, vendors specifically have contributed different types of extension that exemplify different parts of their platform and which eventually make it into KHR. And in this particular talk, I'm going to talk about an extension called AMD Buffer Marker. And what this extension does is that it allows you to track the progress of your command buffer to see, if there's a crash, which command it crashed on. And if you're clever, you can actually find out the shader it crashed on and maybe even the shader stage it crashed on. And if you want to try this at home, then you'll need a AMD GPU and one that supports Vulkan. And I'm not endorsing AMD GPUs, I just happened to be working on one, and I ran into a crash that was hard to track down, and I started cruising through the Vulkan spec, and I was like, what is this buffer marker thing? It seems it might be the right thing for my case, and it turns out it is. There's a possibility of a more general version of this coming in the future from Khronos, but for now, let's just, I'm going to talk about the AMD version. So this presentation is slightly color-coded. I've highlighted hypothetical questions that an audience may ask in purple. I've highlighted the code because I don't have any pretty pictures. And I've shortened some of the Vulkan constants because they are really, really, really long. And PowerPoint does not have autocomplete. Okay, so to get started with this extension, what do you need? Well, first of all, you need the extension. It's a VK device extension, so it has to be loaded at the device creation. What structs come with buffer marker? None. What functions? Only one. VK CMD write buffer marker AMD. That's a really long one. I'm just going to call it buffer marker, write buffer marker. There's not any specific memory restrictions. The buffer that you're going to write to can be host visible. And so here's what the function looks like. The parameters are, it obviously takes the command buffer, and it takes the pipeline stage that you want to write at. and it takes the destination buffer where it's going to write into the buffer that's going to write into, and the offset in the buffer that you want to write, and of course your marker value. And so you might be asking, wait, where does this marking the buffer thing actually happen? From the spec, the way that it happens is that you place the buffer marker command after the commands you want to mark. And when the stage reaches completion and execution, it writes the value into the buffer that you've indicated. And so if you indicated the pipeline stage to be the fragment stage, and so as soon as that shader completes the fragment stage execution, it'll write the marker into the buffer, so you know how far it's gotten. And if something happens before or during the pipeline stage you specified, then nothing happens at all. Whatever value you have in the marker stays there. So the code looks a bit like this, pseudocode. And so you have your draw command, your hypothetical draw command, followed by 2 markers that you want to write for your vertex stage and fragment stage. There's 3 draw calls, and if this completed successfully, this is what the contents of buff would look like. And so the next logical thing to do is once you've written to a buffer marker, a marker buffer, is to view it. So to view this, it's relatively straightforward. If it's a host visible buffer, you can kind of just print it any time, and you can, in this case, it will be printing to the console. Maybe not because I don't have an indel on there. Sorry. So practically speaking, where you want to trap this to start dumping buffer markers to be useful is when you receive a VK error device loss message on any of the Vulkan function calls. For example, in my case, I dumped the marker buffers when I received a error device loss on my VKQ submit, and I'll explain why in a minute. Okay, so another question you might be asking yourself, I see Erik nodding over there, is cool. So I can get the GPU to write a D word from the command buffer after it's as it's finishing up executing things. Why is this useful? And I mean, if you spend a lot of time tracking command buffer crashes, you probably get why it's useful now. But we'll do the exercise of going through this anyways. So let's go through a hypothetical tracking a shader crash. So in this hypothetical code, I'm going to mark all the values in the buffer to 0, and I'm going to record this particular command, or this particular command buffer with these draw calls and these particular pipelines and 2 markers for each one of the draw calls, right? And so I recorded on frame N, and I submitted it, and I go for present, and I move on to the next frame. I'm going to skip over all the details of synchronizing frames, etc. I assume you guys know all that since you're all Vulkan experts. Then on frame command, on frame N+1, I record the command buffer and I go to submit it, but I get a VK error device loss. And so when I receive this, I go and I start dumping the buffer markers, or the marker buffers, sorry. And I noticed that I noticed that only 1, 2, and 3 are written at offsets 0, 4, and 8, and everything else is 0. So something happened inside of pipeline state or pipeline 2's fragment shader. So this is where I have to go and look at the SPIR-V and the HLSL to figure out like what exactly happened, but it helped me at least figure out where something crashed. And so in a real world scenario, you may have hundreds or thousands of shader permutations. You may have 10, 20, or even 100 command buffers in flight. A crash can happen on any random frame. It could happen in any random place in a level or a scene. But if the crash happens to come from a shader, this is where VK buffer marker helps, because it helps you isolate down to at least which shader is crashing so you can begin the investigation. And I think a lot of us have been in the scenario where we have a really complex scene and something just crashed, and we're just sitting there thinking, well, what do I do? Like, I guess I go and start commenting out everything until the crash stops, right? And that's not a fun task, but it's a task that I'm sure we're all familiar with. And there's a few kind of strategies that you might want to use for if you want to explore this. Is you might consider encoding the buffer marker for values that make sense to you, whatever that happens to be. A really simple one is you can track like how far into the command buffer you went by just multiplying a number by the command buffer and adding a shader stage, and then just embedding or inserting a mark call after every draw call. You also may consider wanting to write start and end marker values. And so let's say you have like hypothetically 100 command buffers in flight. I'm not sure why you would want to do that, but that's a big number and it sounds scary, so we'll go with that. So somewhere something crashed. You have 100 buffer markers associated with command buffers. So you can scan through the buffer markers to find out which commands completed and which ones didn't. And the ones that didn't, you can start looking to see how far they've gotten. Usually it's just one that crashed. Okay, so there are some practical concerns if you want to start messing with this. The first one is the pairing of command buffers and buffer markers. Generally what you want to do is just pair one-to-one, and you want to avoid sharing the same buffer among command buffers that have but just by changing the offset, it gets a little confusing really quickly. I did that at first, and it just, my tiny little brain couldn't handle it, so I just went and created a bunch of marker buffers. I apologize that the word buffer is extremely overloaded in this presentation. So after I added a bunch of buffers to write the markers in, I got this nice little error message that said you exceeded the allocation limits. Awesome. So I went in and frantically created a sub-allocator very quickly. And it was simple because I just allocated a giant, I think it was like 2 or 3 gig block of host visible memory and just part and parceled it out. It's a personal project, so I'm free to be a little bit sloppy. There is a slight performance overhead for this. For me, it costs about 2 to 3 frames. And the other thing that you might want to consider doing is I always zeroed out the command buffer, the marker buffer, to make sure that I could, once I dumped it, I could see the progress. In the beginning when I didn't, it was just hard to see, even though I could kind of scan for the values of where it ended, but there were some extremely ambiguous cases and it just didn't really work. Okay. So as I said, this extension is useful for tracking down crashy shaders. It's not a magic bullet, and developers are still required to debug crashy shaders. Maybe in next year's SIGGRAPH we can talk about tools that help you track or help debug shaders. We'll see. It depends on how good the DXC guys make DXC. And so again, it reduces the need to go and start commenting out random code to figure out if you start crashing or not. There are a few caveats. So VK error device loss is the most useful error message to stop on. Other error messages may give you mixed results. So if you happen to run into an error message that isn't VK error device loss, you may find that a bunch of your command buffers show as completed and a bunch of them show as empty, but there's no in between. That at least tells you which ones got completed and which ones didn't start. Depending on your use case, it may or may not be useful. The other giant caveat to this is obviously you have to have an AMD GPU. And here's a little some snippets from my practical experience with this. So as many of you have seen this screenshot of Fish Tornado floating around in the Vulkan community for the last couple of years, I was trying to, ever since this got released, I've been trying to create the next version of whatever this is meant to be with lots of geometry. My experience with Vulkan has progressed about 3 years now, so I know a lot more than when I first ported this. Made a lot of weird mistakes looking through the code, and I was trying to read from some lighting maps, and it kept on crashing, and I couldn't figure out where exactly was crashing. And so this is when I started cruising through the spec looking for something that could potentially help me, because it was a large enough scene where I really did not want to go and start dissecting all my for loops and trying to figure out which draw call this was happening on. Although that might have been exciting too. So I implemented, I added VK AMD buffer marker to my render. It took about 2 hours, and again, I ran into the allocation limit, but I had to implement sub-allocation. About 10 minutes later, I was able to locate the source of the crash. It was a shader in the global emission lighting pass. And so what had happened was I had got a little bit overzealous with wanting to adopt the -f use DX layout flag from DXC, and I forgot that one of my hard-coded offsets was for a byte, was for an array in HLSL, which meant there was a 12-byte difference. And this reading garbage data led to all kinds of madness afterwards. So as I mentioned before, there is a overhead of buffer marking. It costs about for me it was 2 to 3 frames a second. It will vary for your use case. And actually the cost is kind of negligible, and I actually forgot it was running for a while. Until one day I ran into a different crash, and then I saw like my crash dump on the console, and I was like, oh wow, this thing has been running for the past week, and I had no idea it was on. So even writing a bunch of stuff to a host visible buffer is not that costly. But again, your mileage may vary. Test it, profile it. Okay, so we covered a little bit of, pretty much what this extension does, right? So it's kind of a basic building block for a debugging technique or tool, however you want to structure it. But if you're excited by it and you really want to turn it up to 11, instead of embedding into your app, you can write a layer that uses it. So AMD buffer marker plus layer factory could probably get you pretty far. This, instead of having to implement it into all your Vulkan apps, you can just load the layer and have it run at any time and have it go with whatever app you want. You can run it on other people's apps. You don't see what they're doing. And you can combine it with SPIR-V reflection to get more information. I used SPIR-V reflect, and I was able to grab the shader source file name. And so when I saw instead of just digging through the SPIR-V every time, it just printed out the source file that my HLSL compiled from. It does require some bookkeeping, though. You have to keep track of when the pipelines are created, which shader modules are loaded, etc. And if you want to go really crazy, turn it up to 12. You can combine this with VK AMD shader info, which requires even more bookkeeping, because that's what you do with debug tools, is you write bookkeeping code. And you can even have it dump to GCN when anything happens. And this, again, this is just ways to get you access to the data when you want to start looking through the code for debugging crashes. And that's pretty much it. My last frame is, I don't have a cool outfit change like Piers, but we are hiring. If you want to come join the antics that Lay, Ehsan, and I participate in, then come visit us at the Google booth. Other than that, any questions? Yes.
The 3 frames per second is insignificant if you have real high frame rate. What was your frame rate originally?
Sorry, can you repeat the question?
The 3 frame per second penalty is insignificant if you have a very high frame rate. So what was your frame rate originally?
Oh, great question. So my original frame rate was about, it bounced between, I think, 55 and 48. And mostly because, story time, when I was first learning Vulkan, I didn't know what instance draw did, like how it was implemented into the hood, and I probably still don't know some of those details. But for some reason, it penalized the draw. And so I would get this weird fluctuation every time, like a lot of the fish were on screen, because it just batched them and then it would call draw instance. And so if there was just like some fish, the shark, and the nice pretty water, then I got like 55, sometimes 58, and then other times it would just drop. But I never saw it go below 42. Any other questions? All right, so our next two talks, the first of which is from Dan Baker of, oh wait, no, we have one more question. Yeah. What happens when you don't get a good air code?
Yeah, like if I have a hang or like a driver crash or something like that, or blue screen. Is there anything?
Right now, there's not that, from what I know, there's not anything you can, if you don't get a good error code, the first thing that happens is the thing I mentioned earlier, is that you will end up with kind of binary states for what completed and what didn't. If you are fortunate enough to get a hang that you run into an error that results in a hang, a reasonable number of the time, it actually will bubble up to a device loss and then crash hard. And in that case, there's just enough window of time for you to begin dumping out the marker buffers. And in my case, I was able to drop out like pretty much everything before my system locked up and I had to hit the reset switch. So there's little windows and graphics programming helps you. Okay. All right, let me switch this. And Dan will be coming up here. Dan Baker, everyone.
So there are shirts outside, I hear. They're only $30,000 each. You can pay me here. It's a deal. I'll sign it for you too. Okay. So, wow, this is a beast of a notebook here. So I thought I'd back up a little bit, and I went back when they asked me to talk here, and I said, okay, let me actually go back and find some of the very original slides that I presented back in actually Mantle days, when we're talking about why did we build these APIs in the first place? Because I think it's important to ask, because it seems like we've taken this big adventure and everyone's asking, why did we build this? And so let's take a step back a little bit in time and go back to the very fundamental questions. So some of this will be a journey a little bit backwards for things that we were trying to solve back in the DirectX 11 and OpenGL days. And so one of the questions or complaints I hear is, a lot of people in this room are probably thinking, why are these new APIs so hard, right? And it's a common theme, like these new APIs are so hard, and you keep running into case after case of, and it seems to be slower than the old way. Like, why did we make all these APIs and make these big changes when we're going back, and it seems like it's harder to use and it's slower? And I'll go back and we'll say, well, actually, I think this is a myth. Next generation APIs are not hard, and at all. That's not the problem. The problem is that multi-core asynchronous programming is hard. If you have already built and designed your engine around that concept, it turns out that the old APIs make it almost impossible to work with, and they're incredibly frustrating and difficult to work with, and they cause all sorts of problems. So what you really need to learn before you even start saying, hey, I want to program in Vulkan, I want to do these things, like, let's stop and think about, well, what should you be doing in an asynchronous multi-core world where you've got lots of processors talking to lots of different devices and writing memory, and really start thinking about how that works. And we understand how you would architect a system around that world. When you go and you talk about the next generation APIs, they make total sense. They're like, oh, I get it, because I can't be locking resources, I can't be having synchronization points. These things that I have to do manually are actually godsends, because I know I'm not gonna like undo all the work I did to get the throughput. Don't do if possible, which is the thing that I think causing people pain, is you're taking an older, massive system that worked on the old APIs and say, well, let me just retrofit it onto the new APIs. You're not gonna see a whole lot of gains there, because it probably wasn't built around it in the first place, with the exception being when the code was being bottlenecked by the old APIs in the first place. So you really want to take a step back here and say, okay, well, how would you build the entire engine? And I want to talk a little bit about how Nitrous is built and our engine. Now, for those who don't know me, I'm one of the founders of Oxide Games, and we have our own proprietary engine technology called Nitrous. I thought I had a slide on that, but I guess it got lost somehow in my Okay, so this is sort of an example of a lot of engines today, and we call this a functional threading model. And so typically what you're going to see is things like, these terminologies. Stop me if you've heard this before. Oh, I've got my rendering thread. How many guys heard that? Like, that's something you hear. There's a rendering thread. There's the audio thread. In some of these cases, you might have a physics thread. And the idea is you're going to take a particular task and farm it out and put it on a specific thread. And this is really a retrofit on the fact that the engine was probably single-threaded in the first place, and you're trying to do is take some things and offload them onto their threads. So you end up with something like this, where you're not really threading that well. You're only on 2 or 3 cores, and there's these arrows or sync points and stuff. And when you start looking at it, and sometimes you're not even really effectively using more than 2 cores in situations like this. And then the GPU is that green thing sort of running in parallel. And one of the things that happens a lot in older engine architectures is they sort of lose sight of the fact, and the old APIs are really bad at this, of the fact that GPU is running in parallel to you. And it's really easy to inadvertently or not inadvertently cause the whole thing to stall, cause you to stall, and cause back pressure and all sorts of problems because that thing is actually running in parallel. But the API design in both OpenGL and DirectX 11 really hide that fact. And I don't think it was never a good idea, but they really, really hide the fact that that thing is running completely in parallel. And this is sort of a comparison, inspiration slide of like what that level of technology looks like when we keep adding more and more stuff on. Sure, it works, but it's getting pretty clunky to try and keep getting mileage out of this thing. It's not a very elegant approach long term, and you just keep adding more and more things to try and get a little bit better, but eventually it's sort of clunky. And the question is, like, is there a better way? And yeah, it's going to be more complicated. So let me give you a little bit of a breakdown on what nitrous works. Okay, so if we go back to this previous one, that's a typical engine architecture of, 7-10 years ago. This is actually what nitrous looked like. And I've got multiple things in here. So you see here that we have a central thread scheduler GPU messaging system, and we have all these different systems that are services that are all communicating via high-speed message channels. So this is a very radically different approach when we were looking at an engine. And if you've done hardware design, you're like, wow, this stuff's starting to look more like hardware rather than software. And this took a lot of work up front and a lot of experimentation, but this allowed us to decouple all these various things and really remove what I call implicit synchronization points. A lot of code is written in ways that cause the compiler and architecture to implicitly cause a synchronization when in fact these tasks should be run in complete parallel. So once we moved to this architecture, obviously what's happening was the DirectX 11 API was stalling the whole thing because it didn't behave well in this world. It couldn't just sort of farm out and process things in parallel. And you notice there actually have multiple GPUs here because it's not really that different in this world to talk to multiple GPUs as they're sort of independent devices. And in this case, all these things are like almost like different processors, even though they're not really doing their thing and then passing their messages back through interconnections. So this is the architecture that we went down. Now this is probably more radical than what you need to benefit out of Vulkan, but it really is the type of thing you should be thinking about early, is like, how do I get the entire engine running in parallel? And when you do that, you'll start to appreciate all the things that Vulkan has to offer. And this is actually a more detailed, the complete description of what's going on from an architectural standpoint of how we're working. And you see that we've got threading worker pools, we're coming in and out, and you start looking at this like, wow, that's pretty complicated. But that's how sophisticated a modern engine is going to be if you really want to use the system. And we've got message channels and graphics command channels, and all these things are going in and they're being arbitrated by our scheduling system. So, it's a little bit lot to take in. So kind of get me a step back, like, yeah, Vulkan's a little more sophisticated, but it's not really the API that's more sophisticated. We are switching from this sort of plane with all these propellers and things and fins that we keep adding to try and make it like, get bigger and stuff. And we really want is to rethink it and make something like a nice modern jet. And yeah, the nice modern jet's more complex, but it's obviously a lot better. So I guess I didn't encourage you say, hey, it's going to be easy. It's not going to be easy, but the difficulty and the learning curve is really more about that asynchronous coexisting model, that not the actual API itself. And when you embrace that, the API is going to make a lot of sense. Okay, so what was really going on in these old generation APIs is that we just had lots of little things that were piling up to make a really bad or impossible experience for us. And there are really two major problems that were requiring like a complete rethink. And these are like fundamental things. I mean, there's lots of little like warts, but these were the things that really got us. The functional threading model, which is what both OpenGL and Direct3D 11 were, completely throwed a wrench in any sort of distributed system like we're building. I mean, we're building, you know, this thing, and the APIs think that you're supposed to do this, and that just didn't work, right? And the other thing that was really getting us is the implicit hazard tracking synchronization. The APIs were trying to manage that completely, and that was causing implicit serialization all over the place. Where it's trying to track like every little detail. This is actually a major pain point even today that requires some automation, but that was the other thing, that trying to get to the point where like the API is capable of processing every possible combination that can happen was really just causing a lot of overhead. And then there are lots of obviously little things. The memory model, the binding model, and all these things were contributing to just a generally poor experience, but I think that those two things were sort of the crux of it. And a lot of people are really fond of instancing, and we played around with instancing. We were like, why didn't instancing just fix it, right? Why we added some features. I mean, OpenGL added instancing and bindless and all these things, and I was like, why didn't that fix it? Well, it turns out that the reason why it didn't fix it is because if you're at the point where you can instance, that wasn't the slow call anyway. It's the calls that couldn't be instanced and couldn't be done, all these things done to it that were slow, and we needed to make the slow cases fast and not the fast cases faster. And that's something you often miss in graphics. We don't care about that fast frame making it faster. We care about that slow frame making it faster. And this problem here is that those two major problems, there was no path to retrofitting either DX11 or OpenGL on this. We just couldn't change the API. We'd have to change the whole thing fundamentally because it was just a different way of thinking about the whole problem. Okay, so the theme being, you know, I'm deviating a little bit about like what Vulkan here, but I'm talk about like how do you get great performance on a modern architecture. I mean, I meant to have a slide on this, but like on Monday, AMD released a 32-core CPU as a consumer. So that's where we're at now, you know, 32 cores. So how do you use more than two, right? Believe it or not, we've done analysis, and the vast majority of games use between 2 and 3 CPUs, and we are shipping 32 right now, today. So it gives you an idea of how much infrastructure or performance is just on the table. I mean, all these resources. So how do we say, hey, maybe you're not using 32 yet, but you're really thinking about, if you're starting a game or an engine right now, 16, 32 are goals that you need to be thinking about. It takes a long time to build these systems. So what I found over the years is that there's lots and lots and lots and lots of talks about using more multiple CPUs and all the things that people do. And there's lots and lots of really bad advice. Like people who should know better. So first thing I'm going to talk about is things not to do that are commonly done. Spawning threads to handle tasks is generally not a good idea. That's spawning a thread is an extremely heavyweight operation. We're talking hundreds of thousands of cycles to do this. So taking a little API call on the Windows kernel and saying, hey, spawn off the thread, do this thing, return. I mean, that's a retrofit job. I mean, you're band-aiding something. You don't do that. Relying on the preemptive scheduler. The OS preemptive schedulers are not tools to be using for parallelization. There's a couple reasons why. First of all, the OS level synchronization primitives are brutal. Second reason is you get things that you don't think about, that if you're preempting a thread, you are going to be invalidating or thrashing your L1, L2, and probably a good chunk of the L3 cache. And once that cache is cold, it takes a while for that thing to warm back up. So you never, ever want to be in a situation where your CPU core is going between tasks. You really want that thing to be working on one thing, caches are warm, and then going on to the next thing, caches are warm. You do not want to be stalling this thing and then going back to the thing. You do that, you're burning an enormous amount of performance because you just invalidated all your caches. And going a more basic, functional threading in general is just not something that's going to gain good scalability. If you have a rendering thread, well, if there's one thread handling rendering, the most you can ever do is the amount that one CPU can do. It's Amdahl's law, and that's just like one of the strongest laws are, stronger than the law of the land. Like Amdahl can't be violated. You've got one task that's on there, that's it. So if you've got if it's 20% of your tasks are or your computation is rendering, you will never use more than 5 cores ever, right? I mean, you just know it's mathematical certainty. So in general, you want to get away from functional threading. You want things that can run in parallel. Now you start really tweaking it and rolling up your sleeves, and I've got these screen things, and having multiple cores. One of the things that is how do you make them fast? Because it's not enough just to put things in multiple cores. You want to avoid certain things, like multi-thread read of the same location. You can do it, but there can be issues with that. So that's okay. So you can do that. Multiple thread write to different locations on different cache lines, because there's one of the things that's missed is that there's this whole protocol, messy protocol on how caches work. So you can write really fast on different CPUs to memory, but you can't hit the same cache line. Once you do that, you serialize, all gains are gone. So you got to make sure that if you're having these systems, you're not hitting the same banks of memory. Atomic instructions are a caution. So how many of you guys have used atomics? I assume a lot of you? Yeah. So the interesting about atomics is that atomics serialize, and you'll get contention. So a lot of people are like, oh, if I use atomics, I'm going to be fast. Well, you will if you're not contending. So you end up with a lot of latency. So you have you've got to get the cache line in exclusive modes, 150 cycles, and assuming there's no conflicts, you've added, a fixed cost. That's not so bad. But if you've got a lot of threads all trying to access the same atomic, you've now serialized every single thread, and you've taken that machine that was running in parallel and ground to top. So you need to be careful with them. Atomic should be used on cases where you're trying to minimize contention. And reading and writing to the same location in general from different cores, that'll just, again, same problem. It's going to serialize you. So not as bad as atomics, but you'll have issues. And multi-thread write to the same cache line, boom. You turned your multi-core machine, you turned it into a single processor. It actually got worse perf. You'll actually have cases where you'll be really slower. So these are just general things to understand when you're architecting parallel computing systems. So I've talked about what not to do, right? So you're like, all right, what do you do? Like, how do you guys actually use a lot of cores? Well, the idea is that we want to break our work into smaller nuggets. And so this isn't a new concept that we invented. It's task-based systems, right? So you want to break things from one big thing into lots of little things. And this is just a better overall approach. And if you can queue up enough of these things, you can start really farming off whatever CPU resources and use a fairly simple greedy scheduling architecture to get a lot of parallelization. The key to making this parallelize well is having enough tasks. You want to break into as enough tasks as you can, as small as you can, so you've got plenty of things to distribute across a lot of cores. So let's go a little bit back into talking about generating command buffers in the GPU. We end up generating a larger number of command buffers in Vulkan just to parallelize the computation. So the idea here is the way we generate commands intrinsically. So there's a couple different passes, we'll get into it. The idea is that different cores are generating probably some number of command buffers, all in parallel with each other and out of order. That's also important. We don't generate these in order to the frame, and then we're operating on frame data. Now, the interesting thing about our architecture is that we have our own internal command buffer format. So that's a little bit oversimplified. Effectively, we have gone in and defined a very efficient, compact system that we can build our command formats into our own memory buffers. It's a lot simpler than the Vulkan commands, but it allows us to have a layer of parallelization before we even get to the API. And we did this because originally we were interfacing into DirectX 11 and things that couldn't build in parallel anyway, but we still wanted to be able to generate our own internal formats. But the interesting thing about this is that it's actually more efficient to do this, because when you're building up the command streams like this and not going all the way deep into the Vulkan stack, you're starting to hit the CPU in better situations where the L1 instruction cache, the L1 data cache, they're not tunneling all the way through this really deep driver stack. Have you guys ever put a breakpoint into or hit an issue inside the Vulkan driver? You know, there's really deep call stacks in there. So the problem if you intersperse that in your code is you're constantly going through a large amount of traveling, and you could hit all sorts of data cache issues. You're going to slow your processor down. So you actually are better off. We found generating some packets of data in one place and a smaller amount of codes that you're fitting well in your L1, and then handing it off to another system that's being shallower, and that's just a faster paradigm. It sounds backwards. It sounds like, oh, but you're reading data and writing it. But it turns out, because of the way the caches work, it's a better architecture. One of the things we do too is our commands are stateless. So it's unlike I mean, Vulkan's more like this, but each command references has a bank of all the state that's needed. So there's no inheritance of state, it's just all redundant. And we're gonna filter off in the processing layer. And it completely separates us from the actual specific API. It's relatively straightforward for us to build a new command, our own command interpreter to whatever API we're talking to, and what we really want is the fastest translation of our internal commands to whatever API we're talking to. And so internally we keep the entire frame, and then we do a translation. Okay, so one of the key concepts that I can't highlight enough is that the entire application, game, all that stuff needs to be exposed to the concept of asynchronicity. The thing is running in parallel, things are happening out of order, not out of order, but asynchronously. That needs to be understood. You're not going to make a phone call and then spin and wait to get it back. Don't make blocking calls. And so we expose directly the concept that that's going on. I mean, the whole engine is aware of this. And so we have a concept of a frame. It's actually a little more complex now, but there's more stuff than just a frame. And there's data. This is a frame, there's commands, and then there's data the commands will consume. And that's just a fundamental way of working. So if you look at the frame, there's a series of commands, there's probably command buffers, and they're consuming frame data. And then you have things that are persistent, that are not generated every frame. Textures, resource sets, transfer buffers, various things that are persistent across all frames. And the concept's fairly straightforward. We create two copies of our frame data. There's the EVA frame and not a frame. And in one frame, the CPU is writing to it, and the other one is reading from it. So it'll never have a hazard, and it's going to flop. It's just going to switch every other frame. And then, of course, we have to fence things to make sure that the GPU isn't getting ahead, or the CPU is getting ahead of one device or the other. There are probably more complex situations. I mean, people have tried to implement ring buffers, various things, but really this is going to work in 99% of situations. And the frame data includes constant data and any small texture uploads. Okay, so one of the things that's also a little more complex about next generation APIs is that you can't just delete things. Like, oh, I don't want that texture anymore. Oh, delete, in OpenGL or DirectX, or just like, hey, delete it. And you're like, oh, cool, I just deleted it. Well, all sorts of acrobatics had to happen to make that delete because the GPU might have still been using it. So another shot was you didn't have to manage it. But the downside is it was really hard to predict when that work item would happen, and really hard to predict that you wouldn't get a massive frame stall in some random spot because memory cleanup. And another thing that was really frustrating is a lot of drivers just weren't stable. You delete some resource, and because this code path was so complex, you get explosions. And then you couldn't even ship your title. Like, we used to do things like, just to give you an idea how bad it was, when we shipped Civ-5, we never deleted a resource. We recycled them internally because we did not trust the memory manager of the driver not to crash. And this was not uncommon for most games. Like, we could not trust the deletion code. It was too unstable. So even you talk about ease of use, but when you're trying to ship a product and you cannot literally trust the API not to just explode, well, that's broken. So Vulkan got rid of that complexity and said, well, it's on you. If you delete it, you better not be referencing it. So that was great, because then we could actually trust the API to delete things rather than trying this crazy layer on top of it. So we have a few queues we manage. We have a delete queue. We also have state transition queues, and we also have another, our own internal queue called unordered command queue. And that allows us to do, sometimes we have tasks that, like, say you're loading a texture off disk, and you need to run like a height map conversion to a normal map conversion. It's a common operation. Well, that's not really tied to a frame. It just needs to happen before this thing is used. So we have another side buffer that will flush before a frame, and you can do that and not inside the boundaries of a frame. And it's a little less efficient because we have to copy memory around, but that's the other kind of utility thing we have going on. So our internal command form I alluded before, we have about 20 different types of commands total. So not that many, so it's much smaller than, say, Vulkan. Now those commands don't map one-to-one to Vulkan commands at all. One of those commands may generate 15 Vulkan commands, for instance. I mean, there's not a simple one-to-one mapping at all. So we have a fair amount, two kinds of things. We have frame state, which is dynamic, and then persistent state. And so persistent state are things called resource sets, which exactly map to descriptor sets in Vulkan. We have shader blocks, which effectively map exactly to PSOs. And we have various pipeline state, like we have a state block of alpha state, a state block, and that stuff just gets converted into a cache from the pipeline state. So then we have the frame state, which is completely dynamic every frame, and that contains things we call, I'm sort of sidestepping the compute, but for normal draw primitives, batches, and shader sets. And the core of it is batches, which are draw calls, and they contain a primitive and a shader set. And our constant references are constants and things are going into our frame memory. And each one of these things is organized so that it has like a different frequency that's typical to update. And what ends up happening is these end up turning into part of the bind vector down at the Vulkan level. So we only have one of those. Okay, so this is a little more. Right, so resource sets end up mapping descriptors. So effectively what we just decided is that like, well, okay, we need to draw some line in the sand here. So in Nitrous it's a little different, you can't bind textures. How does that make sense? How can you not bind a texture? Isn't that a fundamental thing of the engine? Like everybody binds textures, right? Well, we don't bind textures. We call resource sets. You can only bind a group of textures during a thing. You have to put them in a group. It turns out that when you make that constraint, it's really not that bad for the engine people to create groups of textures. It turns out to actually be sometimes simpler and cleaner code. And we have automation routines that will sit there and group textures for you and give you a handle back. So it wasn't really a hard problem. And then we say, okay, well, we're gonna let you bind 5 of these groups because you're not gonna change them at different frequencies or different things. And so we can allow you to change 2 for every, or bind 2 for every draw call, 2 for a shader, and 1 for primitive. I'll get what these mean exactly. One thing we did too to clean up our whole thing is we got rid of vertex buffers. We just decided, you know what, we don't need a vertex buffer. We can just load it from the shader. And it'll just be another resource set. So if you guys have played around with Vulkan, clearly these are gonna map pretty much exactly to descriptor sets, which is true. They just map straight into it. So the nice thing about this, one of the requirements that we do is that when we create all these things, they're created statically. So we do not create in typical frame a descriptor set. They are statically created because there's no reason to ever actually change them. We don't do any of the caching or anything like that. That's just something the engine does. So we've eliminated a whole level of complexity trying to cache and build these things and manage all that. It turns out you can, with a little bit of pre-planning, you can get rid of the whole thing. All right, I've already talked about this, but vertex buffers, we haven't seen strong evidence, at least the hardware they've run, that we really need vertex buffers. And I'm sure there's hardware guys in the room screaming, no, but it just doesn't mean maybe at least like 0.1 millisecond in some hardware. It hasn't really measured it. Okay, constant buffers. So if you guys have used DirectX 11, concept of constant buffers. And constant buffers are really, really overgeneralized. So this is an interesting thing that we decided. Nitrous does not have a concept of constant buffers. We don't persist constants across frames ever. When you hit a new frame, all the data that the shaders are using from constants or globals are gone. They're zeros. I don't think you bother clearing it, but you can imagine there's zeros. And then when you go and render, you're responsible for filling out all the data again, every frame. So we don't attempt to preserve any of that constant data from frame to frame. And so when you want to bind a constant or upload something to the shader, all you do is there's a giant chunk of memory and you just not lock the memory, you just ask for the memory. You fill out the data because there's a structure that exactly maps to the data format. You write it, and then you tell the command, oh, that's the memory I'm supposed to use for these constants. And it's as simple as that. So effectively what you're doing is just writing the data out to a buffer and telling it, hey, use that data. But this works great. Now, Nitrous does massive numbers of batch draw calls. I mean, we can do 50 to 100,000. It's not even an issue. This is extremely fast. There's no reason to be doing any sort of management of constants frame to frame. It's just extra overhead. Don't even bother. Just throw it out and redo it. The only thing that we do a little bit differently is like with the animation bone data, we have go through a different path, and that's not even we still write it every frame. We just didn't want to dump all the data into one of these buffers just for size reasons. But keep in mind, like we're animating 10,000 things sometimes, so I mean it's an enormous amount of data. But be careful. depending on the implementation, it's possible in some configurations when you're getting these buffers and mapping them, that memory may not be on the CPU. So you don't necessarily want to read it back. You might want to buffer it and do streaming SSE or something. It just depends on the hardware implementation. We've actually seen cases where that memory lives can cause some interesting sensitivity issues if you make that mistake. So, like I said, you can simplify a lot of things just by not trying to save data across frames. Okay. So a draw call nitrous, going back before, it consists of these parts. So we have what we call a set of things to render. And that contains batches, a series of draw calls. Each draw call is actually compressed all the way down to 16 bytes. That's how much the data, the packets are and everything. And a batch refers to it has like a triangle count and a primitive count, you can see here. And it refers to a few resource sets, some constant, and those are just offsets into that buffer I was talking about before. There's pointers. And a shader set. And that's it. And a shader also has its resources, so you can sort of see that there's a natural frequency of things that are happening, and the shader references the actual block. Now we treat our pipelines, PSOs, we always treat them this way. There is no vertex shader, pixel shader, fragment shader at all. There is just a block of shaders, and all resources are accessible to all resource stages. There's no segmentation. It's all just one unified thing. So we just see from the API's perspective, our engine's perspective, there's a pipeline object. There's a thing that shader, we don't know what it does, consumes data, produces results, and that's all it sees. And any stage is all bound uniformly across the whole thing. And then the batch set itself contains things like what render targets, in that we have a render group object, it's a little bit different than a resource set, and blend state and various other things. So that's the crux of how our format works. So kind of interesting point is we really streamlined and pared it all down and found out that you really don't need a lot of these esoteric things. If you're starting from scratch anyway, you can just get rid of them, and it turns out you can render anything this way. It's fine. I mean, the resource sets can have lots of resources in them. You're not really constrained. Okay, so this is a little bit of a description of how our frame sort of looks like. We block on our last frames present job. Now, this is a little different than a fencing object or any of those things because what's actually blocking on our job, not and this is an internal consideration. One of the things that became a little bit complicated is we don't necessarily know what thread we're presenting on, at least we're on Windows, which caused some issues because there's a lot of software, including Windows, that sometimes assumes that you're presenting on the main thread, but we don't. When we have a job-based system, we don't have a concept of functional threads. So getting the mechanics of it, we might have some resource transition things that we have to deal with. Now, the resource transitions in our terminology end up being the series of the various Vulkan operators that I didn't get into too much, but we simplified the entire set of preparing resources. There's 3 different commands for transitioning the compression and flushing the pipe. We simplified that to one operation of what state is it going to be in. We process the kind of asynchronous commands, initialization commands. And then the big job is we translate the nitrous commands into Vulkan commands. Usually about 100 to 500 jobs because it's usually the number of command buffers have been generated, but it can be variable. And it translates them across all the cores. This actually doesn't take very long. I mean, we could do it serially on one core, and it's probably 3 or 4 milliseconds. Vulkan's so efficient to translate command buffers into commands. The simple fact is we did all this work. This is the really weird thing. We did all this work to make sure that we could run on all these parallel cores, and it turns out that Vulkan's so much faster to generate commands than the previous APIs that it almost doesn't matter. I mean, you could probably put it on one core, and it's it all happened in 4 milliseconds. So we still do it in some cases, but you almost don't need to because it's so fast. And then we have the deletion queues, and we have a series of queues as alluding before. We're tracking the frame time when you ask to delete something. So you delete something, it doesn't delete right away. It puts a marker on it and says, okay, well, you're on frame 20, right now and you ask for something to delete, I know that all the commands that possibly can be using this will be clear in 3 frames. So it'll wait, it'll tick it off, and when it's all the frames are retired, it will finally just say, okay, we're deleting it. And this way, the whole driver stack and all these things are depending on it. It's now our responsibility to know it's not being referenced, and we don't end up with random crashes, and hopefully that we can't track down. And then we handle memory readback. So one of the nice things too about next generation APIs, we can read memory back from the GPU. We can say, hey, when that texture, the CPU needs to consider it. And the cool thing about that is that, yeah, you could do that in Vulkan and DX11, but you'd stall the frame because it had to stall everything to do this. Well, we can pipeline this thing and know what frame that data is actually going to be. So if you would do a screenshot, something as simple as a screenshot, say, okay, you're going to do a screenshot. You don't have to stall the frame. We put the request in the queue when we do a memory scrape, and when we know that the command is actually clear, we do a signal back and say, oh, I got this data back. So now we can actually do memory readbacks on GPU without blocking anything, and we can guarantee it's not going to block. That's really nice. Okay. So what's the status? We actually did ship Vulkan, actually the Singularity Escalation Vulkan, actually I can't remember exactly when, it was like a year and a half ago, so you guys can mess around with it. I haven't actually looked at that implementation in a while, so people keep asking me all these questions about it, and I'm like, yeah, I don't remember, because we got it out the door and then we moved on. But it did work, and we were able to get it running quite well in Vulkan, so that's where we're kind of at. All right, so what's the conclusion? Vulkan's ready for prime time. There's been some great changes in the last a year, especially one of the big problems we had in getting, actually the biggest problem we had getting Ashes running on Vulkan was not the API at all. It was the shader compiler stack. We had all our shaders, we had like 10,000 lines plus of HLSL code. I think it was 20,000 lines, a lot in HLSL, and we needed a way to get it in SPIR-V. And I'm not handwriting or having our guys handwrite like 20,000 lines of code in like GL, so that wasn't going to happen. And at the time, the pipeline, the shader compiler stuff was pretty raw, but since then, a lot of work has been done on the compiler toolchain, and I've not used the latest one. Everyone tells me it's great, so that was a #1 concern, but that's starting to work pretty well. I would say that moving from, if you've got a DirectX 11 engine, that I don't have as much experience with OpenGL. Moving to DX11 to Vulkan is probably about the same as moving from DX11 to DX12. I mean, there's not really, like, if you're going to move from DX11, I would actually do them both at the same time. I would take both of them, set them side by side, just to make sure you don't do something that one API likes and the other one. It's really, they are much closer to each other than GL and DX was. So, if you're going to do it, just say, okay, I'm just going to do both of these at the same time. I don't even see a reason to not do that. Like in fact, for us, like we support both the X12 and Vulkan, and the app doesn't know there's a difference. I mean, it's just your ring likes API, and they look the same, and they're all just exposed. So that's it. I forgot to put my slide. I had one requirement. I want to put a hiring slide in because we're hiring too, and I totally forgot to put the slide in. But if you're interested, we're hiring basically every position right now. So, go to our webpage and you can look. And now I'll open up to Q&A. I'm gonna get a drink. I have 5 questions or 5 minutes? I have been told I have 5 minutes. I think you finished early, and I just ate that time right back up, didn't I? Questions? No questions?
I have a question. How do you deal with...
you got to repeat them.
How do you deal with task dependencies?
The task dependencies inside the engine? Okay, so that could be a whole talk on itself. We have this thing called an application graph, called an app graph, and so you mark out a whole subsections of graphs, and the graph has all the nodes in it marked for which nodes dependent on which other nodes internal to the graph, and then graphs can signal other graphs. And one of the important things is that the graph itself won't execute while another instance of it while that graph is running, but other graphs that have a dependency on it can up until they signal each other. and that's the highest level, the application level of the dependency. And then after that, we have a concept of task lists. And so you can spawn a task list, and at any point, the task list will send you a delegate, will signal you when calling a function when it's done, and then you can also spawn whatever job you want. So there's sort of two levels of it. The application has a series of these parallel graphs that are executing that have various synchronization points, and then at any point you can also spawn large number of jobs. So what we tend to do is you have maybe 100 to 200 like sort of big tasks, and then the big tasks will branch off lots of little smaller tasks. So we do about 50,000 tasks a frame or something like that. So we usually have plenty of little things to fill the graphs. Those lights are like, there's like I'm being interrogated.
Yes, that is really bright. Okay, so I want a devil's advocate question. I loved your first, your step back point early on.
No, I can see you.
About, you know, what's really hard? Is Vulkan really hard? No, it's really concurrent programming and asynchrony that's hard. But I want to be devil's advocate and say, okay, well, so looking at other modern APIs, let's look at Madill. Madill is claimed by many people to be easier to work with than Vulkan. I'm wondering, do they solve the same problems, or what's your take on that?
I'm not an expert at Madill. I've looked at it a little bit. I think Medill's a pretty clean API. I think they solved some of the bureaucratic problems, like the just nuisance stuff, and they cleaned all that stuff up. But I don't think they solved the parallel creation problem. Like if you want to actually talk to the GPU on a lot of different cores simultaneously, they still haven't really cleanly solved that. And in the short term, it's probably fine because you know you're in 4 or 8 core machines. But I don't see how you're trying to use a 32 core machine in the future, and you're gonna that's gonna work. No other questions?
Seriously, you don't use push constants, you don't use, I mean, Vulkan has all this hair to handle, you know, different kinds of constant propagation. And
nope.
You're saying you don't use any of that?
Not really. I mean, we use
just
the
read it from a buffer object.
We use one giant buffer. We have one. And basically, we just update the dynamic. So we have a dynamic descriptor, and we just say, hey, dynamic descriptor, point over here now. Here, point over here.
No.
Yeah, that's it. So yeah, pretty simple. I think that we sort of advocated for like a fast path, or saying, hey, just instead of a push constant, be like, hey, have a couple bind slots, like because you try and use very many, because if you use a lot, you're slow. So there's only like two or three of these dynamic ones per batch, so a minimal number. So the hope is the driver just says, okay, well, this is where your constants are. So all it really needs an index, rebasing index for it.
So like root constant table would be sort of maybe something you'd like to see, or?
I mean, we could. It's just like all we really care about is, so we just reduce to the fact of like every time I do a batch, I probably have 2 to 3 points where I'm like, hey, this is where a constant, sort of like a constant window, this is where you should be pointing. I mean, we always bind one buffer. That's the funny thing. It's like we never change the buffer, we just change the offset. So it's just literally, our hope is that the driver looks at this and says, I'm going to actually turn this into some sort of push buffer where I'm just taking the constant buffer and just pushing an offset down from the base thing. And it's fast. And it has been so far. I mean, that's what they're doing. But I mean, I could be fragile in some cases where a driver's like tries to do it in some poor way.
Cool. Okay. All right, no, you do the introductions. You did the organization. Thank you, Dan.
And next up, we have Miko from Unity.
Let's thank Dan again. Yay, great talk.
All right, good afternoon, everybody. My name is Mikko Strambori, and I'll be sharing some war stories about Vulkan in Unity today. This really ties in really nicely with Dan's presentation, as we have a large product with massive existing amount of content, so blowing all of that up simply isn't an option. So we're going to go through some horror stories of how we're going to shoehorn Unity to work with Vulkan. So, brief slide about me. I've been involved in the game industry since 2002, and I've been at Unity since 2013. I wrote Vulkan and OpenGL rendering backends, HLSL CC, our rewrite of it, and many other things. So here's a brief status update of Vulkan support in Unity. The first version of Vulkan rendering backend, it was released back in Unity 5.6. The latest official release, 2018.2, adds experimental Vulkan editor support, and the next upcoming version, 2018.3, will remove all experimental flags in anything Vulkan related. We have it running on Windows, Linux desktop, and Android, and feature-wise, we're pretty much fully complete. For example, you can take the Book of the Dead environment asset from Unity Asset Store, run it in Vulkan editor on Windows in 2018.2, and it'll work, it'll render correctly, it'll be fairly fast even. The few bits missing are native rendering plugins and async compute support, and native plugins is currently under development already, and async compute is planned right after that. So let's dive into how Unity does graphics abstraction. Here's a partial list of platforms Unity supports today. And as you can see, that's a whole lot of different devices and different programming environments. So we'll be needing a robust way to do graphics abstraction so that the high-level engine code doesn't need to care about it. On the high end, we're looking at desktop PCs and consoles. And on the lower end, we'll have to scale all the way down to low-end Android mobiles with GLES 2.0 GPUs, and even the Nintendo 3DS that doesn't even have any shaders. Luckily, we are dropping 3DS very soon. Therefore, the range we have to support is very large. We call the graphics abstraction layer the graphics device. The API has grown organically over the years. Unity started as OS X game engine and then expanded into Windows and mobiles and so on. So the design is limited by two major factors. First of all, the engine must be able to run on our lowest spec targets. And currently that means OpenGL 2.0 and by extension WebGL, which is essentially the same thing. This also forces us to have a base API that looks more or less like something you'd expect from the DX9 era that we can then augment on newer stuff. Secondly, the design is limited by the fact that we must offer backwards compatibility to existing Unity content within reason. This means that we cannot just remove a rendering feature unless we have a very good reason to do so. Implementation-wise, the graphics device API looks like your typical DX9 style immediate rendering API. So the high-level engine rendering code generates a stream of these commands, which are then processed by the render thread. And the granularity of these commands looks like so. Set render target, so clear the render target, set shader plus all its parameters, or draw mesh, etc. Unity has a few different rendering threading modes. This is the simplest one, which has been around in Unity for a good number of years, and it is called simply multi-threaded rendering, even though it's like just one producer and one consumer thread. But this is something that we can implement on all rendering APIs. Here the high-level rendering code generates a command stream, which is then serialized into a ring buffer and handed over to the render thread, where the commands are deserialized, and then the actual renderer-specific graphics device API implementation gets called. In this diagram, the only Vulkan-specific code lives in the blue box in a graphics device VK, and we can easily switch that to other rendering backends, such as graphics device GLES or graphics device D3D11, and the same threading code will continue to work unchanged. This diagram illustrates how the actual multi-threaded rendering mode works. As the name multi-threaded rendering was already taken, we have to call this mode graphics jobs. This mode needs a lot more involvement from the renderer-specific implementation. The main entry point for this mode is a function in the graphics device API called execute async. Effectively, what the high-level engine code is saying to the GFX device is that, hey, here's a callback, run it this many times, hopefully in parallel, and afterwards submit all the rendering commands each of these functions happen to generate to the GPU in whichever way this specific rendering API needs them. Now what happens is that the rendering backend will spawn many jobs and give each job a custom graphics device instance. This is effectively a subset of the full graphics device API, so as you cannot, say, create a texture from within a graphics job. So when running on Vulkan, each per-thread graphics device records a secondary command buffer, secondary Vulkan command buffer that then gets sent over to a Vulkan-specific task executor thread, which takes care of building the actual primary command buffer and related stuff. Let's look at the task executor thread in a little bit more detail. You could also call it the submission thread, as that's the only thread that actually submits any work to the GPU. This thread is also used when we are running in the legacy client worker mode, as this helps us to distribute work to more cores. As said, it receives secondary command buffers plus a list of software commands from the rendering threads, and based on those it does the following. Well, it synchronizes the completion of the graphics jobs so that the work gets submitted in the correct order. It builds render passes, it builds memory and image barriers, and things like resource copies and so on. It is responsible for acquiring the swap chain image and presenting it, and it builds the primary command buffer based on all of this and submits it to the GPU. Basically, in Vulkan parlance, it takes care of everything you couldn't do in a secondary command buffer. Let me now introduce what I call the first law of Vulkan resource barriers. If you think you understand Vulkan resource barriers, you do not understand Vulkan resource barriers. This law applies universally, except if your name happens to be Tobias Hector. So, why are the resource barriers so challenging in real-world engine then? You just make sure your resources are barriered against any previous access before rendering, and that's it. How hard can it be? Turns out pretty hard with a number of nasty corner cases. First of all, when there are multiple threads in flight concurrently, the whole concept of now or current state gets very fuzzy. In fact, it doesn't even exist. There isn't even a global what's the current frame number, because different threads can and will be processing work from different frames. However, we still need some place to keep track of the state of each resource consistently, and turns out this is the task executor thread. Due to how Vulkan works, and due to the fact that we have multiple threads in flight simultaneously, we have an ordering problem. Any resource barrier must be submitted outside a render pass. This means that when we run into a draw call that requires a barrier, we'll effectively have to go backwards in time and insert a resource barrier before the render pass we're currently building. However, we cannot just have a dumb list of barrier calls. There may be situations where different draw calls access the same resource from different shader stages, so we'll need to combine those barriers into one. We take care of all of this in the task executor. Let's look at how we actually do it. Each Vulkan resource and sub-resource carries a barrier state object that stores information about its current barrier state from the perspective of the task executor thread. It keeps track of the previous GPU writes to this resource that have not yet been barriered against, and other information. When the render thread is processing a draw call, or switches render targets or prepares for a compute dispatch, it can send a request to the task executor as part of the command stream that's produced for the task executor. It essentially says, hey, I'm going to access this resource like this from these shader stages. Make sure all the barriers are fine. The task executor keeps track of all the pending requests, and when it's time to actually start the render pass, it looks at all the pending requests, it ignores all that aren't actually needed, and combines the rest into as few Vulkan barrier calls as possible. However, if we did this for each and every sub-resource we use in a render pass, we'd end up with tons of barrier requests that would be clogging up the task executor. To prevent this, we do a slight optimization. Any texture or buffer we know that won't usually get written to by the GPU is deemed static. This includes static textures, vertex and index buffers, and so on. When the rendering code accesses these, It'll simply assume that the resource is already in correct layout and does not need any barriers. There are situations where the GPU does write to those resources, and for that we have a manual override. For example, when you do an initial texture upload via a GPU copy from the staging area, we manually add a barrier request after the upload that puts the texture into shader readable layout and barrier to be ready for all possible GPU read operations. Now let's look at a few horror stories from the time we started working on Vulkan Renderer for Unity. The first one is about shader parameters. So here's how Unity typically draws things when none of the shortcuts and optimizations are enabled from the perspective of the graphics device. First we get a setShader programs call. It says, here's a shader for you and here's a list of parameters it's going to need. The values for those parameters are serialized into this data buffer. Set this as the active GPU program. Before the draw call, we'll have to look into the Unity built-ins for all the world view and projection matrices in case the current shader might happen to access one or more of these, and update the shader parameters accordingly. Then we get to your very typical draw call, nothing special here. Afterwards, we may get another other call called setShaderPropertiesCopied. It basically says, hey, use the same shader and the same parameters you already had, except tweak these few things, and a partial list of parameters, so only the ones that need changing, and a value is serialized into the buffer. And this is, of course, a CPU-only buffer, because we cannot have any nice things. Again, we update the matrices and draw again. At this point, I assume every Vulkan developer in the room has facial expression something like this. Because none of this maps to Vulkan. This is a problem, and to be fair, it doesn't map to any other modern graphics API either. So why? As said, the graphics device API has grown organically, and this kind of approach made total sense on Lobodzinski ES and DX9. For example, on GL, this is just a handful of GL uniform calls and all well. On Vulkan or on new APIs, not so much. And this approach has a lot of problems. As the matrix update step is separate from the other shader parameters, we'll have to defer all constant buffer upload up until right before issuing the draw call. And speaking of constant buffers, or uniform buffer objects in Vulkan terms, this approach makes it super hard to reuse any of them. We have no idea whether each C buffer is supposed to be per frame, per camera, per material, or per draw, and whether we should try to keep them in some sort of stash for possible reuse later, either in the next frame or even within the same frame. And when we get a partial parameter update, it's even worse. It means that we already dispatched a draw call with the previous contents of the C buffer, so now we'll have to do a shadow copy from that and only update the needed parts. And yes, this is quite horrible. So this is how we ended up implementing this, and this is what's shipping currently. We tried various different strategies, doing a lot of caching and mem compares to try to reuse the buffers. But in the end, the fastest approach was just to get rid of constant buffers altogether and just pack everything into a single C buffer per shader stage. If multiple shader stages access the same parameter, we'll duplicate the data to each C buffer. And none of the C buffers are ever reused, so they're all single used. And they are uploaded using a large scratch buffer in CPU visible memory, and we keep that persistently mapped. Graphics jobs can allocate areas locklessly from that scratch buffer, and we cache all descriptor set objects and use dynamic uniform offsets when binding those buffers. So as long as we keep accessing different offsets into the same scratch buffer, we get to reuse the descriptor sets at a very nice rate. All of this is still a whole lot of work for something that should be much simpler. And here's one approach we started looking into at this year's Unity Hack Week. As you might know, Unity nowadays allows the user to implement their own rendering pipelines, and we call them scriptable render pipelines, or SRPs for short. Our new approach would allow SRPs to bind a constant buffer on a given name. This means that whenever the shader accesses a constant buffer with the same name, it'll use the values directly from that buffer, and the setShaders call won't have to spend CPU time serializing all those shader values. This acts as a sort of a short circuit over the whole ShaderLab parameter setting system. Similar to other shader variables in Unity, there's a per material version and a global version, so you can bind a C buffer into a specific material or globally. Using this system allows the scripting side to manage the constant buffer lifetimes and update frequencies and so on. Of course, this also means that the data layout in the buffer must match exactly with what the shader and the graphics API expects. This allows the render pipelines to experiment with different batching schemes, instancing, and so on. For example, filling up all the world and projection matrices into one massive buffer and then just indexing directly into that, or anything really. The SRPs would mainly use this feature for parameters that the render pipe itself has most control over. Per frame, per camera, and per light, maybe even some per material data where the SRP knows the parameters won't get animated. And this would only be accessible to SRPs, and as usual, no promises on when or if it'll ship. Second horror story, the grab pass. As you might know, the ShaderLab syntax allows the user to write a shader containing multiple passes with a few special pass types. One of those shader pass types is the grab pass. What it does is that it instructs the renderer to grab whatever's been rendered into the current frame buffer so far, copy it into a texture, and makes that accessible to the shader by a special grab texture name. And of course, this is part of the material itself, so we'll have no idea beforehand whether a draw call would trigger this. What's even worse, that this must work even when running from a graphics job. There are so many things wrong with this, but especially the tiled GPU driver devs in the room are probably going something like this. Okay, we were young and we needed the money. To be fair, it made sense on the DX9 desktop hardware, and it provided a cheap way to do distortion effects and whatnot. Unfortunately, the grab pass happens to be a feature that's fairly thoroughly tested by our graphics test suite, so we had to get to work. The requirement here is that any render thread must be able to stop and resume a render pass. This of course means storing everything. It includes storing MSAH surfaces from the current render pass and then loading everything back when resuming. The task executor must defer everything it receives until it sees the end of the render pass, because it may need to override the render pass store actions because of this. Of course, this totally kills performance on tiled GPUs when used, but it does render correctly. Oh, and speaking of the load and store actions, remember earlier when I said that we have set render targets call in the graphics device API? It keeps the render target active until the next set render targets call is made. It does have the ability to specify load store actions, but it's a bit of an afterthought, and the default parameter versions go to full load and full store for backwards compatibility, of course. Legacy rendering code is especially bad in not utilizing proper load store actions, even more so in the editor, just to ensure backwards compatibility in case the scripts want to do something silly. So when we do come across a set render targets call, we cannot do much anything quite yet. And why is that? It's because we'll want to wait and see whether there's going to be a clear call before the first draw, and therefore we can override the load action and save a lot of bandwidth. However, this puts us into a special kind of limbo. Remember that the barrier requests will have to travel backwards in time to be injected before the current render pass. Now, however, we cannot yet start a new render pass because we're waiting for possible override on the load action. So now any barrier request submitted between the set render targets call and the time the render pass is actually started, it must be moved forward in time instead. So they'll go into the same batch as the rest of the requests for the next upcoming render pass. This of course includes the surfaces we'll be setting as the active render targets, as those pretty much always will require layout transitions and barriers. And this is a notice for any of you who are writing your own render pipeline or migrating your code on top of SRPs. Please be extra careful with load stores and clears. Make sure you only use load action when you absolutely need it. There really shouldn't be terribly many such cases. And never just clear a surface without also directly rendering to it. This will result in an empty render pass on Vulkan and an empty rendering command encoder on Madill, and it's just wasteful. We also have a solution for the load and store actions. It's called the RenderPass API. It landed in Unity Codebase last year. It's mainly modeled after Vulkan's RenderPass subpass API, so it allows a subpass to read the current fragment value. On Vulkan and Madill, it's implemented natively, and elsewhere we emulate the functionality with a simple textual fetch. The API enforces an explicit start and end to a render parser and makes the load and store actions super explicit to the user. Again, only accessible from within the SRPs. In conclusion, here are some things we'd like to see in the upcoming Vulkan versions. First one is round-robin swap chain order. This means that we would know in advance which swap chain image index VK acquire next image will return. This is important because we need to know which image we'll be rendering into already in the render threads as we're building the frame buffer objects. However, the image acquisition has to happen in the task executor thread, so this would cause an unnecessary extra sync between the threads, and this prevents having different CPU cores be working on different frames efficiently. There is a workaround, of course, by making the swap chain one image larger than necessary, but there are drawbacks. Many GPUs don't support swap chains larger than 3 images, plus it uses extra memory for no good reason. So having a guaranteed round-robin order for swap chain images would be super nice for us. The second ask is the tile shaders. With tile shaders, I mean some sort of ability to access the contents of the current tile, and here with tile, I use a very loose definition of it. Basically, whichever somewhat local pixel area the GPU thinks is fast enough to access from the shader. This could be exposed either as a compute subpass or a pixel shader that could access the tile local storage of neighboring pixels. As even desktop GPUs are nowadays becoming somewhat tile-based recently, this could allow for interesting algorithms on both mobiles and desktops. Our immediate use case for this would be to be able to implement fine-pruned tiled lighting algorithm without flushing the G buffer to RAM. And I'm sure there are a lot of other uses for that as well. And finally, we'd like to see some improvements in the raw SPIR-V shader performance. It looks like the SPIR-V shaders tend to be slightly slower than their DX11 or GLSL counterparts. We've seen this ourselves and also heard similar reports from non-Unity Vulkan users. We've seen this on both mobile and desktop, but it seems to vary between GPU vendors, so it looks like there's some driver optimization work to be done. We do a few tricks to help SPIR-V performance, such as baking static shader branches into specialization constants and using push constants for very small constant buffers, and this helps a bit, but we still seem to be behind DX and GLES when it comes to raw pixel processing performance. And that's it for my part. Thank you for listening, and it's time for questions. Any questions? Go ahead.
So, I know you are the maintainer or the author of HLSL.
Yes.
You mentioned that SPIR-V shaders are a little bit slower. When the ones that are slow, are they coming through the HLSL flow, or are they coming through a direct compile?
They come through HLSL, but I mean, even manually verifying that they seem to end up using the control flow is similar, and both use the same amount of, say, registers on those GPUs where we can actually look at those data. It's just pixel by pixel on some platforms. They are slower, and we've been talking with those GPU manufacturers, and they acknowledge that yes, we know they are sometimes slower.
Slightly nerdier question. So FXC does its own layer of optimization on top of that. So I know you're coming from DXPC.
Yes, yes.
And does that help you or hurt you in any way? Because the translation, like I've looked at HLCC code, and I know the path that it translates to. I'm just curious if there's anything in the translation process that could be contributing to the slowness.
Well, I mean, it does a fairly good job of optimizing the code, like in getting it very tight, and it does a lot of like ugly tricks at times to get it what it wants. So we have to do a lot of analysis to like squeeze out the type information back from the fact that the DX bytecode seems to think everything is a vec4. But once that's done, the resulting code is fairly tight. And we use the exact same GLSL on GLES, for example. And there we know that we can see the performance difference on Vulkan versus GLES, with the shader being literally the identical. It just goes through GL slang then.
Thank you.
Were you pretty happy with secondary command buffer performance, or do you ever wish to write your own version of command buffering?
Own version of what?
Were you happy with the performance of secondary command buffers in the driver?
Yes, actually, good question. We have two modes for doing this. So when we run those graphics jobs, we generate, in this normal mode, we generate secondary command buffers there. We also have just a flick of, there's a switch in player settings, by the way, in Unity. You can, Vulkan software command buffers, by the way. You can, if you enable it, it'll instead go do pretty much what Dan described. So it goes to a serialized list of just raw Vulkan API calls. So the instruction cache keeps warm when we just play them back in task executor. But it's not a performance win. It's usually slightly slower. So there's no win there, at least in our tests. But we have both modes. We can run it either way.
Thanks.
Any more questions?
Yeah, I know. I'm the last man standing between you guys and Piers. So. Oh.
Any heckling? I have a more general, probably annoying question, but I know that a lot of the shader source is kind of a hybrid language in Unity. Is there a desire to have, say, direct SPIR-V from the developer?
Not really, because the basic idea is that whichever language the shader is in, we have to be able to retarget it on. Some of the devs will want to work on Mac, so we have to get a Madill out of it. We have to be able to run it on DX, whatever, on the consoles, everything. So right now, our pick for it seems to be HLSL or something that looks close enough to HLSL, just for the reason that that's what the shader authors are accustomed to writing, even outside Unity. We did this last Hack Week, a year ago. We wrote a prototype of being able to write shaders in C#. And it is actually really cool that you can write unit tests for your shaders and run them on desktop like this. But turns out that still, from technical artist or shader artist point of view, it has to be HLSL-ish. That's what PlayStation is doing. That's what Xbox is doing. They are all more or less HLSL. So it looks like that's the way forward. Whatever we end up being is some sort of augmented HLSL.
I want to keep asking questions if people don't have any, just to kill time. So I noticed that one of your wish lists for Vulkan was to return the index of the next swap chain.
Yes.
I think that's a problem that a lot of us have seen, because the acquired image call kind of requires some kind of blockage, and it's kind of annoying to deal with.
Yeah.
In my own design, I have it separated out. It just looks ugly. Would a handle suffice as opposed to an integer?
Well, whatever that we can use in the earlier frames to create or pick a frame buffer object, because we need to, when we start rendering to our back buffer, so whichever swap chain image is coming up, we need to have a VK frame buffer which points to the swap chain image. So at that point, we have to synchronize with the task executor to see, what is our current swap chain image.
Right.
And that's if we want to be as asynchronous, if we want to get as much overlap between the threads and frames, that's not good. That is a sync point. So it's an unnecessary extra synchronization point that prevents having different cores doing overlapping work in different frames.
So basically anything that allows you to figure out which thing to target afterwards.
I mean, round robin is the easiest way, because driver could then simply have its own remapping of those indices.
Right.
Well, okay, not
Possibly.
Really. Yeah.
I don't actually have a question for Mikko. I wanted to say if other people do, that's awesome. But I also wanted to kind of open it up, if people don't have more questions for Mikko, to you all for anything you want to ask of anybody, or stories you want to tell, or gripes. This is your chance. You've got a large fat target in the room, a whole bunch of people who work in the working group, and I would just like to take advantage of this opportunity. Of course, we have, they told me the beer will be here either at 5:20 or 5:30, so we'll see how things go. But I did just want to say, let's view this as a broad opportunity to ask questions in general.
Yep.
So I'm just curious how other people are tackling the issue of you develop for your desktop and then you want to port it into mobile. You have a few things, you know, kind of like what initiatives people are taking when going from desktop to mobile.
There are actually the Vulkan ecosystem today is in a fairly good shape, as we have all the validation layers we can enable on Android. We have RenderTalk that we can actually use a remote to get the remote frame from Android to see what's going on. It used to be a whole lot worse, but today I think it's fairly fine.
You said there's a place for gripes, so I want to point out it's a small piece of Vulkan desert, place that's not covered by Vulkan. I'm working on Windows on MacBooks through Bootcamp, and even though the CPU is 6th generation Intel and the AMD chip even states, the AMD software states it supports Vulkan, eventually it does not work. So I don't know if Apple is in the mix here or whoever. Even if you download the Bootcamp drivers from AMD side or from Intel side, you can't even start an instance. So if there are any Intel or AMD people here or somebody solved it, I'd be happy to hear about this.
Did you install the Vulkan SDK?
Yes, of course.
Okay, because that just like missing the DLL, that might be that's a common problem on AMDs. It doesn't, when it ships a driver, it doesn't come with the Vulkan DLL every now and then.
I have a weird solution for that, but I'm not going to say it for recording.
Hello, so I come from a slightly different industry. So I'm not involved in the games industry anyway, and I come from the safety critical side. So I actually work for an avionics company. And one of the key things that we've noticed is we've only recently, as in 2 years ago, actually got shaders. So that's how far behind we are with the SC 2.0. So we still don't have a lot of these fun, fancy things to play with. And one of the key things that we're finding with Vulkan is justification in our industry to explain why Vulkan's a better way to go. I mean, we still have limitations on multi-core on the CPU. So at the moment, we've got a lot of these things that come through. So one of the key things I found very interesting was at the start talking about the education side of it and trying to educate in schools. There's actually a few industries that still need that level of education as to why Vulkan's a different approach and why you can get different performance from it. So yeah, it's not a question, it was just an observation. So, from there.
I could have missed if you talked about this. I was just wondering how a ray tracing API fits with Vulkan, or if it's outside of Vulkan. Sorry.
It's not a fundamentally different problem from trying to integrate a ray tracing API into DX12. The problems are analogous. This is kind of an elephant in the room, so I should probably address it. You may have seen that on the slide, ray tracing is one of the things in our candidate box. We are, it's an interesting problem. It's a problem that requires a long time to solve. So we're looking at it now. The urgency of it is driven by what we see in the marketplace. So, there are many problems that Vulkan needs to solve to become, what we want to be, which is the preferred graphics platform for everybody on all platforms. It's a big goal. You have to ask whether ray tracing is problem one to solve. Well, probably not. There are others. It's something that we're tracking, but it's not something that we feel like, oh my God, we have to solve this tomorrow. So yeah, over time, it's going to become more important, and we're going to track it. And we are, of course, interested in the experience. It's great to watch some of the fun that people are having, trying to see if they can possibly do something with less than 500 million rays per second. But yeah, it's interesting. It's not a tomorrow kind of thing for us.
So one of the great things about Vulkan, of course, is that it's an open platform that anybody can add, innovate on, and it's a great innovation platform. So we, NVIDIA, with my NVIDIA hat on, we're working really hard to get ray tracing into Vulkan, initially as a vendor extension, but I think the ultimate goal is to make it a multi-vendor and eventually a Khronos ratified extension.
Lisi is telling me that we're good for now.
Okay.
All right.
Tom?
Okay, so Neil. Hold on. I can hear Neil trying to speak.
Oh, no, you're the last man. Oh, no, yeah, right. I got asked a question earlier, which was a good question. I just wanted to relay the answer. I got asked several times during the break, and that was, it goes back to Vulkan portability. There were some rumors when the first iOS apps shipped with Molten VK that Apple had rejected them in the App Store. That is a conspiracy. It's fake news. There was a problem, but the app vendor had just linked a weird library that was nothing to do with Molten VK, and it was an old version, and it triggered the Apple filter. So it's nothing to do with Molten VK. Apple has not put any barriers to iOS or macOS apps shipping through the App Store, so that's cool. And I actually had a question for the GE, Paul. Are you finding interest in safety critical Vulkan? Mike?
Yes and no. One of the major
Mike?
disadvantages we have is our level of legacy that we have to support.
Yeah.
And the cost of that and the age of the project means typically we don't have any engineers left, we don't know how that stuff works. And we don't typically have a lot of engineers who actually know OpenGL. So a lot of the time they're not willing to open up those code bases. So they want to be able to move to new platforms for new applications, but still be able to run that legacy. Perfect example is you may have a mission critical application developed in a military environment that's fully certified, that is 20 years old, and they still want that to run next to their nice shiny 3D map that can move around.
Right.
So because of that, they're quite reluctant to have any new APIs in that system without first showing what the performance gain is.
Okay.
Unless you can actually show and say, here's the performance gain, because typically we might have 35 watts of power to play with. Not a lot. So typically, unless you can actually show that your benefit is saying it's worth rewriting your app because this is the performance you're going to get.
Okay.
Sometimes it's a non-starter.
Okay, right, cool, that's interesting. Yeah, we should continue to talk, yeah. Okay, thank you.
I think, we can go on in town hall mode as long as you want, but we have apparently stuff to drink. Where did it go? I think we should go into chill mode. So So, I mean, lots of us are here, and we could keep the microphones on, I suppose. I think the audio-visual guys need to... Oh, that's how it works. Okay. Okay, all right. So I think we will say thank you all. Don't go away. We'll get the wall unzipped. We'll go into chill mode, and you've now seen enough of us that you can come and beat on us or harass us with hostile questions. Thanks all very much for coming. You know, it's exciting times. We want to hear your input, so please come talk to us. Thanks.